Hello, everyone, and welcome to Half Moon's presentation of Masonry Design and Construction. My name is Andrew, and I'll be moderating the program today. We will be starting here in a little bit, but before we do, there are just a couple things to go over. First, remember everyone that it is very important that you're logged into the webinar through your own connection. This is required so that Half Moon can accurately prove your attendance. Also, it's the only way for you to gain access to the quick quiz, which will be emailed to you at the end of the program today. And that's another requirement if you're trying to obtain your CE credits. Next to the right of your screen, you'll see a panel, and towards the bottom of this panel, you'll see a dark gray questions section. If you double click this, it will open, and this will be how you submit any questions you might have during the webinar. And then please feel free to ask any questions at any time, and we will answer them at the end of each section. For any other issues that happen to come up, you can call Half Moon's customer service at 715-835-5900, and I'll post that number in your chat section. You can email me, and I'll post my email in the same place, or you can just submit a question as normal, and I will get it that way. With that being said, I am pleased to begin our program and welcome our speaker for today, Sam Rubenzer, sorry.
Yeah, good. All right, so masonry design and construction. So today we're going to talk about a lot of different topics related to structural masonry design. We're going to talk about, first, we're going to go over some codes and guidelines for masonry construction, just kind of a broad brush overview of kind of what you should be looking for with masonry design and the codes that you should be exploring. Then we're going to look at the different types of materials that we have for structural masonry. We have a lot of the common things that I'm sure are all aware of, the gray blocks and stuff like that. But then we also have reinforced clay units, and we'll talk about some other stuff related to the materials of masonry. We'll get into some of the design requirements for designing structural masonry. We'll look at some construction procedures. We'll look at different types of elements of masonry that we want to look at designing. We'll briefly look at the sustainability of masonry, kind of look at some of the environmental impact of masonry and kind of how to help with some of those elements in design. And then lastly, we'll wrap up with the software for masonry design, just kind of talking through some of the different options that we have for design elements. So I appreciate the introduction. My name is Sam Rubenzer, work in Eau Claire, Wisconsin. I'm licensed in a lot of Midwestern states and structural engineer in Illinois. I went to University of Minnesota for a civil engineering degree, kind of emphasis in structural, and then spent a little time at Marquette University. I am a consulting engineer. A lot of the work that I do covers all kinds of different materials, just like any other engineer, steel, concrete, so on and so forth. So we cover a lot of different things. I'm a consultant for the International Masonry Institute. So you're going to see them referenced on many different slides and a lot of different topics that we use. So I certainly specialize in structural masonry design, again, here in the Midwest, but then also out east, out west, and kind of pushing the borders of the country. So kind of designing all over the place. So like I said, I'm one of several people that work at Force, so we have a lot of different things going on. Some of the different, excuse me, some of the different elements that we have or codes that we are looking at. There's a lot of different options for masonry design. Some of the primary ones that we'll focus on are the masonry codes that are referenced by International Building Code by IBC. 2022 TMS is going to be the current codes. There's 2016, which is the current reference code. There's 2013, and then back and back. We have different books and design guides. We have all kinds of different references here. So I just try to list a bunch of different references that I've used through the years and different types of, whether it's actual papers or books that I think can be helpful. And then lastly, you can see here some elements from the International Masonry Institute. They have a lot of different information. And then on the right, some of the different software programs that that I reference and look to. But we'll kind of reference those more during the program as we're kind of getting through some of the different options. So the first one, we're really going to be kind of focusing on code. So learning objectives for the code is just kind of talk through the development process of the TMS 402 building code and the 602 specification for masonry structures. Understand the relationship between IBC and TMS. TMS is the Masonry Society. That's going to be the current code for masonry design. Review and understand some select changes as they've been incorporated in the 2011, 2013, and 2016 code books. And then just understand how to implement the new provisions for design. So some of the development process for masonry codes, hopefully everybody's aware of the different codes that are out there. International Code Council, they really are trying to go with had been going with a 3-year cycle for their codes. IBC, International Building Code, has several sections that are relevant for masonry. Chapter 14, Veneer, Chapter 21, Masonry, and then 17 for special inspection. And then you also have the International Residential Code. So that's the general codes that everybody is aware of. And then we get into the masonry specific codes. The codes for masonry used to be the MSJC, the Masonry Standard Joint Committee, where we had several different code bodies coming together to put out a masonry code. So that's the MSJC, the first two lines that you see there, where you had TMS and you had ACI, and then you had ASCE. So as we look at those different code bodies, really most of the work was really being done by TMS. So in 2016, the masonry code just is now referenced as the TMS code. TMS 402, 602 are going to be the building code requirements and the specifications for masonry structures that both come in that one book that you see highlighted there on the right. So 402 code is going to contain the primary structural design provisions, but have a few construction requirements. Really, it's kind of written for use in design. And it's really trying to help designers come up with different design equations and really trying to help everybody get the masonry design information out there. 602 is really a specification for, say, contractors and inspector oriented. Certainly designers need to be aware of the different provisions in 602. There's a lot of things that are in 602 that we want to be using as designers as well, but it's written just a little bit differently. And like grout procedures and stuff like that is going to be stuff that's going to be 602. So a designer might not need to think about all the different means and methods for grout, but certainly being aware of the different options that might be selected by designers or by contractors. And certainly there's a commentary which is non-mandatory. So in the development, you have some mandatory language that provide minimum requirements for design. That's certainly things that we have to stick with. It's been a 3-year development cycle, but masonry is changing to a 6-year cycle. So just the 2022 code that just came out, that's been 6 years since the 2016 came out. And so that, obviously is, we get a little bit exhausted with constantly buying reference manuals and so on and so forth. We're trying to, hopefully with the different materials, kind of settle down into a little bit less frequent code cycles. Like I said, the main sponsor now, the main body that's going to be representing the code is going to be the Masonry Society. So it's not going to be a collection of all those different bodies. It's just going to be TMS. So that's why we see the references to the codes being changed. So obviously there's going to be IBC is going to be the model code adopted with or without local amendments, and then there's the masonry code. Generally, you have to make sure that make sure you check which masonry code is actually referenced by the different IBC codes. Obviously, that's always going to be important. The way the masonry codes are trying to be developed now. They're trying to be developed so that they come out a year or two prior to the IBC, so that all of the information in the masonry codes can be adopted into a similar year, maybe a year or two later, IBC code that can reference them. For the most part, IBC is referencing most of the information directly out of TMS codes. That's going to be, I think, very useful in our designs to make sure that we don't have multiple different codes that we're trying to cross-check and reference, and make sure that we're not using something that's, you know, not working in the IBC when it says that it's working in TMS. IBC is referencing more and more the masonry code as they do other materials. Just as kind of a review, trying to walk through and look at some of the different changes that we have for the different codes. The code and the commentary are now kind of in a side-by-side format, which is, I think, a little bit easier, similar to some of the other codes that are out there, instead of having everything kind of intermixed. The masonry code updated to the ASC 710, so that was kind of a major change. If you guys remember, for wind design and some of the different factors for wind design, empirical design, veneer, and glass unit masonry all updated to the newer design codes. We had a recalibration of stresses. Anybody that's been doing masonry design for a while remembers the 1/3 increase option that was formerly permitted for ASD when considering winter seismic load. So that was taken out. We just want to make sure that we just have some simplicity there. And so all of that stuff is still going to be there in terms of safety, but it's going to be more cooked into the capacities so that we don't have to worry about increasing stresses relative to those two different design loads. There's more harmonization of, and I see this certainly started back in 2011, that goes all the way to the current 2022 code, trying to bring together the ASD and strength design provisions so that you have similar results between the two different code options. And boy, I see that a lot across different materials. We don't want to have design, I mean, certainly there's preferences. Designers have preferences in terms of maybe the way that they learn or understand materials and design provisions between allowable stress and strength design. That really should come up with very equivalent results. Just because you have a preference in design procedures doesn't mean that you should have a completely different capacity that gets determined. So when the codes, especially the masonry code as it was developed, I mean, it definitely had, you know, different parts of the code that were more current. Strength design provisions tended to be more current than allowable stress design. So there would be new things that would be added to strength design provisions that weren't in the ASD provisions. So what that created was a pretty big difference in sometimes in some of the capacities, but we really don't want to have that. I mean, there's really no good reason for doing that. Just again, because of your preferences to the code doesn't mean that you should have wildly different answers. Certainly there are different procedures, so you can have some small differences, but we want to make sure that that kind of is brought closer and closer together. Some allowable stresses were increased. Some of that, sometimes that was, you know, reduced the impact of the 1/3 stress increase options. There was some conflicts between ASD loading provisions and the 1/3 stress increase in the ASC 7 prohibition of the 1/3 stress increase. So all of that stuff is certainly now been eliminated. For the anchor bolts, there was really no change in 2008. There was an increased allowables, kind of some harmony with, again, more with strength design. Bearing stresses increased from 25% to 33% of the strength of masonry, so giving a little bit more capacity there. And again, sometimes as these provisions change, it's maybe more testing was done to have a better comfort level with the overall capacities. It's not that masonry and bearing got stronger suddenly, but a lot of times that is what the code is. It's really just having a better understanding, and the code writers having more comfort in increasing capacities. So as you can see there, so nominal strength also increased from 0.6 to 0.8, and then it also makes it similar to other materials. Unreinforced masonry. Yes, we can still design with unreinforced masonry. That is definitely something that I'll reference from time to time today. I think that's a pretty important aspect of masonry design. Certainly not major structural elements aren't going to be unreinforced as we get into some large tall walls or shear walls. Large elements are still going to be reinforced, but we do have plenty of options in times where an unreinforced partition wall or different parts of masonry buildings can still be unreinforced masonry. And so that's a really important element for designers to remember and reference. So we'll talk about that certainly in different parts of the day, different sections as well. Flexural tension was increased by 33%, and axial compression was unchanged, combined with flexural and axial compression. So just some of the different updates that were done there. Allowable stresses, reinforced masonry, allowable stresses for axial compression not changed. Allowable steel was increased to 32 KSI for grade 60 steel. Again, more comparable to strength design. And then you have allowable masonry stress due to combined flexure and axial increased to 0.45 strength of masonry, again, to bring it in a little bit of harmony with strength design. Shear provisions now similar to strength design based on comparison to experimental data. Again, strength design provisions were maybe created more currently, so just bringing allowable stress design closer to that. So with the impact of ASD strength design provisions, so you have approximately the same amount of reinforcement as strength design. Really, again, two different procedures. We don't want to have wildly different results. ASD shear provisions requires significantly less reinforcement. So again, that's going to be important for some of the typical common masonry walls. And the shear provisions required approximately the same amount of reinforcement in 2008 for special shear walls. So those things are certainly important as well. So just kind of an overall example of the benefits. If we look at a building perimeter, say like a 350 by 500 foot building, 1,750 linear feet of wall. So if we look at 2009 in the masonry relative to that, number 5 at 24, you have a certain amount of rebar, a certain amount of grout. That certainly doesn't seem to be changing much if we go from a 24 to 32. So with the current code, or with that more current code, it does require a lot less bars, a lot less grout. It's really going to be saving, small changes in masonry designs, as I talk about that in different times, being more efficient with masonry. It doesn't have to be much, and you can really save quite a bit. Saving 33% of the grout or something like that could be a pretty significant amount of material that you can save. That and placed within confined spaces, all that stuff makes a pretty big difference. So we want to make sure that we continue to go with that. 2011 really, the Masonry Code really got pretty specific about the lap lengths, and IBC has certainly been getting us more and more information, or giving us more and more leeway to use the TMS, the Masonry Codes provisions for lap length. I still have people that will talk to me from time to time and using some of the old provisions based on IBC. But we want to use lap length provisions that were developed by the masonry people, by the Masonry Code. And here you can see the equation for lap lengths. Larger cover has been taken into account for the computation of lap length, changed from 5 to 9. So that certainly helps with lap length. Lap splices are permitted to be reduced when transverse reinforcement. So what does that mean? So anytime that you have a wall that you have vertical reinforcement that you're trying to lap, if you have horizontal reinforcement within that wall, where the horizontal reinforcement occurs where the bars are lapped, then we can reduce the overall lap lengths. And so that can certainly help, for different elements of the design. If you have a wall that's got both horizontal and vertical reinforcement, just detailing that wall correctly can really save on some of the overall lap lengths. And that can make a pretty big difference, certainly as some of the bars get a little bit larger. So it was really nice to be able to see that get added to the code and have that help us design-wise a little bit. In 2011, there was some deep beam provisions that were added for masonry, and this can be very useful as well. We'll talk about masonry and masonry lintels here at different parts of the day today. You know, if we look at a masonry wall, you know, one of the big misconceptions that I think people have is that we need some sort of different material to be added to a masonry wall to span an opening. Not only is that not true, there's a lot of different options for designing masonry, you know, for the wall. So the different provisions being added, really kind of a couple different images really do help. You know, deep beams could be added or looked at as the entire height of the wall above an opening. Really, when we have a masonry wall, we have everything that's staying interconnected there. Really, you can utilize, you would utilize the wall itself is going to be spanning that opening. It's going to be working together to span that opening. There's no smaller parts of the wall that can fail and the rest of the wall is going to stay in place. I mean, it's really going to be working together. So kind of giving us some deep beam options is really a nice way to look at the reinforcement that you can add for a wall above an opening and not have some other different material that's going to be needed. You know, there's an alternate beam depth, which would be a lower height. But again, I like how the code writers developed this and pointed out, you know, if we do want to look at the shallower depth, and maybe that's a little bit easier design-wise and a little bit less detailing requirements, that's the alternate. You know, again, you have the whole wall that's going to be working to span that opening. We might as well use that wall design-wise. So in those deep beams, you know, flexural reinforcement added in a tension area equal to half the beam depth, maximum spacing to be 20% of the beam depth or 16 inches. Joint reinforcement permitted as flexural reinforcement. I mean, certainly that's a very nice way to add some reinforcement in these deep beam areas, considering all of the joint reinforcement that's going to be added to our walls. We have shear reinforcement and different requirements for shear reinforcement, spacing for shear reinforcement, and then the total reinforcement for those deep beams. So again, it's a very nice option for being able to look at the design of the wall above an opening and how it can span an opening, and very nice to see that get added to the code. 2011 also looks at masonry infills, so unreinforced concrete or clay. So this is going to be developed more in later codes, and we'll kind of see some of that as we kind of review those as well. So you have participating and non-participating infill. Really, you know, the strength that you have in infilling this elevation that you see below is really going to be, you know, looking at the elevation where you have, say, a concrete frame or you have some sort of a frame, and you're infilling it with masonry. A lot of times it's not going to necessarily be a structural reason for adding in that masonry. Maybe it's an architectural, probably an architectural reason for adding in the masonry. So when we do that, we can either utilize it and make it a participating infill. And so then there's certainly design provisions that go along with designing it as a participating and resisting shear and maybe even axial loads, or a non-participating infill where it's just going to be there architecturally. And then what some of the design checks for that are anchor bolt installation. So we see some different developments for anchor bolts, and so as we're attaching to masonry, it's going to be important to utilize the current references for anchor bolts, references to running bond or not in running bond. Hopefully that takes out some of the misunderstandings between the different bond patterns. Obviously, there's the very direct stack bond, and then there's the very direct running bond, and then there's all the in-between. So running bond or not in running bond is maybe a little bit easier way to reference and capture all the different options that are there. You know, we don't see a lot of pre-stressing for masonry. Hopefully we see more and more as we go. I think there's a lot of different times for pre-stressing masonry. is going to help with masonry design. We see more prefabrication of masonry, which we'll talk about a little bit later, but that certainly can help quite a bit, you know, as we're going to be maybe building and shipping masonry panels. So having some provisions for pre-stressing and having some of those updated as well. Some of the other changes, empirical design. Empirical design is definitely something that I would love to see. Moved out of the code. I mean, it really doesn't have a good place in structural design, whether it's concrete, steel, whatever material you're looking at. Empirical design is really something that we used to use, something that we should be moving away from. So it's restricted in its use all the way back to 2011. You can see it moving further and further out. As we go here, we have some adhered dimensional stone provisions added, ties permitted for anchoring veneer, and so just other changes that we made in the 2011 code. AAC, that is a material that I think we can explore more. Autoclaved aerated concrete in the masonry code, it makes a lot of sense. It comes out as units. It certainly has joints, and you know, they're solid blocks, so they're a little bit different than kind of the standard masonry elements. They have a lot of great, you know, architectural reasons for using AAC. AAC is a material that we don't talk about nearly enough here in the United States, but it's definitely a material that's got a lot of potential for meeting different energy codes, fire ratings. It's a really great material for a lot of different options in masonry. So having that moving to a standard chapter in the code and not just an appendix, obviously the code writer is giving more and more attention to that material as well. QA tables being added, certainly that's going to be more helpful as we get into having better and better reviewing of masonry design, and hopefully having more and more confidence in design. Just some very straightforward changes. Grout height lift changed to 5'4". So anytime that we're writing a limitation for low lift grouting, we have to make sure that we reference that it's why 5'4" instead of 5 foot, because 5'4" is coursing. So instead of penalizing people and maybe having them at 4'8", then 5'4" would certainly more sense. So there's certainly more changes than that, but that was some of the highlights from the 2011-2013 code. The major thing in 2013 is there's a pretty big reorganization of the code. If anybody had the 2011 code or used 2011 code, you see that 2013, 16, and 22 are certainly organized a lot different, trying to break apart the code in different ways so that it makes a little bit more sense. To general requirements, design requirements, engineered methods, ASD, strength design, pre-stressed, and then AAC, all being different engineered methods. Prescriptive methods for veneer, glass unit masonry, masonry partition walls, all different options that are added to the code. And then you can see some appendices that are added in there. Sometimes, you know, appendices are interesting. It's either stuff that's moving out of the code, like Appendix A, empirical design, that's getting further and further out of the code, and then you have new things like design of infills or limit design of masonry being placed in appendices. So a little bit of a different look at, you know, kind of what the organization looks like. So 2013, again, it still references MSJC. 2013 Masonry Code, we have Appendix C, where we added limit design. It's a seismic design, optional. It's a sophisticated analysis method that certainly, I think, helps designers get a little bit more capacity out of their masonry designs. So limit design requirements for reinforced masonry structures in forest-based design. ASC 710 emphasizes strength. Displacement design emphasizes deformation. Forest-based seismic design limitations. Uncoupled cantilever walls are easy to design. Coupled cantilever walls are more difficult to design. You know, I think some of this stuff also comes into play as the more and more that we use software and software provisions, we have more options for looking at coupled walls or perforated shear walls. We have a lot more options that are being given there. For empirical design, empirical design of masonry 2013 appendix is going to be where the empirical design is now going to sit. Maybe it's going to hang around for a little while. Like I said, it's definitely something that we should be moving away from and more into the more allowable stress design or strength design provisions. You know, things that can be maybe looked at as more like a empirical design partition walls, where you really do have pretty hard guides for what are the loads for an element, you know, what are the different sizes of the elements. That's where, you know, partition wall chapter being added, not being part of the empirical design chapter, but really being its own chapter itself. Tables for 5 pounds per square foot, 10 pounds per square foot. So just you see an example of what we have there. Just a little bit more about partition walls. You know, really partition walls are an interior wall without structural function. They're really in there as it dividing, demising, you know, a wall to separate spaces. You know, in the code in 2013, it really did give it its new chapter, but then it also kind of talks about how, you know, there's really no forces that should be applied to a masonry partition wall that are not intended. So slipped connections at the top, no connections at the ends, really do help partition walls not see a lot of loads. And this is important, I think, in the masonry world, because if we look at making sure that we have efficient designs, we want to make sure that we don't have any unintended forces, so that we can make these walls as simple as possible. You know, if they have more reinforcement, there's going to be you know, a little bit better response, but it's going to be more costly. So making sure that we don't put too much in there. Smarter connections, we don't want unintended loads. We want to maintain efficiency though. We want to make sure that we don't design them as shear walls. If we do design them as shear walls, then it's going to get very expensive very quickly. You know, less grout equals less weight. Studies show a significant cost related to partition walls when more grout and reinforcement added unnecessarily. Really what we're looking at there is, you know, I talk about partition walls in this sense because, you know, we have masonry partition walls that sometimes will get valued engineered out of a project, and that can be unfortunate because sometimes those partition walls were not as efficient as possible. So really, what I try to get people to look at partition walls as, well, yes, if we had enough money and we had all the different options, we want to make the partition walls maybe a little bit stronger, maybe be a little bit conservative. But we don't want to value engineer out a conservative partition wall for a stud wall with chipboard on each side. I mean, why not go to the most efficient partition wall as your value engineering option? So that for me is always the important step to take. Make sure that we make partition walls as efficient as possible before we start value engineering things out. You know, looking at different seismic design characteristics that are in the code, you know, there's some really important ones that are in there. Reinforcement within the top of the walls, that's the second one from the bottom of the ordinary reinforced walls. You know, that's a seismic requirement for a seismic shear wall. That's not something that we need for partition walls. And then in the intermediate reinforced, vertical reinforcement no further than 48, that provision is also for an intermediate reinforced wall. There's nothing in a masonry wall that requires reinforcement to be at 48 inches on center. So we take some of that stuff into account, like recognizing these are shear walls, shear wall provisions. I can recognize that I really don't need a ton of reinforcement within partition walls. And so the code is going to give us, you know, some tables. We could also create our own tables where we have a lot of partition walls that can still be unreinforced. Seismic design categories A and B really do allow partition walls to be relatively unreinforced. We get into seismic design category C, we need some reinforcement. We still have many different partition walls and thicknesses that can be very lightly reinforced. And so that's going to be our efficient masonry partition walls, making sure that we utilize those. We get into higher seismic design categories, and more reinforcement is going to be needed and added. And certainly we need to go there because we're in a seismic area, but we want to be as efficient as possible. those places as well. In 2013, we had partially grouted shear walls that were addressed, and some refinement coming in the future. Moment magnifiers, modulus of rupture values were increased by approximately 33%, again, to help with some of the unreinforced masonry capacities. Masonry cement mortar permitted for fully grouted. Just a little bit of bookkeeping there. AAC infill provisions were added to Appendix B, Design of Masonry Infill. AAC, again, being something that is...
Hey, Sam, are you there?
Yeah, I'm here. Yep, can you hear me?
It seems that your audio may be stopped here. I can't... There you go.
Can you hear me, Andrew? Let me see. It looks like it's...
I don't know if anyone else can still hear them. Maybe they could say something in the chat. It could be my microphone, but okay. Sounds like it's just me. I'll check my stuff.
Okay, sounds good. Yeah, if anybody can't, if you guys want to pop in, do any chat or questions, glad to see everybody can hear okay. Let me see, other things that were in the 2013 updating for mechanical splices and reinforcement. Boy, that's for plastic hinge zones, something a little bit more of a seismic requirement. Joint reinforcement seismic clips for anchored veneer. Joint reinforcement can be used as primary reinforcement in strength design. Again, very, very helpful. Joint reinforcement is pretty common, pretty easy to add. It's going to be something that we can get into those mortar bed joints, and that can be very, very useful. So we'll cover that more. We'll get into the material section a little bit. One of the big things that happened in 2013 code, and something that we can talk more and more about, is there was a kind of recalibration on the overall strength of masonry. And this is something that's really, really important. We get into the design capacities of masonry. Prior to the 2013 code, we had a lot of people designing to lower strengths for masonry. And so really a lot of that stuff was based on old test data that really kind of pointed to masonry taking a little bit of a hit when we took our units and we put them in mortar. Really what we found in kind of that recalibration is that really the block strengths were going to be the same as the design strengths for the lower end values of masonry. So what I mean by that is, if I looked at the third row up here in my table, the 2000 psi strength of masonry in the far left column, all I would need is a 2000 psi block strength with type MRS mortar. That's the second column. If I have type MRS, I have 2000 psi block strength, then I can have my 2000 psi design strength. So there's no hit. There's no, I'm going to reduce the strength of the overall masonry wall based on putting those blocks in mortar. Prior to 2013, I would need to have a block strength of 2800. So you can see those 2013 values shown up there. I had to have a block strength of 2800 in type S mortar to have a design strength of 2000. So again, very, very significant. It really does kind of put the floor on designs actually at 2000 now. You can see some revisions in the code, but certainly anything that was, block strengths had always been at 1900. So you can see 1900 to 1900. What they did was just eliminate that. The current ESDM are putting out block strengths at 2000 is the minimum block strength. With that block and type S mortar, we can have a design strength now at 2000. So that's really a 33% increase in the typical minimum values that are used in design. And then achieving and meeting higher design strength has gotten easier as well. So that's going to be something that's pretty important for design. So looking at different compressive strengths, I can use a prism tests as well. Compressive strength of the block being at 3067 or something or higher is certainly something that can be stuff that we can utilize. 3067 is going to be something north of 2250, maybe just shy of 2500 design-wise. So we want to make sure that we utilize the full strength of masonry that we can. So again, a lot of times people were using the lower end of masonry, the 1500 as a default or standard. Strength of masonry can be a lot higher. It can be as high as 4,000. In fact, we don't have to stop at 2,000 now either. We can certainly keep going higher. Really, the point is making sure that you understand what the actual block strength are, and then you can figure out what the overall design strength is. You know, for masonry, the two elements that you need to define the overall strength is the block strength and the mortar type. Once you have those two components, then that gives you your strength, your F prime M. And then once that's defined, then we actually define the grout based on the other two elements that are there. Strength design in the code gave us a range of 1,500 to 4,000. Again, we can go up to 4,000. We can move all the way up to that. What we do is we just ask for higher and higher strength of blocks to be able to achieve that. Other things that changed in ASTM, minimum thicknesses for units changed, and that is going to give a lot better units for having better thermal performance. If we can reduce the amount of grout and reinforcement in masonry walls, and we have relatively thin web elements, when we have a lot smaller areas that are going to be creating these thermal bridges. So that's going to be something that was motivating the ASTM, the different code writers, to allow for smaller and smaller masonry elements, so that those elements can then be have a lot better thermal performance. And so we can see some of those changes as well. So within the table, we have you know, some of these different thicknesses and requirements changed in ASTM C90. And then from that, we have a lot of different types of blocks that are created in the web. Like I said, the primary elements there are going to be your web thicknesses that we're looking at for the different types of blocks that we have, whether it's a standard 2-cell or it's a bond beam block or an H block. I mean, that actually can have pretty minimal webs. An H block or something like that is obviously going to be a block that we're going to be used when we have more grout and reinforcement. So having a minimal web there maybe isn't super critical. But if it's an A-shaped block, there's some of the different blocks can certainly have plenty of benefits in having a minimal web area. More and more on the changes in some of the block requirements. Partitions and empirical minimum normalized web area required unless section is solidly grouted to be used. Prescriptive provisions allows the web shear stress to be avoided. Other things that I think are really important in some of the clarifications that were made in the 2013 code, I really like these little images and guides that were created. What this does is it helps designers see what the tolerances are for bar placement. The number of times that I've had people ask and have questions or have heartburn over bars not being exactly in the center of a grouted cell. Well, here the images really do give good, clear direction to designers and contractors as to what the tolerances are. So tolerances that are for the reinforcement, if the bar is not quite on center, we do have plus or minus an inch that you can have for the bar when you have like a 12-inch wall. If you had an 8-inch wall, you can have plus or minus a ½ inch. But that's a huge number to be able to see. I still have plenty of capacity with a 12-inch wall if my bar is a little bit off center, if it's 1 inch off center. Boy, that can be really helpful for designers to see that, to know that your wall is still going to have adequate capacity. Your bar can be plus or minus 2 inches along the length of the wall. Again, very, very helpful when we look at the overall design of masonry and construction of masonry as we go ahead and review things on site, giving you more confidence in the overall design of masonry. So knowing, again, tolerances are for knowing that you still have the capacity, even if the bar isn't exactly where you detailed it. It does have some tolerance in terms of where it can go, and your capacities are still going to be okay. Step bond beams, just some details in terms of how we can step bond beams. So it's nice to have some of those details added as well. And then more and more changes. So getting into 2016, something that's more and more current. There was some really big changes there in 2011 and 13. I didn't want to kind of brush over it just because I think there's a lot of people that are still designed to some of the early provisions pre-2011. So covering some of the stuff that was covered in those two codes, I think was really important. 2016, some of the highlights are going to be shear friction strength provisions were added to both ASD and strength design. Shear transfer across horizontal interfaces and walls subject to in-plane loads. Subject to in-plane lateral loads, walls that have a low axial compressive load and a low shear span ratio are vulnerable to shear sliding, which normally occurs at the base, function of the roughness of the base. You know, all the different things being added and confirmed in the 2016 code. Other things, reorganization efforts continued, moving common provisions into Chapter 6, reinforcement, accessories and bolts and stuff like that, that stuff being added to Chapter 6 as well into the design chapter. Splice and development length requirements were put into Chapter 6 and removed from individual chapters, which is nice. You know, the more and more clear that it can be. Let me see, nominal bar diameter requirements. Bar diameter should not exceed 1/8 the nominal member thickness. That could be really helpful in terms of understanding, you know, masonry having confined spaces. What the code writers are trying to do there is prevent really big bars from being added to really thin walls. Obviously, that's not going to make a lot of sense. So it's just trying to give some guidelines to the overall maximum reinforcement that would be added to walls. 2016 previous tables for 5 and 10 for unreinforced masonry walls were included. Concern expressed for seismic loading, limited use for designers. New tables have height to thickness and length to thickness lateral loadings for 5 to 50 PSF. So kind of trying to expand upon some of the different loads. I mean, you have all kinds of different types of buildings and structures and different loads that you maybe have. So some of the different tables, just as an example in the new code, giving you the different pressures from 5 to 50, and then giving you again the LT or height to thickness ratio for ungrouted walls, really is going to be able to give us a pretty clear definition in terms of what we can do design-wise. Load terminology, make it more consistent. Obviously, that's better. Level stress, level loads, strength level loads. So just a little bit of clarity there. Definitions were added for beam, lintel, pilaster, and cavity, as well as modifications for collar joints. So just trying to help clarify some of those things. Just kind of pointing out some of the different elements that we have here. Lintels, beams are really going to be the area that's going to be spanning an opening. It's going to be the length, the clear span, plus the depth of the member, minimum 4-inch bearing, deflection limited to L over 600, consider horizontal bending. You know, the thing with lintels is pretty common to have bottom bars. Top bars are, I think, things that we should be considering for lintel design. Again, it's the top of the lintel, but it's, you know, well within the space of the wall itself. You know, if we're looking at horizontal bending, especially making sure that you have some balance in this element that you have in there for having horizontal bending, having top and bottom reinforcement certainly makes a lot of sense. Lintels also have both positive and negative moment regions. when we have finite element analysis designs, which we'll see towards the end of today, some of the different loads and forces that you have there, top and bottom reinforcement can be very helpful. Stirrups, you can certainly add them when you had limited depth, but adding more depth to the overall lintel will be a much simpler way of solving that. So lintel beams are certainly those elements. Columns, within the code, we have a minimum side dimension of 8 inches. So yes, an 8 by 8 inch item would be a masonry column. Reinforcement between 1/4 and 4%. Minimum of 4 bars, lateral ties, at least 1/4 inch diameter. So like a number 2 would be the tie that would be needed. So that's kind of the standard column provisions for masonry. So that's quite a bit of reinforcement, especially the minimum 4 bars. Within the code, they also have now lightly loaded column provisions, which are allowed in seismic design categories A, B, and C. Anytime that you have less than 2,000 pounds of force, no more than 12 feet high, the minimum reinforcement that you need to add in that lightly loaded column is just one number 4 bar, no ties. So that's certainly a very nice element. I always like to ask the question to designers, what is a column? A column is going to be that isolated element that's going to be away from the rest of the wall. The wall, if it's a section of wall next to an opening, that's not a column. The code writers did not define that as a column. It's certainly meant to be part of the overall wall and should be reinforced with wall provisions, not column provisions. Could be considered a pier. I mean, it could be something like that. So really what that does is get, those isolated elements away from having all that stirrups and everything that you have to add to those elements. The one caveat that I make to that is if you would have some of the material in there for a lintel design, then you could certainly be kicked back more to a column. You could actually create a hinge in that wall where that element is actually maybe even a cantilevered column, something to prevent that hinge from occurring. So what is a column? What is a lintel? Some of those things are important to look at design-wise. Tables instead of written provisions incorporated in several locations to make it a little bit easier. Obviously, trying to make using the code a little bit better. Just some examples of how that was being done. So again, just some cute little reference tables instead of long descriptions that are trying to explain the same thing. Hopefully that adds more clarity. Hopefully that gives designers a little bit better options for design. Distance between the inside face of veneer and backing increased from 4.5 to 4 5/8. Looking at going all the way to 6 5/8 inches in later codes. Anchored veneer 6 5/8 maximum space from inside the veneer to the backing. What some of the different requirements are to be able to do that. Adjustable anchors with 2 or more W2.8 wires, kind of the minimum. So pretty heavy wire. Barrel anchors. Masonry backup can also be used. Tab anchor with a minimum of 2 eyes, inside face of veneer to end. So giving it that larger space is certainly, as we have more and more insulation, we have thicker and thicker walls, having that larger space can certainly be very helpful. Quality assurance tables were rewritten and simplified. Some of those quality assurance tables that are there. So hopefully the code getting a little bit easier to use, definitely getting thicker and more things being added, but hopefully getting easier to use with some of those different tables being added. Kind of 2022, some of the major elements that are being added here. Now, again, these aren't going to be showing up in most people's designs quite yet. They're going to be referenced in a IVC that's probably not quite referenced in too many places. But there's some veneer provisions giving some actual forces for those ties. So again, as we have more and more creative designs, we have more and more different options for tying veneers back to structures. So hopefully giving a little bit more of attention to what some of those design loads are and what some of the different ties that would be allowed for that would be. Also in the veneer design category, trying to point to having stiffer backups, or actually giving what some maximum deflections that would be allowed for the backup when you have a rigid veneer. Obviously, you don't want to have veneers that are cracking too much or are moving too much. So giving some references to what the actual backing should be for stability wise for the veneer. Other clarifications that were made as you look at reinforcement. One, old codes had different bar sizes that were allowed within different sections of the code. So strength design, for example, had number 9 as the maximum bar. Allowable stress design had number 11. So now just giving one bar size as a maximum for either strength design or allowable stress design. The reason for that, I think, was just the testing. Again, they didn't test strength design provisions for larger bars, so it just stopped at number 9. I don't think that we should be using 11s often within masonry walls, but it's nice to have that option, I guess. I don't think you should be using number 8s and 9s for that matter, but anyway. And then giving a little bit more definition to the amount of reinforcement that's added when you have H blocks or you have stretchers that are used where you have some flanges that extend past those cells. Those do create a smaller actual net grout area. So different reinforcement maximums because of that reduced grout space that would be common. Again, all of that stuff I think is stuff that we can as designers exceed from time to time, but I think that we have to be careful when we do that. I think we have to really think about dealing with these confined spaces and overlapping masonry elements and mortar fins that can be created. Anytime that you reinforce these masonry walls, you're dealing with these confined spaces that are moving around a little bit. The code's really trying to give us some really good guidance as to the maximum reinforcement that would be used within these walls. Other things in terms of different provisions for net shear area, trying to define that more better as well. So a lot of different codes, a lot of different options. And then the last section of today is really going to be looking at some of the different softwares. And really, I think the rubber meets the road in terms of the different software programs and what actual codes they actually have referenced. So we have a lot of different softwares, and I'll cover these more later today. But I just threw these two tables in here, and again, we have these in the sections later today. But this is really kind of pointing to different software programs have different code sections that are actually covered. So being careful with making sure that you use software programs that use the current code or use the code that, so this, I would call these component design softwares where you design one-off elements, or some of the finite element analysis programs, RISA and RAM, how they cover codes. So just a really quick, in conclusion, 2011 masonry is in 2012 IBC, 2013 is 2015. 2016 masonry is going to be in the 2018 IBC, and then the 2022 masonry code for reference in the 2024 IBC. So, code, hopefully it continues to make things a little bit more clear. Obviously, they have more and more things that are added to the codes, but hopefully it's going to keep giving us more guidance, more harmonization between strength design, allowable stress design, reduce some of the confusion, stuff like that. But there's other things certainly that the code can go into. And so with that, it kind of takes us to the end of that first section. I don't know if you guys have any questions. It was just kind of a pretty big overview in terms of codes that are out there and then some of the recent changes for masonry codes. All right, so we'll take just a couple minutes here. I'll just kind of keep a look at the questions. In the meantime, I'm going to switch over to a different presentation if I don't see too many questions in the next couple minutes. And then just a quick, make sure you guys are all still awake. Can everybody still hear me okay? Is audio? Was that just
Yeah,
muted?
that was just mine. I think I bumped a mute button or something like that. So everybody else said they could hear it the whole time. So
Very good, very good.
yeah.
Yeah, sounds still good. Okay. All right. Let me, look like there's too many questions, so we'll switch to different presentation. All right, so maybe we'll go through this section as well, and then we can take a 5 or 10 minute break maybe after this section for everybody to just to have a break, grab some water, do whatever we need to do. So, all right, so exploring masonry materials, kind of going beyond the codes. The options and things that I looked at here for obviously most of the information that I'm going to cover with the different materials and stuff is going to be either referenced in the masonry code. Other really great guides for masonry design is not necessarily in the code. I'd say the elements and some of the different papers that I have, International Masonry Institute does have some information, but the NCMA tech guides are really great items for that I'll reference throughout the day. There'll just be different times where the code doesn't quite cover something, it doesn't go into this in depth, and really we have to go to NCMA. So the National Concrete Masonry Association has a lot of different resources that would be papers and guides, and there's some spreadsheets and stuff that are out there that could really be very helpful for masonry design. So I utilize those guys all the time, and if I point to a few different papers that they've written, really because we're trying to acquire some insights about the different components of masonry walls, build knowledge about the materials that make up the masonry system, learn how local strengths can affect masonry design, and just look at some best practices. When I talk about masonry, I like to compare to how does masonry stack up with steel and concrete design. We have some pretty typical kind of design flows that we use for steel design or concrete design. Both of them, we just start with common sizes and strengths. For steel, if we need more strength, we use larger sizes. Sometimes we use higher strength, but that's kind of rare. Concrete design, we have typical strength sizes. We just, if we need more strength, we can specify larger sizes, or often we can use higher strength. It's kind of fluid on both of those different parameters. For masonry design, we start with a minimum strength, often, and then if we need more strength, we just use thicker walls, larger blocks. And so really what I want to do is I want to kind of eliminate kind of the traditional way that we look at masonry design. I mean, masonry does have a lot more options than that. We can need more strength. We can use larger blocks. We can use higher strength. Masonry is available as a product, but masonry product is made all the time, and different block producers can specify. If you specify a higher strength block, block producers can make that block. Certainly, I wouldn't ask for 10 of a higher strength block. You want to have a lot of that material that you would need, but masonry is something that is easy to increase the strength. It's going to be a special order, it'll be a little bit stronger, but so is concrete. So you have a FC of 8,000, that's going to be something that's going to be a higher cost of concrete. So just same with masonry. If you need something that's a 5,000 psi block, that's something that they can make. It's probably going to cost a little bit more, but you can do that. So I think that masonry does have some similarities between steel in that there are common strengths. We should know what those strengths are, but it's quite a bit different than steel. I think a lot of times people put them in the same category, like it's a product and it's just something that's static, and we really can't do anything else with that. So again, as I kind of compare the two, it is available as a product. Strength, in steel is uniform. Strength with concrete varies. Strength with masonry varies. It's easy to modify sizes in steel. It's rare to increase strength with steel. Easy to modify sizes and strength with concrete. I think masonry is the same. Easy to modify sizes, but it's also easy to modify strength, especially if you need to get to higher strength. So I'd like to kind of show how masonry has got some similarities between both of them. It's not kind of this material that we just put on the side and just design to a minimum strength and so on and so forth. You know, what's in masonry? There's, you know, quite a few different components that go into masonry design. You know, blocks, you know, are going to be your primary element. Concrete or clay, could be even a different material, but those are going to be the most common. We have different mortar types, type N mortar, type S, or type M. All of those have different pluses and minuses and different times that you would maybe use different types of mortar. For grout, we have different types of grout. We have fine grout, coarse grout, or SCG, which would be self-consolidating grout. We have vertical reinforcement that we have in the design. Certainly, any place that we put those, we're going to add grout. We have horizontal reinforcement that can be used for strength design. Often used for crack control. We have control joints that are in minimum locations so that we can keep the horizontal stress in the wall minimal as possible. So a little bit more about the blocks. Again, we have concrete masonry units, ASTM C90, that's going to be your common masonry element that's out there. We see more and more provisions for clay, hollow structural brick, ASTM C652. This is different than your standard veneers, your standard clay veneers, which is going to be ASTM C216. The hollow structural brick or the concrete masonry units, both of those are going to be structural elements. You can see the two images on the screen. Both of them have large cavities for reinforcement and obviously meant to be reinforced in that way. We have different types of elements that are available. You know, again, you can, hopefully that image looks familiar to the 2013 code. You know, the different minimum thicknesses of the different flanges, webs, but it also points to the different types of blocks that are available for concrete. Really, concrete can be, it's formed so that you can form all kinds of different shapes relatively easily. I would say clay, I mean, so it's a hollow structural brick. The one thing about that is referencing the fact that it really is going to be one unit. I mean, they're going to extrude one unit and then they can modify it. But really, as you look at reinforcing a hollow structural clay wall, you'd really want to look at, you know, detailing that, make sure the right different block shapes are used in different locations so that we can reinforce the wall the way that we want to. You don't have all the different shapes that are made coming out of the plant. You really have one shape that gets modified to create your flow-through bond beam. So you're going to see that there's no U-shaped block, there's no lintel blocks for clay. It's just going to be pretty standard, just a little bit more information because this is still new to some people. Hollow structural brick units are going to be typically 4 inches tall, and then they can 6, 8, or 10 inches wide. But it could be shallower than that. It doesn't have to be 4 inches. It can be actually the 2 5/8 or whatever that it could be similar to the common clay elements. And then for using it as a bond beam block, that's going to be something that, again, is going to take that standard unit and then they're going to be cutting the webs down so that you can place that horizontal reinforcement a little bit more straightforward design-wise. So just a quick question about concrete masonry units. Are normal, medium, and lightweight blocks all different strengths? Not necessarily. Within the actual ASTM table, it points to the same minimums, all the same requirements for the different weight material. Obviously, lightweight is going to be different aggregate likely than what you would have with a normal weight. Different aggregate's going to lead to probably different strengths, but all of them do start with that minimum standard of 2000. Oftentimes I see normal weight probably being the stronger design strength, but I have seen lightweight blocks that are made that break out over 4,000, 4,500. So it's really good to get the test results to see, what the different concrete being added to the different normal weight, medium weight, lightweight options are. See what the data points to. Concrete units are typically 8 inches high and 16 inches long. Clay units typically come in 4 inches high. Concrete units are usually 3,000 to 6,000. Clay is going to be somewhere in the 9,000 to 13,000. The movement of the different clay is going to be different than concrete. Concrete's going to shrink, kind of have a tendency to shrink over time. Clay is going to have a tendency to expand over time. Otherwise, there really isn't any prescriptive changes to prescriptive code requirements. Really, they're going to be designed in the same way. You're going to be designing concrete and clay really with the exact same equations, exact same things as we're going through. And really, detailing is going to be very similar. Obviously, you have more options for concrete. You have more different types of elements that are going to be extruded, but clay really can be used in some of the same ways. Some of the different differences that you have between the two different materials. How do you determine the overall strength? The first way, prism testing, is going to be very straightforward. You take samples, you test them. The limitation to doing prism testing is the fact that you're usually doing prism testing close to when you're actually building a structure. That can add a little bit of a stress to the designers in terms of how do we make sure that we have the right strength in our designs. So unit strength methods, that's why those are created. And then you can see the two tables that are at the bottom. That's going to be unit strength tables. The one on the left is going to be for clay. The one on the right is going to be for concrete. So you can see the one on the left, it starts with a lower strength of 1,000, but really I don't ever see 1,000. I don't ever see 1,500. For clay, because clay units are typically quite strong, we usually see with design strength starting at 3,000 to 4,000 psi for F''M. So that means our clay units are usually somewhere in the 8 to 12,000, 9 to 13,000, I think was in the previous slide, in terms of the overall strength. We typically put structural clay units with type S mortar, so that's why I'm sticking to the center column for matching that with the to get the overall F''M. So the concrete strengths you can see are a little bit smaller, but the difference between the overall unit strength and the design strength is going to be a little bit closer. You have a little bit more uniformity between the actual element strength and design strength. So strength of masonry, historically designers with concrete masonry have designed with blocks at 1900 and then F''M of 1500. And that's just not valid for masonry today. We don't have blocks that are that weak, and with the updated code as of 2013, we typically have higher design strengths. In fact, I typically point designers to using design strengths for concrete masonry with block of usually 3250 or greater. Why 3250? That's just a very nice round number that points to a design strength of 2500. So that's typically where we can start with concrete. With clay, we can start a little bit higher. We can go all the way up to 4,000. So there's just a little bit more about a clay masonry, just because it's something that we haven't seen a lot of, or I don't see a lot of designers using it, so I'm going to just give a little bit more reference here. Reinforced clay is as old as masonry itself. I think that's fair to say. We've had reinforced brick masonry since the 1920s, so it's definitely going to be something that's been around for a long time. The units are going to be placed very similarly to how concrete units are going to be placed, and so that's why the overall detailing and everything can be pretty similar. What I try to point people to is sometimes people want to look like clay, but why don't they just use reinforced clay units? There's fewer manufacturers. There's less supply for this product. than there is going to be for the common bricks are available all over the place. So I would say it usually comes down to a supply side, making sure that you can get the material. That being said, there's some very large projects that have been done in reinforced clay masonry. So it's something that is definitely worth looking into if you want something to look like brick. Instead of putting, like a sign, I think that's an interesting. Like if you wanted a brick sign to be designed, I see designers out there putting common brick and then a reinforced concrete masonry and then a common brick. So it looks like brick from both sides, but it's got the 3 different layers to it instead of what could be one. It really could be a reinforced brick design that has one material. You have no layers. You have no differing material there. That could be something that works really well. Or if you wanted to have a single white project, you have something that you can do with structure if you wanted to look like brick on each side. Really, with the structural clay, I think there's a lot of different options. Atlas is going to be one of the main manufacturers. There's Belden. There's certainly many others that are available for doing structural brick. What it does, it gives possibilities to a lot of different things, like prefabbing a curtain wall or curtain walls that go past structures. They point to the different types of options that you have with different designs that are coming out, again, architecturally. It really does have a lot of potential for a lot of projects to be material that we could use to do a variety of different things structurally. So if I just wanted to tie the veneer back just at the floor lines, I did that on a project where the brick's going to be kind of self-supporting, self-sustaining. It just ties back at the floors. I don't need all the tiebacks everywhere, and so that's a very nice option. Sometimes you can use it as structure. You can use it as load-bearing or shear walls. All the different options that are available there. Sometimes I would design it as a long lintel. If I can use soldier courses across the space, I can use it and design it as a lintel that would just stay in the brick veneer. So that's something that's a very nice option for structural clay. Again, they have a design guide for a structural brick veneer, which is very nice to be able to use. So again, clay units are going to be, different manufacturers are going to have, again, different ways that they're going to create those elements, and obviously it's going to be starting with clay. So if I looked at masonry walls, I would have the different options that you can see here. 4-inch walls that could be reinforced would only be with clay. You could have a 4-inch concrete masonry, but it doesn't have the space for adding reinforcement. 6/8 and 10s are really both concrete and clay can be designed. You get into 12s and 16s, really you don't have clay units that are that large. It's really then you're going to be into concrete design. And then obviously different heights that are available from there as well. So masonry walls and thicknesses certainly really come down to the unit sizes. Other material, mortar is going to be the other material that you can see, right? You have most of the wall, 90% of the wall is going to be the units. What you're going to see between the units is going to be the mortar, really meant to be a glue, something that binds the different blocks together. So it's a mixture of sand, cement and lime, and water. It's not as strong as masonry units, and it really doesn't need to be. It's something that's just in these confined spaces. What are some of the different proportions that go into the different types of mortar? So again, you have the cement lime, you have mortar cement, masonry cement, all with different types of concrete that's going to be added to the different mixes, mortar cement, and then, like I said, water. So just some of the different values there. But really when it comes down to design, we really want to look at, again, the type M, S, and N. As a designer, I tend to gravitate towards the left, right? I like the mortar compressive strength to be higher. Really, that's going to be a value that maybe is overplayed a little bit because the overall assembly strength, really, if I look at the unit strength method, the method that's in the code for determining the overall strength of the walls, type N is weaker, type M and S are really the same. So we come to full strength with type S mortar. Really what that does is it really says, you can use type M, but it's really not going to help you with your overall strength. or so marginally that we're not going to give you any more credit for doing it. So those two are really going to be kind of equivalent. That's why they're together in the tables. So those two are going to be kind of lumped together. If I look from a construction perspective, workability, ease of construction, that actually, the further I go to the right, so if I put these three mortars up in front of a contractor, which one would you want to use? They would always choose type N. They would gravitate towards the right. So really, I think it comes down to, types of mortar, probably what's in the middle. Type S is a good compromise. We want more strength, they want more workability. Type S is really going to give us our full strength in terms of the unit strength method. So I think that's a nice kind of happy medium to live in. We have different, in terms of mortar, what are the different types of capacities that we have? Tensile stresses for clay and concrete masonry. This, if you're designing an unreinforced wall, then you certainly want to get into maybe the different types and the different, whether it's a Portland cement or masonry cement, you want to make sure that we have those different types in mind as we're designing with something that could have tensile stresses, which would be an unreinforced wall. So what should we be specifying? Again, type M is more strength, but usually more costly, reduced workability, doesn't result in a higher strength unit strength or compressive strength method. It can be used below grade, but it's used in high load application in extreme environments. I recommend type S for structural walls. It can use in all the different seismic areas, can be used below grade as well. That's something that is really important to remember. Type N for non-structural walls, veneers usually use type N unless it's a reinforced structural veneer, then maybe we again go back to type S. Can be used in some different applications. Type N is not to be used below grade, and it's not to be used in the higher seismic design categories. So again, it can be used in masonry partitions, but results in reduced wall capacity. Again, so the three different types, type S is probably the most common place for most structural designers to sit. Grout is going to be something that the strength of the grout is going to be an important component of the overall material, but just as important as the strength is going to be the flowability, because really we want this to be very liquid to flow into all the different confined spaces that you have within a masonry wall. So it's going to be different than mortar. It's definitely going to be fundamentally different. Mortar is meant to be a little bit stickier, something that binds to something very quickly, and certainly grout is meant to bind, but you certainly need the flowability to be one of the primary functions of the grout as it's flowing in these spaces. Looking at the different types of things, I mean, just looking at the spaces here, you can see fine grout would be something that you'd want to use anytime that you have a fair amount of reinforcement within a confined area. Fine grout would be something, and there's different requirements as to when you can use fine and coarse grout based on clearances. Coarse grout is probably going to be the more common. Hopefully we have typically single bar reinforced designs. Within the code, it also points to grout pours and grout lifts, making sure that we have, maybe the lift is going to be what we define as low lift grouting, 5'4". You can get it increased to 12'8" under certain circumstances with cleanouts and a lot of space to use. And self-consolidating grout could increase your pour height to 24 feet. All this pour height, pour lift, a lot of this stuff is really meant for contractors to be reviewing the different pour heights that we can consider. Adding cleanouts certainly adds a lot more ability to add more and more to the lift, and like I said, self-consolidating grout being the one that can go all the way to 24 feet with just a clean out at the bottom. So that might be a really nice option for contractors. So if you look at all the different materials, the block, the mortar, the grout, one of the things that I try to point to is people are specifying these different materials for projects. Is I recommend not just saying F prime M is equal to a certain value. Really what we want to do is we want to call out each material, the different properties of each material, and the different strengths of each material. So as an example, what I would point to people is putting an overall assembly strength, F prime M of 2500, but then specifying your block strength to be 3250 or greater, and then your grout strength to be 2500 because that's your F'(M) or greater, and then your type S mortar, and then once you define your type of your mortar, you don't have to define your strength. So that could be the two different. So in that you can also have different strengths on a same project. I mean, that's something that we certainly can do. We do that all the time for concrete, but just like for concrete, we want to be careful as how we store material, so on and so forth if we would do something like that. So for F'(M) for concrete masonry, again, if I boil down all the tables into a really simple chart here, if I put 2000 PSI blocks with type S mortar, I get an F'(M) of 2000. So again, that's our minimum. With the 2013 code and beyond, that's our minimum design. If I have blocks of 3250, type S mortar, and 2500, then I have a strength of, like I said, 2500. 4500 PSI for the block to get to type S, to get to 3000. Really, it's the one in the middle. That's going to be our typical design strength across the country. And so when I started talking about masonry design 10, 12 years ago, really kind of pointing people to this fact, and people really wanted to see some data. So what I did was I created a website. I actually started crowdsourcing some of the different strength that I was getting for blocks. So this is a normal weight block, 8-inch block in these different states. You can see the minimum strength of 3020, the average strength of 4438, maximum of 7870. So if I go back to 2500, that 3250, that's something that's met most of the country with normal weight block. That's something that we can achieve pretty easily across the country. You get into medium weight, light weights, you get into different thicknesses, all those different things you can check on this website, or you can just call the different block suppliers that are going to be used on your project, or the different block suppliers in the area to see what the actual strengths are. Anytime that we want to go to a higher strength, I think that we can go beyond what was even in the unit strength method. We could get to that F'(M) of 4000, but to do that, we certainly need to use a higher strength block, maybe type M mortar. Really, you're going to have to just define higher strength elements, but more than anything, you're going to have to then specify a prism test method to make sure that we have 3 different samples, and the test between those 3 different samples, we average them out to make sure that we get a higher F'(M). That could be up to, like I said, 4000 for our strength design provisions. Why is F'(M) so important? It's important not just for the wall design. You know, the small differences in wall reinforcement can make a huge difference in materials and stuff that you'd use throughout our design. But lintel designs, the depths of lintels, sizes of lintels, columns and pilasters, reinforcement that you would need. Lap lengths are a lot shorter when you have a higher strength F'(M). And then connection to masonry. Anytime you connect to a masonry wall, usually the controlling parameter in the connections to masonry walls is going to be the actual masonry strength. So I actually put together a little white paper a couple of years ago, and I think this can be kind of useful. It really kind of spells out all of that stuff. This stuff, you know, all these papers that I put up here, by the way, I'm not selling any of these. These are all free to download. You can certainly grab those. I could actually send some of these PDFs as kind of a follow-up to the presentation today. So this is one for concrete masonry in the Midwest, kind of what I typically see, how to get to the F'(M) of 2500. And then for clay, also pointing to the fact that it could be 3,000 to 4,000 pretty easily with most of the common clay elements that are out there. The other materials that we want to point to with the materials in masonry, so reinforcement. Obviously, reinforcement is going to be added. It's going to strengthen your wall quite a bit. You have the blocks, the grout, the mortars, all that are all creating compression, but not so good in tension. So obviously, reinforcement's what makes your wall quite a bit stronger because it has that tensile, high tensile strength. Every place you put reinforcement, obviously you need to put grout. Grout's kind of that mechanism to create that internal moment arm between your compression block in the masonry and your tensile force in your bar. So grout, that's why grout's obviously really important to be consolidated to make sure that we can find, contain, and bond to the reinforcement and the masonry as well. Again, the strength design provisions, pointing to number 9 bar, the number 11 in the new code, but then also some bar diameter to wall thickness limitations, and then a bar area to be less than 4% of the cell area. Right, because we're adding the reinforcements, so then when you put a lateral load on the wall, that tensile force that you have due to the bending in the wall is taken by the reinforcement, right? Kind of some pretty rudimentary illustrations for why reinforcement's important. And then what I wanted to do next is I wanted to put together a couple different tables. You know, when we had some of the different reinforcement provisions, what does that look like? So I'm an engineer, I like to throw together spreadsheets, the different wall thicknesses and the different reinforcement options at the top, all the way from 4s to number 9s. You can see where I can use those within different walls. I think it gets a little more interesting when we put in doubly reinforced walls. Really, again, we're dealing with confined spaces. Doubly reinforcing a masonry wall should be done, you know, carefully, and we want to make sure that we're not adding too much reinforcement so that it's hard to build. So that's what's shown by the code. The other side of this is, you know, what do contractors prefer? You know, what do masons prefer? So what I actually did was I created a little survey to try to see what different masons would prefer. If I had an 8-foot or 8-inch masonry wall, 22 feet high, 24 feet long, I have 4 different reinforcing options that have very similar capacities. Which would they rather build? A 6 at 48, a 5 at 32, so a smaller bar closer together, 2 even smaller bars, but this time even maybe a little bit more spacing, or a number 5 alternate staggered reinforcement placement, which is kind of unique, or a 12-inch masonry wall with the different reinforcement options. So if I look at the survey results, I think it's kind of interesting. You know, for masons, you know, if that 8-inch wall, you know, the larger bar at 48 inches on center was their preference, kind of a strong preference. They'd prefer that much more over the 2 number 4 bars, even though that 2 number 4 bars would be less grout. They prefer that over the smaller bar because there would be a lot more grout with the smaller bar. So again, I think that that's interesting. You can see the strong preference in an 8-inch wall for the single bar further apart. It gets a little bit more interesting if I look at the results for the 12-inch masonry, 1 number 7 bar at 56. So again, smaller bars. Number 6 is at 40 is what's required. 2 number 5s at 64, something that, you know, would be even less grout. So kind of similar options, right? Here you can see a slight preference for the number 6 at 40, which I thought was really interesting. You know, so they are looking at this and saying, you know, number 6 bar is really the largest bar that I want to deal with. I get into 7s and I start to shy away from it, even if it's less material, less grout. At the end of the day, they would prefer to use a number 6. Again, cost-wise, maybe cost the 7 at 56 is what costs a little bit less. So maybe that's what they go with. But I think that that's interesting. You know, when you deal with what masons want to build, 4, 5s, and 6s are the preference. You get into 7s and they start to get a little bit gun shy. Get into 8s, 9s, and like I said, all the way up to a number 11. Obviously, they're going to have some concerns with placing some of those very large bars within a masonry wall. This is that little image that I pointed to before when it was added to the code. This is a great little detail to add to your standard notes and details, specifying where the reinforcement can be. Again, when it's 8 inches thick, the bar can be a 1/2 inch off center. It can be plus or minus a 1/2 inch. If it's a 12-inch wall, it really can be plus or minus 1 inch. So that's really great information to have, that you bar doesn't have to be exactly at the center and you'll still have the same capacity for your wall. So that's really important to realize kind of where the bars can be placed within a masonry wall. So it's a very nice detail. You get into a little bit more about the lapse of reinforcement. Again, I said, you know, different things make the lapse shorter or longer. So they are different. Obviously, they're going to be longer the larger the bar is. But if we have a higher strength of masonry that we're considering, that's going to make the strengths lower. Really, I think it's pretty easy to take this equation, drop it into a table. We can see pretty quickly where the number 3s, number 4 bars have pretty short laps. This is an 8-inch wall, 25 psi, 2500 psi. You can see what some of the different lap lengths are. So I also want to point to the old reference of 48 bar diameters. Certainly for the smaller bars, you have too long of a lap that's required, but some of the larger bars, you have too short of a lap that's referenced. So it's not necessarily to just save material, but to make sure that we're more accurate based on current test information, where we are with laps design-wise. The other thing about lap lengths is I think it's something that could be added to schedules. Reinforcement lap lengths can actually be different for the same size bars. So here you can see the W2 with the one number 6 at 32 inches on center. That's a 33-inch lap because it's in an 8-inch wall. One number 6 at 32 inches on center and a 12-inch wall would be 21 inches. I think, if W5 is the most common wall, making your lap at 33 inches is probably not, that's a lot of 12 inches of extra bar every place that you have a bar. So I think a schedule is just really good, and it helps create a lot of clarity over what the actual laps that are going to be required for different areas. Other things about reinforcement, lap splices can be achieved in different ways. I've had mason contractors that have preferred lapping bars over mechanical couplers. I've had some of them prefer mechanical couplers. Recently, I've had a few mason contractors that said, hey, we know how to weld. Let's just weld the reinforcement. So obviously you have to have weldable reinforcement, but that's a very nice option for lapping reinforcement. You have different options that can be selected there. If I get into reinforcement, I always like to step back here and say, hey, you can have an unreinforced masonry wall. Masonry can be a little bit heavy, so that's one thing that really does help it, because if you look at the different bending loads, certainly anytime you put a pressure load on a wall, you have a negative side that's in tension, you have a positive side that's in compression from the bending force. But if my wall weight is actually sufficient that I actually keep both sides in net compression, one's going to be more compression than the other, certainly you can have an unreinforced wall. Or if it's in mostly compression and then a very minor tension, you can still have an unreinforced wall. So it's really important to remember, and this is, like I said, important for partition walls, walls that really don't have a lot of load demand or lateral load demand. A lot of times it's pretty easy to keep both faces in compression and have that design still be valid. The other thing about reinforcement, so you don't have to have reinforcement. When you do have reinforcement, horizontal reinforcement is reinforcement that we like to add to walls. Horizontal reinforcement really does keep the horizontal stresses from getting too high due to temperature changes or shrinkage in concrete. Could be different reasons why you have horizontal reinforcement to prevent some of those cracks from occurring. There's different levels of horizontal reinforcement that you'd want to add. You can add a minimum amount of horizontal reinforcement and add control joints. Control joints are joints that are placed within masonry walls to relieve some of the stresses that might be accumulating due to, again, shrinkage in temperature forces on a wall. You could also add enough reinforcement so that you don't have to have control joints. So what are some of the different options here? Options, joint reinforcement, we commonly have 9-gauge, which is what all masons are going to prefer. You have an option to have heavy 3/16-inch diameter wire that could be added, which could be added in rare situations for certain reasons. You could have bar reinforcement. You don't have to have horizontal joint reinforcement. You could actually have horizontal bar reinforcement instead of joint reinforcement. So bar reinforcement is going to be obviously placed in bond beams, which again can be common for concrete and structural clay masonry. You know, from the code's perspective, reinforcement is not allowed to be more than half the width of the mortar. So half of a common 3/8" mortar joint is 3/16. So that's why the 3/16" wire is the maximum wire that you can place within a bed joint, and still have it be horizontal reinforcement. How much and where? Empirical method, engineered method, two different methods for how we place reinforcement. From the joint reinforcement, closer spacing, than bar reinforcement, which could be nice. Bar reinforcement option is larger spacing, but it's not unlimited. We only can go so far with bar reinforcement. You got to remember, we're trying to control the stresses in that masonry wall due to shrinkage and temperature. Putting bar reinforcement too far apart, and maybe we'd have some localized cracking that would be undesirable. The big thing about horizontal reinforcement is the code itself is relatively silent on the topic. It doesn't give a lot of provisions for what is needed for horizontal reinforcement within a wall. So that's where I go to those NCMA tech guides, 10-2D and 10-3. You know, that's really going to be my main references for horizontal reinforcement within masonry walls. The one thing the code does say, a mandatory checklist in the specification 602 section, that designers have to indicate the type and location of movement joints. So if you're going to locate the movement joints, you better know where the horizontal reinforcement is so that we can understand what movement joints we even need to add. So just some really quick, and we'll cover more on movement joints and control joints and horizontal reinforcement a little bit later. Some of the main parts of this section, just understanding materials, consider that strength can be from a minimum of 2,500 or higher. If it's clay, it's even higher. Locate control joints and horizontal reinforcement. Understand different wall options. Consider unreinforced partitions. And then we can get into a little bit later today software and you know, how that can help lintels and stuff like that. So that's going to take us to the end of this section. I'm not sure if anybody has any questions, but I think we can take a 5-minute break or so. So if anybody has any questions, certainly throw them up there in the next 5 minutes. We can take a little bit of a break. I'm going to switch to another section. And let's see, why don't we say, so it's 10:12, let's say 10:20. We get restarted with the next section of the presentation. Does that sound okay with everybody?
Yeah, that sounds good, Sam. We can definitely do that, and we'll all be back at 10:20 then.
All right, thank you. Hey everybody, hopefully everybody's back and ready to go.
Yeah, we're back.
All right, so we are gonna just keep going. Hopefully I didn't see any questions come up. I don't think I missed anything here.
Did you, you might have already caught it, but someone asked about, could you please comment on the different mortars, MS and N? I don't know if you caught that one yet or not.
Oh, I see it there, yeah. Yeah, so different types of mortars. Yeah, Gregory, I don't know if you have any specific questions about the different types of mortars, but type M is going to be, why don't I go back to a couple slides here. All right, so hopefully everybody can see that different types of mortar, M, S, or N. Really, I kind of put this slide together to really kind of show that really type M and S are going to be similar in terms of the code perspective when it gets to the unit strength method. In a sense, the code is basically saying you don't get a lot more strength from the overall design strength of the wall between the different types of mortar. It's really kind of similar. Type N, it's going to be a weaker wall. It's a weaker mortar. Workability, that's going to be a lot easier when you go from left to right. So type N is going to be it's going to be the most workable, ease of construction. Contractors prefer N. Engineers tend to prefer M. And I'm trying to say is type S is actually the best mortar to use for most applications for the structural wall. If you get into a veneer or like an architectural wall, sometimes partitions, type N can be the one that is the best. So I just go here, let me see. Yeah, so this is kind of a summary slide on mortars. Type S is going to be the best for the most people. Engineers are going to like it, contractors are going to like it. The very common mortar. So hopefully, Gregory, hopefully that's everything you were looking for. All right, let's go ahead and skip ahead to design. All right, so the design of masonry walls. Really what we're going to be looking at here is the TMS 402 is going to point to a wall being something that's 3 times longer than it is thick. So, if it's 8-inch thick wall, then 24 inches, 12 inch, 36 inches long. Load-bearing loads greater than 200 pounds per foot in addition to self-weight. So all different things that make something a masonry wall. A shear wall is going to be things in the code where we're obviously taking on some lateral force. Different than a partition wall, it's going to be taking some in-plane forces. And then the different seismic design regions, ordinary reinforced shear walls are going to be pretty lightly reinforced, or the requirements for them are pretty light. You have boundary reinforcement, top reinforcement, reinforcement at each end. It's really when you get into the intermediate reinforced shear walls. Intermediate reinforced shear walls have reinforcement requirements at 48 inches on center each way. Obviously, the more complicated, the more ductile the wall needs to be. So like if you get into specially reinforced shear walls, it's even more and more reinforcement requirements for higher seismic areas that really demand the walls go through more of a ductile response as it has the higher seismic forces on them. We talked about columns, we talked about beams. So those are going to be the two different main elements for walls. So lintels are going to be obviously this area that spans an opening. We'll go a little bit deeper with lintels. I have a whole section on lintels just because masonry and lintels are going to be something that is going to be a preference from the overall masonry perspective. It's going to be fast, economical, matching a wall. moves at the same rate of the wall, which is going to be important from an engineering perspective. Built in place or prefabricated. And a lot of times, the main reason for people using some other material for the lintel in a wall was the fact that shoring was complicated back in the day. Shoring has gotten a lot less complicated, and a lot of masons actually don't mind at all shoring up an opening. But prefabrication is going to be, as we get into more and more prefabricated elements, prefabricating masonry lintels is going to be something that's pretty straightforward, pretty easy to do. Any length really being possible. So here you can see the actual lintel in this wall is something that was prefabricated. You can see the shim on one end that kind of points to it. Really, there's any length is possible. There's not a lot of length restrictions, 20, 30, 40, even 50 feet. 50-foot masonry lintel is certainly something that is possible and doable, and really does, like I said, have a lot of benefits for the overall wall. So again, a lot of different types of elements that we're going to look at. We want to get into the actual design provisions, strength design versus allowable stress design. And I know a lot of people in masonry are allowable stress design, so I'm going to kind of take the opposite perspective in strength design, and you know, why it makes sense and why it maybe is worth a look. There's like I said in the first section today, there's a lot that the code designers are trying to do to try to bring allowable stress design closer to some of the strength design provisions, to be honest. So harmonization of the code is really kind of that effort. Really the most common codes, you know, are based on strength design because it gives more uniform factor of safety against structural failure. Loads on a building are either permanent or transient, or moving, changing. Strength design puts a higher factor of safety on less predictable transient loads. So I think that that's something that's important to think about and recognize. I mean, it's strength design does make a lot of sense. You know, just a quick comparison between the codes and different time frames. ASD there was ASD in concrete, believe it or not. It wasn't always strength design, but that was pre-1970s. And I would say most masonry design today is ASD. So strength design for concrete been very common. Most people have learned in strength design basically in concrete, and then hopefully masonry. Maybe that's starting tomorrow for all of you. I think it makes a lot more sense, and that's where a lot of the efforts go into in terms of the codes and the testing. It's more in the strength design, and like I said, the harmonization is really kind of bringing allowable stress design up to the strength design parameters. ASD compares actual and allowable stresses. Stresses typically kept below their yield for a member, computing the load capacity by factor of safety. And then again, strength design obviously looks at different strength provisions to try to keep it within actual, and then the combined forces are kept below computed member capacity with a resistance times resistance factor and resistance factor. Again, strength design specification accounts for the separation of the different predictability of the different loads through different load factors. Again, allowable stress design made some efforts in kind of moving towards that direction. For material and constructability variability through resistance factors, separating factor of safety, independent load factors, resistance factors, more consistent effective factor of safety is obtained, resultant in safer, lighter structures depending on predictability of the load. So obviously you get into more of the wind loads, seismic loads. When those are dominating the demand, then you're going to have maybe a little bit more conservative designs. When it's more of the gravity loads, dead loads, live loads, then strength design probably be more favorable of a design. Just looking at the overall stress distributions here, obviously masonry being able to be unreinforced, you have tension equal to compression, and obviously we have to stay within the tensile limits. Obviously, if you have more compression on the wall, then you could actually maybe reduce or almost eliminate some of the tension on an unreinforced wall. Otherwise, we have some different variables that we look at in terms of tensile force. And then strength design obviously has a compression block and tensile force. So some of the similar diagrams, just a little bit different ways of coming to the same conclusion, hopefully. Similar to strength design uses for masonry design of materials F prime or Fy of 60, KSI F prime M of whatever the masonry is here, 2250. Factor loads come from ASC 7, 1.2 dead, 1.6 live, 1.0 wind, 1.0 times seismic. And then you have the strength reduction factors phi. Limiting reinforcing ratios, I think, are also really good to make sure that we stay into a ductile area. Here's some of the different variables. F prime M is specified compressive strength of masonry. That's the overall assembly, right? That's not block strength. That's not mortar strength. That's the overall assembly strength. The grout FG is going to be the specified compression of the grout itself. Grout is not one of the variables in determining F prime M. That's always something that we have to remember. That's why it's kind of held separately here. FR, the modulus of rupture, is really going to be looked at as the kind of that tensile capacity, the tensile stress that's allowed for our masonry wall. FY, specified yield strength of the steel. The PN, VN, MN is going to be the nominal axial shear moment strength. PU, VU, MU is going to be the factored axial load, shear force, and moment. You have strain variables. We have net cross section areas. So all the different variables that are going to be used throughout some of the different code equations specified here. Rho going to be your reinforcement ratio, D distance between extreme compression fiber to the centroid of the tensile element, dV actual depth of the member. So chapter 9 strength provisions, we have the all the different, again, sections of the code that we're going to be looking at. So factors design actions must not exceed the nominal capacities reduced by our phi factors. Quotient of the load factor divided by phi is similar to the factor of safety of allowable stress design. It should be comparable to that safety factor. So that obviously something that's good to think about, compare. And here's some of the, again, some of the load equations that we have with strength design. The other thing that I do appreciate at the codes, and this isn't just masonry code, but we look at the masonry and concrete and steel, all of them using similar strength design provisions. Strength design 1.4 times dead, 1.2 times dead, 1.6 live, like all of those things, instead of the concrete code having the 1.4 dead, 1.7 live, so on and so forth. So having all that uniformity obviously helps a lot with the different material designs. So within the code, design strength must equal or exceed the required strength. Especially reinforced masonry shear walls do have design strength shall exceed the shear corresponding to the development of 1.25 times the nominal flexural strength, but not more than 2.5 times the required shear strength. So not just meeting the required strength, but actually staying within a range of values. So especially reinforced walls, obviously a higher seismic area. So strength reduction factors, you can see unreinforced masonry having lower phi factors for the combinations of flexure and axial load. So basically giving us higher factor of safety, right? It's less predictable with unreinforced masonry. So we have a 0.6 for the phi factor instead of reinforced, which is at 0.9. We have similarities between shear and bearing at 0.8 for shear and 0.6 for bearing. Phi factors again for the connections to masonry, we have 0.9 for the actual steel, anchor bolt steel. We have 0.5 for masonry breakout crushing. So we looking at the actual kind of tensile strength out of masonry itself, that phi factor at 0.5, the anchor pull out at 0.65. We have deformation requirements, ASCE 7, 10, and 16. Deflections of unreinforced masonry are based on uncracked sections. Obviously, we can't have cracking occurring. Deflections for reinforced masonry consider the effects of cracking. Flexure and shear stiffness properties assumed for deflection calculations is not to exceed 1/2 the gross section properties, unless a cracked section analysis is performed. So basically, when we have reinforced masonry, we have to take into account that the actual section properties are going to be less. There's going to be section properties are going to be reduced once the section goes from uncracked to cracked. Once we have cracking occurring, we have something that's going to have less stiffness. So that 0.5 times the stiffness of the wall, accounting for the crack factor. But you certainly can come into having a better analysis. We actually wrote a couple papers on cracked sections for masonry, kind of coming up with a better value. Certainly the 0.5 is a nice place to start, but we can certainly get into something that's more more relevant to the section. Within the sections of the code, we keep the 1500 in there, but all the way up to 4000 for the masonry compressive strength. We have grout, which is going to be greater than F'(m), so that's going to be important, but then less than 5000 psi for the overall grout strength. So we want to make sure that we stay within those values. We don't want grout that's overly strong. In plane, out of plane bending, we have different types of mortar and moduluses of rupture, so different tensile capacities that you have, with those different options for an unreinforced masonry section. Reinforcement strength, we have Fy of less than or equal to 60 ksi. Yield strength will not exceed 1.3 times the specified value. Compressive strength of reinforcement should be ignored unless the reinforcement is tied in compliance with certain sections. So unless you get into some of the higher detailing requirements of the code, you really are going to be ignoring any compressive capacities of the reinforcement, which would be very common with concrete and concrete masonry design. Unreinforced, obviously, masonry shall remain uncracked. Compressive stress will not exceed 0.8 times F'(m). Flexure stress shall not exceed those moduluses of rupture. Consider the H/R slenderness ratios and consider the P delta effects on uncracked section. Obviously, if you have something that's load bearing, it can be good in terms of it's going to keep the section in compression, but it's something that we need to be careful of to make sure that we don't exceed some P delta effects, making and accentuating the actual moment on that wall. So linear elastic theory, plane sections remain plane, stress proportional to strain, compatibility between masonry reinforcement and superposition of forces. So factored design is less than the design capacity, so our flexural stress is less than the unfactored loads. Must not exceed the modulus of rupture reduced by the phi factor. So obviously we can't get into any cracked sections or anything like that for a masonry wall. We have some pretty specific equations for axial strength for our walls for unreinforced masonry members, and then a moment magnifying for the unreinforced masonry members as well. Axial tension resistance in unreinforced masonry should be neglected in design. And then we have nominal shear strength based on these different equations. Depending on running bond or stacked bond, grouted or ungrouted, we can have different types of capacities that can be determined for our shear strength of masonry. So we get into reinforced masonry. Obviously, it's going to be quite a bit different. Reinforced masonry is cracked. Reinforcing is needed to resist tension, similar to the design of reinforced concrete. Again, design assumptions, there's strain compatibility between reinforcement, grout, and masonry, reinforcement requirements, details, all those different sections for design of reinforced masonry. The continuity between reinforcement and grout, we have some equilibrium For concrete masonry, plain sections remain plain. Tensile strength of masonry is neglected. Equivalent rectangular compression block in masonry with a height of 0.8 times F prime M and a 0.8 times C. So we look at the overall stress strain force diagram that you have. So obviously you can see that tensile force be there for reinforcement. Go back into the reinforcement section, we again see the provisions in there for number 9 bar or smaller, bar diameter less than an eighth of the overall wall thickness, which we talked about. And then we have hooks that we can use within masonry walls. Hooks obviously need to be detailed very carefully. Within a masonry wall, again, we're dealing with confined spaces. So how can the hooks be placed and located? Do we have bond beams, and do we have the right types of blocks that allow for hooks to be utilized? Development length and wall shear reinforcement must be bent around extreme longitudinal bars. Good detailing requirements. If we do get into splices, we have welded or mechanical splices have to develop 25% more capacity than the overall bar itself. So making sure that we have good force transfer from one bar to the next is obviously going to be very important. We have maximum reinforcement provisions. For reinforcement within a wall, we can't just add number 11 bars to a 6-inch wall. You're probably going to have too much reinforcement in that wall. So there is some maximum reinforcement. Here's your axial moment curve. We have balance, compression, we have tension. And so we obviously need to stay within that capacity curve. Design of beams, piers, and columns. We have nominal axial compressive strength. We have axial force, 0.8 times strength of masonry. Different variables in there for areas of steel. We have a slenderness factor that we have to determine for different height walls, making sure that we have basically a P delta effect that we're taking into account of, and make sure that we consider that within our design. We have different shear capacities depending on the different moment to shear ratio that we have for the member. The lower moment to shear ratios, we have Bn times 6 times An over square root of F prime M, versus the higher moment ones, we have a little bit less capacity, 33% less capacity. Objective is to avoid crushing of the diagonal strut, so on and so forth, with linear interpolation between these extreme values. And then obviously there's more capacity that you can develop if you wanted to add in some steel for shear strength. You have the shear strength provisions, and then shear capacities with the steel. Axial moment capacities for beams. All bars must be within 1 bar size, no more than 2 bars. Lateral spacing, space more than 32 times the beam width. Nominal depth not less than 8 inches. I think it'd be hard to have something that would be that shallow. Transverse reinforcement, when required, shall be a single bar with 180-degree hook at each end. I mean, it's really kind of looking at, anytime that you have shear reinforcement, transverse reinforcement for beams, lintels within a wall, you have to make sure that it fits in and works within the wall itself. Reinforcement for piers, isolated elements, got a different axial equation, thicknesses between 6 and 16 inches, nominal plan length between 3 to 6 times the nominal thickness, clear height not more than 5 times the nominal plan length. Again, we have reinforced requirements for columns. We have different ratios for reinforcement that we want to add. We have lateral ties that we can include. Remember that we do also have the ability to have a lightly loaded column that we can consider. We have a least cross-sectional dimension, which is 8 inches by 8 inches. That's a pretty nice little small kind of a masonry column that we can consider. Nominal depth not greater than 3 times the nominal width. For different walls, we have all kinds of different forces that we have to consider. Capacity under the combinations of flexure and axial load is based on the code 9.3.2. We have out of plane forces, we have in plane forces, and then obviously we have axial forces that we have axial load and moments, so all things that we want to consider when we are checking the capacities of these walls. And different sections for maximum reinforcement. Typical walls, the tall walls, height to thickness ratio of 30. We have a limiting value of the axial load to the gross section area. And then we have deflections that are limited to delta times 0.007 times the height. So that's something that creates a deflection that I think is probably more than what most people are used to, but making sure that we stay within that code requirement would lead to a safe design wall. And anytime that you can be less than axial to the gross area, less than 20% of F prime M, then we have a factor moment that we can utilize. Taller walls, if the height to thickness is greater than 30, then the limit to the axial force on a wall drops to 5% of F prime M. So again, we have all these different equations, and I'm obviously not going through each one of them. We have tension controlled, compression controlled designs. We have a nice little handbook that we can see with the chart in there to help us make some design decisions. A lot of times, I mean, I'm going through this stuff pretty quickly because a lot of times our designs are going to be based on a computer or a spreadsheet or something like that we're designing these. So I'm not going to go through these really in depth. Another flow chart, more and more in depth to determine the overall capacities for moment and shear for our designs. Then the in-plane forces, obviously having a lot of the similar requirements, a lot of the similar bending and shear capacities that you would have. Other things about in-plane designs, vertical reinforcement, not more than 8 feet, so not more than 96 inches on center. I think that might be a little bit of a surprise to people. A lot of times people put a lot more reinforcement in walls than every 8 feet. So really it's not until you get into looking at the wall for in-plane loads, for the wall being a shear wall, could be an ordinary reinforced wall. That's when we have to start putting some reinforcement in there, not more than 8 feet apart. So again, that's when some minimum reinforcement provisions start to kick in. But like I said, I think that would be a surprise to a lot of people. A lot of people would put in reinforcement a lot closer than 8 feet on center to start. So flexure and axial strength based on 934.1.1, vertical reinforcement, not less than 1/3 of the horizontal reinforcement. So we want to make sure that we have a decent amount of vertical reinforcement in the wall. Nominal shear strength provisions. There's an alternate approach to maximum reinforcement. I mean, you have minimum requirements for walls to avoid boundary elements based on certain provisions within the wall. All kinds of things that we get into when we get into kind of special design of the masonry walls. I have a couple different charts here that we can, with a separate, for a separate seismic design, just kind of with some pretty straightforward information. An ordinary masonry wall doesn't have any prescriptive requirements for seismic design. You get into the detailed plane and ordinary walls, that's when we start to get into some design provisions here. We have basically a number 4 bar that needs to be placed in the corners and within 16 inches of the side of the openings, within 8 inches of each side of movement joints, within 8 inches of the ends of the walls, and then a maximum spacing of 10 feet on center. So detailed ordinary reinforced walls just don't have a lot of requirements. 2 longitudinal, basically 9-gauge wires at 16 inches on center, or a number 4 bar with a maximum horizontal spacing of 10 feet on center. So again, pretty minimal requirements. Horizontal reinforcement at the top and bottom, basically boundary reinforcement within a wall within 24 inches or 40 bar diameters, structurally connected to roofs and floors and within 16 inches of the top of the wall. So an ordinary reinforcement just doesn't have, it's not that much that it demands and requires for your design. We really do have, it's really the intermediate reinforced walls. If we skip to that, that's when we really have all the same requirements that we had for the intermediate is going to be the same as the ordinary reinforced, except for the vertical spacing is limited to 48 inches on center. You get into specially reinforced, then you have all kinds of other consideration to look at. You have reinforcement that's tighter together. You have reinforcement ratios, really kind of looking at more and more of a ductile response for the wall. If we looked at, again, seismic design category, it doesn't really have any, A doesn't have any seismic design requirements. B, you get into shear walls must be a detailed plane shear wall. C, you can get into still having an ordinary reinforced shear wall. And it's when you get into D, when you have to have a shear wall designed to be a specially reinforced shear wall. So in terms of our seismic design, really looking at strength design and you know, whether it's going to be beams or lintels, columns and walls, out of plane and in plane bending, all kinds of different provisions. And then where is it going to be used? So strength design is going to be also in the different software programs. Again, it's going to be the last section today, but you're obviously going to be able to use that within all the different softwares that we have. All right, so that was a little bit of a brief section. There's a lot of equations, a lot of stuff that I didn't want to spend too much time on today. I don't want to put anybody to sleep. So we wanted to move through that section a little bit quicker. But again, if anybody has any questions, like I said, a lot of design equations. Just take a second here to switch between this and the next section. Okay, it doesn't look like we have any questions that popped up there. I'm just going to give it another minute just in case anybody's writing something and wants to finish. Okay, so the next section here is going to be maybe a little bit more on the practical side of masonry, the different topics, and what I would call the wall construction procedures would be wall movement joints, wall lintels, connections for masonry, and then notes and detailing. So I would say if we get through the first two parts of this section, wall movement joints and wall lintels, hopefully we can move through a couple of those before the lunch hour. That would be good. We'll see how long. Let's see how long those take, and then we can kind of see where we are before we take some time for lunch. All right, still no questions. All right, let's keep moving forward. All right, so the masonry wall, horizontal reinforcement, and movement joints. If I looked at a wall like this, kind of a common wall, I really have a couple different options, or we have a lot of different options for this wall movement joints. You know, how much horizontal reinforcement with or without control joints. You know, that really has implications, obviously cost implications and constructability. You know, two different things. You know, if I'm looking at these different options for these walls, you know, architects might say, you know, how does it look? Will this crack? I mean, obviously those are going to be things, you know, designers will look at. And then if you're located in Wisconsin or in the Midwest, engineers might ask, you know, who designs without a control joint, you know, in certain areas of the country. I mean, you know, how easy is this going to be to build if I took out, you know, control joints and just designed this wall with no control joints? You know, how much is it going to cost? It's all kinds of different questions. So really what we try to do is we try to come up with different options for contractors so that they can price out different options. Obviously, this is just one little example, one elevation, you know, and then, you know, if I do take out control joints and stuff like that, you know, I'm making the design more complicated. You know, designers need to be able to design this thing. So let's talk a little bit about movement joints, control joint definitions, horizontal reinforcement options. We talked about what horizontal reinforcement we have, but what are some of the different options that we can utilize, understand the balance between control joints and reinforcement, and then the structural impact of the various options. So this is a slide that we looked at before, right? The different materials of masonry. Really, we're going to kind of focus in on the last two here. Horizontal reinforcement. Like I said, the horizontal reinforcement can be used for strength design, whether it's shear for the wall or if it's horizontal bending. Most often, horizontal reinforcement is going to be there for some respect of crack control as we go through the different shrinkage and temperature stresses and forces that are on a wall. And then control joints in horizontal reinforcement situations, we're going to look at where we want to put control joints. One of the first questions that I like to ask is, do all masonry walls require control joints? And then if control joints are provided, then what type and how much reinforcement is needed? If control joints are not provided, then what type and how much reinforcement is needed, right? So there's within, again, within the code is kind of silent in some of these topics. So I think that that's good to understand, different possible scenarios of control joints, because there's kind of this balance. The more control joints you have, the less reinforcement that you need. If you don't have any control joints, then you have to have much more horizontal reinforcement. So the different NCMA tech notes are going to be where we come to for getting some of the guidance here. One option could be joint reinforcement and control joints. Another option could be just bond beams with no control joints or joint reinforcement. And then another option might be a combination of joint reinforcement and bond beams and minimal or no control joints. So movement joints within a masonry wall, often within a structural wall, are going to be called control joints. We just label them as CJs, which is going to be common for structural masonry design. Expansion joints are going to be things that are obviously a little bit different. They're going to be a little bit of a different reasons for putting in expansion joints. We label those as maybe EJs. They're going to be common for the structural clay masonry or just common clay masonry. So today we're just going to kind of maybe the nomenclature. I mean, when people put these on plans, it's either EJs and CJs, or you could just call everything an MJ, a movement joint, for now. One of the very important things to remember especially if you have a cavity wall, anytime that you're looking at differences between masonry walls, an unreinforced wall has different requirements for movement joints than a reinforced wall. So an unreinforced wall might have expansion joints at certain locations because the wall is unreinforced. When you have a reinforced wall, you're going to have, again, different requirements, and those maybe are going to be called control joints. So they're very likely not going to be at the same location within a wall. And there's really no requirements for having those joints aligning within a wall. The veneer ties that we use today, if you have a cavity wall, allow for the different movements to be occurring within the walls. And so it really does allow for those joints to be in different locations and really those walls to be acting independently. And so that's going to be something that's pretty important to remember. If we have those joints, they're going to be in unreinforced and reinforced walls in completely different strategies, different locations, and they do not need to align. In fact, I would probably say that they should not align. I think you would want them to not align in your designs. So again, different options for our horizontal reinforcement. We have joint and bar reinforcement that we can add. Code says that reinforcement is not allowed to be more than half the width, so that's why we have the 3/16 inch reinforcement that's allowed. And so, how much and where? So we have these different options for where we're going to put the reinforcement. We have empirical or engineered method, joint reinforcement. Joint reinforcement is going to be a lot less area of steel, so that's why it's going to be closer than bar reinforcement. Bar reinforcement, we can put quite a bit of steel, say within a bond beam, but it's not unlimited the spacing that we, and like I've said before, code can be kind of silent, which is why we turn to the tech guides. Within the tech guides, what it does is it points to horizontal reinforcement options. If I have 8-inch high units, NCMA Tech Guide 10-2, this is an empirical method, says that we have a length of wall to height of the wall ratio that can be 1.5 to 1, with a maximum of spacing of 25 feet for 8-inch high. So a common concrete masonry design is going to give us that joint reinforcement at that spacing. So that's why we can see 9 gauge at 16 inches on center. That's the very, very common way to put in horizontal reinforcement. We can also see within that table, though, if I put one number 4 bar every 8 feet or number 5 bar every 12 feet, that's sufficient amount of horizontal reinforcement. You don't need to have both. If we decide that we're going with horizontal bar reinforcement, then I just use number 5. I don't have to put in joint reinforcement. If I just want to have joint reinforcement, then obviously I don't have to have bar reinforcement. I've seen designs, as I've reviewed designs where, you know, people tend to put in both, maybe kind of a belt and suspenders, which just isn't necessary design-wise. And then anytime you have a 4-inch high, so obviously we're getting more into the clay, reinforced clay masonry or half-high concrete units, then we have slightly different maximum spacings that we would want to use for the different reinforcement requirements. So that's the empirical design method. This is kind of independent of anything other than the thickness of the wall. You know, this is the height of the unit. That's really the only variable here. Getting into the NCMA Tech Guide 10-3, similar provisions. This is going to be, again, looking at the requirements for horizontal reinforcement when we have control joints. So table 1 at the bottom is going to be showing us our maximum length of wall and the length to height ratio. So 25 feet high, 2.5 times length for the height ratio for a crack coefficient, minimum horizontal reinforcement 0.0007. So what is 0.007? That's going to come to giving us for different wall thicknesses. So now what we're doing at the engineer method is we're looking at the actual area of concrete. You know, back here when we did the empirical method, there really wasn't. We're just looking at, empirical is really looking at, you know, what has worked in the past. What do we see success with? We don't necessarily have a lot of engineering number crunching to back this up, but this is what's worked well in the past. Here, this is why engineered method, we're actually getting into kind of the nuts and bolts of area of concrete that's, you know, shrinking, you know, due to shrinkage and temperature. You know, the actual, what is our demand going to be on our horizontal reinforcement? Because all concrete's going to crack, all concrete masonry is going to crack. Really, the reinforcement that we're adding in here is going to be preventing those cracks from actually opening up, where you'd have any water or any type of things that are going to be infiltrating in the design. So again, so now we have all kinds of different because thicknesses have different, wall thicknesses have different face shells that you have. So a 6-inch is going to have thinner face shells than a 12-inch. So even if it's ungrouted or partially grouted, the continuous concrete is going to be a certain value. And then fully grouted actually has not just the face shells, but obviously then it's a full concrete wall. What I think is really interesting here is when we have the engineered method, we look at the actual designs, we can see that there's quite a bit of a difference between empirical and engineered method. In fact, what I thought it was so interesting, I actually created a comparison. I did a table to look at the joint reinforcement based on NCMA Tech, the engineered method, versus what I had from 10-2D. So if I have a partially grouted or ungrouted masonry wall, is going to be the top table that I see at the top of the screen. And you're going to see it compares pretty well. There's areas of the chart that are going to be unconservative. You know, if I have, you know, a design here, you know, where I have different thickness of walls, you know, the thicker the walls, the less conservative I am, but it compares pretty well. It does actually compare pretty well to the overall what matches up here. It's when I get into the fully grouted walls, I can see that I'm very, very unconservative by using the empirical method. I have far too little joint reinforcement in here design-wise. The 2 9 wires don't work for any wall grouted solid, whether it's a 6 to a 16. All of them are going to be very unconservative, and certainly as I get to some of the thicker walls, it's going to be worse and worse. I have that much concrete. So like the bottom row is 16 inches concrete. So that's something that's very important to remember. If we look at the Tech Guide 10-3, there's also a provision in there for moving beyond adding control joints. 10-3 also gives us an option for providing enough horizontal reinforcement so that I don't have to have any control joints that are prescribed within a wall. I can design a wall without control joints at specific locations, and that's just it's a higher level of reinforcement. If you look at the chart, the reinforcement ratio that you see at the top in the top title, it's 0.2% of the overall net area of concrete is what's needed for the area of steel. 0.002. It should look very familiar to everyone because it's essentially the same area that's required for the horizontal reinforcement needed for concrete. So it's really, we're not doing anything different. We're really kind of looking at making sure that we have enough reinforcement in there to prevent any shrinkage or temperature cracks from opening up. And so we have this higher level of reinforcement. If I put in, again, we put it into a table, you can see for both an ungrouted and a grouted situation what the actual spacing would be from 6-inch all the way down to 16-inch walls, what the different reinforcement that you would need for the designs. So the other thing that going beyond the guide is what I'm looking at. I'm trying to see, if I have a combination. So sometimes I have a design of a wall where I'm going to put in some horizontal reinforcement, but I still going to have joint reinforcement. Joint reinforcement might be in there for adding in joint reinforcement for, maybe it's a brick tie and stuff like that. So I'm going to have the joint reinforcement. I want to add some bar reinforcement. So what I did was I created some tables here for if I have both joint reinforcement and bar reinforcement, the actual bar reinforcement requirements are going to be pretty minimal. So for a 6-inch wall, for example, I could put a number 4 bar every 12 feet and joint reinforcement and not have to put in any control joints. That's a pretty straightforward design. Get into 8-inch, maybe it's number 6 bar every 12 feet and joint reinforcement, and I don't need to put in any control joints. So that's a pretty nice options for being able to look at the minimum amount of horizontal reinforcement that you would need to not have to put in control joints. So horizontal reinforcement, movement joint guides. Again, going back to the code does require that as designers that we do locate them. We have to locate the type and location of movement joints on project drawings. Way too often I see this being delegated to contractors. We can't just list the requirements for where the joints go. We actually have to be specific to the type and location of movement joints on the drawings. If I look at different types of joints, for veneers, for movement joint basics, so a veneer, unreinforced masonry is what we need to be thinking here. We have vertical joints that we add, we have horizontal joints that we add. What are some of the reasons that we add vertical joints? Needed to prevent cracking, we talked about that a little bit. We also need to add vertical joints when there's differential support. Anytime that we might have a wall that could be supported on different types of support systems, one might be a roof, one might be a foundation, there could be, it's just going to be stresses that are going to be created there. It's pretty rare that you would eliminate vertical joints in a veneer. I mean, you'd have to add a fair amount of joint reinforcement in a veneer to eliminate those, which maybe for certain projects would be desirable, but it'd be pretty rare to eliminate vertical joints. For horizontal joints, again, you need to allow for differential movement. This is movement between the support structure and the veneer itself. We'll talk about that in a little bit. The horizontal joints is not to relieve. So anytime we look at masonry, we look at like even, or say a brick veneer, the capacity of brick is very, very high. We do not ever need to relieve the stresses that bricks are going to accumulate. Masonry is going to have plenty of capacity to support itself. Really, the horizontal joints is just trying to create some break between the veneer and the backup so that movement can be different between the two different spaces. And we'll talk about that in a little bit. There's some cases where you could eliminate the horizontal joints. In fact, you could in quite a few cases, and we can talk about those as well. So again, the vertical joint example, the differential support. Again, if you have parts of your veneer that's supported on the foundation, and then you have part of your veneer that might be on a shelf angle or on a lintel angle, those are going to be locations where you have a differential support. You know, the supported by shelf angle, that angle can move a little bit. So that's why we do put those joints in those locations. That would be a common place for cracking. So that's differential support from the veneer perspective. If I looked at a structural masonry, so veneer is going to be unreinforced, structural masonry is going to be reinforced. Vertical joints, we still need to put those in to prevent cracking if we don't put enough horizontal reinforcement in. You can use vertical joints also to isolate structural elements. There's times in a structural design where we maybe want to have shear walls just in a certain area, and so we maybe want to add in joints to isolate, you know, the shear walls that are going to have a lot of reinforcement versus other joints. And then vertical joints we can eliminate in the structural masonry by having sufficient horizontal reinforcement, which isn't that hard to add. So horizontal joints in veneers, again, we had those options. When do we put a horizontal joint in structural masonry? And the 3 times would be never, never, and never. I mean, there's just no time that we actually need to put in those horizontal joints in a structural masonry wall that's got plenty of capacity to support itself. So the horizontal joint needed for differential movement, this really kind of comes to the structure, which is going to be moving, tends to be shrinking, especially if it's going to be something that would be like a wood structure. It's definitely going to be shrinking. The thing about the masonry and the veneer is it's going to be very strong. So that's probably going to be expanding. So that differential movement, that's why our veneers need to be separated quite often. We have something going on with the structure behind that's moving quite a bit, whether laterally, vertically, so on and so forth. So the joints that are needed there horizontally really have to account for that, the different movement. If we have the multiple story structure, the reason why we typically add joints there is because we don't want that differential to accumulate over the height of the building. So that's why they're shelf angles and not relief angles. The shelf angle is just there to panelize the wall so that our differential movement isn't too high. It's not to relieve the brick veneer. So what are some of the structural elements that you might want to isolate? Partition walls could be an element that you want to isolate. So you put in a vertical joint to make sure that it doesn't get any gravity or lateral forces that you don't want to have. It could be a shear wall, maybe again the shear wall that you don't want to have too many other forces, stresses, or you want to simplify the behavior of the shear wall so that it stays in one plane. That might be a nice reason to put in some vertical joints in a reinforced masonry wall. To talk a little bit more about lateral walls, one of the things that I look at for lateral design is looking at the elevation like this. Typically, in the past, without some better tools to design, what I might have to do is I might have to look at individual areas between openings, because maybe that's where I put in joints. Maybe I put in joints at most or many of the openings within a wall. And so what I ended up having was a lot of smaller, shorter shear walls, which are less effective design. And the reason for not making it, include the opening is it just gets pretty complicated. It gets pretty complicated to design a perforated shear wall with an opening in the middle as a shear element. And so that's really, we talk about software. A lot of my background is in software. Having a finite element analysis software to look at a masonry wall with openings that can be all over the place is really not that complicated. And then you have a system for actually looking at a wall like this. We can look at a lot longer wall, which again is going to be a lot more effective. So again, basically some masonry movement basics. All buildings move, concrete masonry shrinks, clay masonry expands. Two things that we have to think about. If we have the two of them in the same wall, if we have a cavity wall, we definitely have to think about it. But just knowing that they move, concrete tends to shrink over time. As it cures, it tends to shrink. Clay is going to expand over time as it takes on more moisture and the actual bricks grow a little bit. That's why you have the shrinking and expanding. I mean, both of them both shrink and expand due to temperature loads, if that is variable. So the best thing to do with those is either accommodate some of the movement or restrain the movement. So we have to have some way to restrain the movement so that it doesn't have negative effects in the overall building. In terms of the actual construction documents, we typically have structural engineers locating control joints on plans, sometimes on elevations, and architects usually locate expansion joints on elevations. I would just say again, you cannot locate movement joints with a single sentence in the specification. It's not enough information. We have to be specific. We have to make sure that we have those plans or elevations that we're putting those joints on. In terms of some references, some guides that you might want to use for, again, clay brick veneer, BIA is a good reference. Brick Industry Association, they have a 20-foot spacing that 20 to 25 feet that they allow for clay brick. International Masonry Institute, IMI, has 18 to 25 feet, so somewhere in there. 20 feet is probably a good maximum length of wall before you put a control joint. If you have a concrete masonry veneer, again, NCMA is going to say 1.5 times the wall height, not to exceed 20 feet. That's within NCMA Tech 10-4. If I have a concrete masonry design where it's a reinforced wall, then again, I have similar 1.5 times the height, not to exceed 25 feet. That's one reference. But then I also have the reinforced wall options where I can have no limitations. I have movement joints that I can put wherever would make sense for the overall design. I don't have to put them regularly. So you really have three different types of walls here. You have a veneer, you have a mostly vertically reinforced wall with the second option, and then you have a vertical and horizontal reinforced wall where our limitations are very minimal. So I would say there really should be somewhat of a balance between the horizontal reinforcement and movement joints, take into design consideration what different things that we have in here. Again, our options are one or two, one minimum horizontal reinforcement and control joints. If we go with this option, just recognizing that you don't have to have as much horizontal reinforcement as concrete, that's why you can get away with just the light gauge reinforcement. And that's why we put the control joints pretty regularly. And then the second option, really getting into the additional reinforcement, being more like concrete and having no, which is practical terms, less joints. The NCMA Tech Guide also gives a nice little diagram here to kind of point to, anytime that you have a change of wall height, that's a good place for a control joint. Anytime that you have intersecting walls, that's a nice place for a control joint. Pilasters, just because the change of the overall capacity or maybe change of load demand might be a good place for a control joint. And then, as you kind of go around corners, maybe there's a good place for a lead-in for a contract. There's another good places for control joints. If you look at the diagram a little bit closer, you can see maybe partition walls or exterior walls. You can see the different color, right? It's maybe shaded a little bit red to show a brick veneer. Those kind of showing unreinforced options where you'd have next to lintels where you would want to have some joints. So a nice little diagram pointing you to some common locations for joints within a building. Then, like I said, we went through the table a little bit, kind of looking at what are some of the different horizontal reinforcement options to not have to have reinforcement. So again, we look at, again, different strategies. We have different options. We have different designs that might look at, what would be the best for this option. So this is something where I actually created this survey and reached out to several different contractors to look at, what their preference would be, what they would want to do design-wise. So looking at option A, where we have standard joints, standard reinforcement. Option B, where we have standard joints, no joint reinforcement, but horizontal bond beams. Not a bad option. And then C, where we have no control joints, heavy joint reinforcement. That's another option. And then no control joints and no joint reinforcement, but 2 bars throughout a wall. And then no control joints, no joint reinforcement, but even more bars, more regularly spaced within a wall. So just kind of what do those elevations look like? So this is, again, a pretty common masonry wall with a lot of joints throughout the wall and joint reinforcement kind of everywhere. This, just looking at the wall, obviously it's a lot cleaner. There's not all the horizontal wire that you have to add. You can put in these mid-height bond beams. That can be a really nice option preventing cracks. Maybe this is a nice option, anytime that you have a cavity wall, if there's some minor cracks that would occur in some of these bigger panels, then maybe it's not that big of a deal. If you start to get into some of the options that look at eliminating the need for regular control joints, this option is one that contractors did not like at all. Putting this heavy joint reinforcement every 8 inches, yeah, you can eliminate control joints, but it's that heavier 3/16-inch joint reinforcement is not one that contractors enjoy using. So having to do that regularly throughout every level of the building, or every course of the construction, is not something that's desirable. Option D, less bond beams, more reinforcement, or option E, more bond beams with 1 bar. So different options that you have that would satisfy some of those control joints versus minimum reinforcement. I think it gets a little bit more interesting when we start to add in some openings. Putting in openings, just because of the location of the openings, reinforced, masonry walls don't want to have control joints at the openings. It's unreinforced ones that do. So now we're maybe even adding in some control joints because of the openings. We have joint reinforcement, we have lintels. It might be simpler to put in just have the lintel reinforcement be continuous, have the sill reinforcement be continuous, and maybe that seems like a very nice little option for our control joints and movement joints. So for the movement joints, we looked at horizontal reinforcement in the masonry walls, movement joints, purpose and location requirements. We looked at different reinforcement and movement joint strategies, and then some of the structural design impacts. The resources, there are a lot of different resources that I referenced here. A lot of them are going to be NCMA tech guides. There's a BIA, and obviously the Masonry Code is also utilized here as well. All right, so that's going to take us to the next section where we're going to look at lintels for masonry walls. All right, Gregory, it looks like you were looking for some design examples. I don't know if there was design examples specific to a certain topic or if just kind of in general. I can send you a reference to one of the guides that I use that has tons of design examples. Masonry Designer's Guide is a very nice book that's provided by TMS that gives a lot of different examples for every different thing that you could possibly think of doing for masonry design. So again, that's the Masonry Designer's Guide that's available from the Masonry Society. Okay, lintels for masonry walls. This section is maybe a little bit longer. So we're going to try to get through the whole section before we take lunch. Lintel for masonry walls, I think the things that we're looking at here is maybe a kind of a proposed change to what the typical, the way that we've typically did lintels for masonry walls. So that's why we're going to spend a little bit more time on masonry lintels today. We're going to look at the basics for lintels, what options do we have for lintels and masonry walls, what I'll call high performing masonry lintels, and then how to use software for the lintel design. I think there's definitely things that we want to remember, maybe things that we've talked about a little bit already. Designing all masonry, especially lintels, for that higher strength FRM of 2500. Moving control joints away from openings for a reinforced masonry wall is very, very important, and we'll see why here within the lintel section. Loads on masonry lintels are a lot less. We'll talk about why that is versus some of the other materials that you could have. And then masonry lintels are going to be the most effective, efficient, and robust. And we'll kind of talk about why and how and kind of why that's important. So really, lintel is just going to be the area above an opening, right? Per TMS 2016 C-beam, a member designed primarily to resist flexure and shear induced by loads perpendicular to its longitudinal axis. So it could be vertical load, could be horizontal load. Either one of those could be options that we can look at there. And when I look at something like this, sometimes I want to step back a little bit and say, are we overcomplicating something? I mean, we have this concrete masonry wall. Have we been overcomplicating it? Have we making this more than we need to? What are the principles that work in stone and masonry to spanning an opening? And so I look at some of the pictures and images of stone and masonry that have spanned openings. I mean, you can see that we don't need to add reinforcement. We don't need to add steel. We don't need to add a different material. We look at some of these historical structures and buildings. We have the principles in place of these materials that are compression based materials for spanning openings. Can be pretty large openings. We can span those openings pretty easily by just recognizing the compression friendly materials that we're dealing with, right? There's not a lot of tensile steel that needs to be added to these openings. And so I think that's really good to recognize. I mean, these are just different archways that we've seen, that I've seen. This is me way back in the day down at the Alamo. Just you can see compression arches all over the place. And so when I look at doing a masonry design, lintel design, there's several different things that I want to look at. Definition of materials, geometry of openings, opening sizes, lintel loads on the lintel. How do the loads actually get to a lintel? How does it get distributed through the wall? What are some of the different options that I have to look at there? And then design options. The different lintel material affects the analysis because it has different demands on, back to number one, geometry of the walls, opening size, so on and so forth. So let's go ahead and look at define materials, geometry of walls, strength of masonry. Again, if we look at the area that you have that we're dealing with, the strength of masonry is going to be, looking at that right above the opening. It's going to have, the same block, mortar, grout, rebar that we've talked about in previous sections. A lot of times, if I looked at masonry lintel, it's going to have the same materials, just utilized in a little bit of a different way. Obviously, you're going to have horizontal reinforcement, not just vertical reinforcement in this lintel. So it's going to be common materials. We have a little bit different blocks that we want to look at. We can have all kinds of different blocks that are used throughout the lintel, though. We have the lintel shaped blocks, which are going to be the standard kind of UW shaped blocks that are going to be used because it's got a solid flat bottom, right? And that's going to be important for lintels because when we span an opening, especially if it's architecturally exposed, obviously you don't want to see anything there but a solid masonry at the bottom. So it also contains the grout. It works good construction-wise. Other lintel blocks are going to be just your standard stretcher blocks. If you have a several course masonry lintel, your standard stretcher blocks are going to be just fine. Then you get to the blocks that are could probably form the top course, so you can have a flow-through It's going to be a bond beam block where you can actually remove the webs of the block and you can run the reinforcement kind of through. So that's your concrete masonry options. If you get into the clay masonry, again, we have pretty similar blocks that are going to be used throughout a reinforced clay masonry design, but those blocks would be modified, right? If we had a bond beam block would need to be created, or something would have to be created design-wise. If you wanted to have reinforced masonry both in the backup wall and the veneer, the only way to kind of do that with a clay masonry is you'd have to have soldier courses. You actually have to turn the block on its side. Now, it doesn't have to be a full soldier course. It could be a half high or it could be a third, but it does have to have a soldier course. That would be, so then you could have both masonry weights that could be reinforced masonry lintels. So F prime M of masonry, again, this is, we keep going back to this, but this is a good reminder. 2500 is really going to be our typical design strength for our masonry wall. That's for obviously for our concrete masonry. So the next thing to look at, strength of masonry, is what it is. The geometry of the wall, what do we have in terms of the geometry above the opening, the height above the opening, control joint locations. Two things that are going to be pretty important to look at. Control joint locations is going to be something where, again, if I have an unreinforced masonry wall, which again isn't too common for a structural wall, but an unreinforced wall, that's when I have a control joint that's going to be at the opening. But when I have a reinforced masonry wall, again, let me see 1 second. Yeah, there we go. Sorry. When I have a reinforced masonry wall, that's when we're going to get into the control joint wanting to be away from the opening. The reason for that is I don't need the control joint at the opening because I have reinforcement on each side. I have reinforcement that's going to be vertically on each side in the jambs, and I have reinforcement in the actual lintel and sill itself. So I don't really have the ability for cracks to occur at the opening corners. So that's why control joints are going to be important. Again, locating the movement joints, just like we just talked about, plans or elevations, this might be a really good point to putting them in on elevations, but making sure that we remember that it's not okay to just put the movement joints in notes just because of like the lintels that I'm talking about here. Moving the lintel away is actually going to change the overall design capacity. So locating control joints away from openings, it's going to be something that, control joints away from the opening, you actually can have arching action. You can actually have the masonry wall that can form the arch over the opening. If I put a control joint there, then I don't have the ability to have arching action. So that really does change the overall performance of the lintel, the wall itself, the lateral in-plane shear force, the perforated shear wall is not able to happen when I have a control joint next to the opening. So there's a lot of different things that change. So what I suggest is at least 2 feet from the edge of the opening would be their first lintel location. Again, this is just kind of a quick review for what we have. We have a couple images there from the NCMA Tech Guide, but then the most important images when it comes to the lintels is looking at when I have, within the Tech Guide, it points to when I have an unreinforced masonry wall, that's when I will put the joints at the openings. Anytime that I have reinforced masonry, anytime that I have a reinforced masonry lintel and jambs, then I want to make sure that I move those control joints away from the openings. And so obviously it's going to affect the overall lintel capacity quite a bit. And then again, we have the maximum reinforcement that, or the reinforcement that you need to eliminate control joints, and how that affects lintels are, let's just say, area like this, I'd have very limited locations to put control joints anyway. But if I don't have a control joint, then I have a continuous lintel. I have an area of wall that I can design as one monolithic kind of piece of wall. I have the lintel that's going to be continuous. I don't have any control joints interrupting and breaking up that continuity with the lintel that I have beyond the openings. I mean, it would be obvious, right? A continuous beam is obviously going to be more effective than a bunch of simply supported beams, and that's why we really want to get away from having control joints at openings. Those individual beam lintels are going to be a lot less effective. It's going to make the overall wall performance a lot worse, you know, just because you're going to have those piers that are going to be the only lateral resisting element. We're going to have those lintels that are going to interrupt those piers quite a bit by having some bearing area. Anything that time that you can have this continuous lintel, this continuous wall span is going to be a lot better performing design. And then obviously, like I said, with the shear walls, you have an integrated lintel, you have a perforated shear wall, you're going to have a lot more shear wall capacity. So again, having that integrated lintel, you know, if I look at a historically detailed wall, I would have a wall like this where I'd have a control joint at the edge. You know, I really have a third of the capacity with the two small walls versus if I eliminate that joint and just have the one really long shear wall, that's going to have about 3 times the capacity over those two short walls. So that's going to be kind of a pretty big difference on the overall lintels, control joints, everything that you want to consider there, shear wall capacity, all of that stuff kind of working together, coming together with those few just a few simple things with the control joints. And then loads on the lintel. How do the loads get distributed through a wall? You know, that's going to be something that's really important. You know, looking at different types of loads that you have on the wall, uniform loads, point loads, and arching action. 3 different topics that we want to look at. How do the loads get distributed through the wall? I mean, just not so much quantitatively, but qualitatively. If I looked at a wall, I put on the gravity load that would be on the wall. Those are going to be my red arrows at the top. If I just look at the wall, how do you think it's going to respond? You know, how is it going to get to the demand? Mostly it's going to be those blue arrows. It's going to be vertical compression capacity that's really going to create most of the support. You know, what's going to happen to that area below those blue arrows above the opening? Well, really, that's going to be what's covered in another NCMA tech guide or another NCMA lintel design manual, arching action. So that goes all the way back to those first few slides of this section, is looking at arching action. You know, arching is really going to be how the wall is going to respond to the loads on the wall. The compression, stiff compression elements that are part of masonry are really going to do most of the load supporting for the masonry design. It's just going to be kind of that small area below the arch. That's really going to be the only load that you're going to see on the lintel itself. The wall itself is going to really support most of the wall loads, the roof loads, so on and so forth. You know, looking at an arch design, you know, what are some of the key components for an arch? Anytime, if just looking at a simple 3-hinge arch is probably the best way to kind of get a handle on some of the forces that you would have or reactions that you would have. Really, if you have a load at the top of the arch, right, it gets resolved by having vertical loads at the bottom, but because it's an arch, you really have some horizontal loads that, you know, the arch is going to be creating or forcing load into the abutments on each side of it. So if I just looked at a free body diagram, you know, looking at some of those forces that you would have in there, the horizontal force is going to equal to kind of that vertical force. It's going to be kind of equal and opposite if it would have a really simple 3-hinge arch. Obviously, we don't have that, but that's kind of a really nice, simple way to kind of look at and see what the forces would be design-wise. So thrust being half of the load of the arch. I mean, I think that's what sometimes can scare people away from looking at arching action, just kind of recognizing that there's all these new forces that we have to consider. But again, masonry is good in shear. Any areas outside of the openings are going to be very good at resisting any of those thrust loads. So load on the lintel is really going to be just kind of a triangular area. The NCMA guide does a really nice job of showing, you know, again, if the wall is taking care of itself, it's taking care of those roof loads. You know, really the load on the lintel is a pretty minimal self weight plus the weight of the wall in that triangular area below the arch. Within that lintel design manual, it actually has a nice little flow chart. If we can consider arching action, then the very small loads that you have to consider for design or if you can't consider arching action, that's when really a lot more load starts to kick in. We have to not only take into account the self weight, but the full weight of the wall above. We have to take the full weight of the roof load. We have to take, all of the concentrated loads. So we're really now demanding a lot more load on that lintel once I can't use arch. And why wouldn't I be able to use arching action? Again, that gets into if I have control joints on each side, then I'm going to really lose the ability to do that. The other load that we want to think about again is lateral loads, pressure loads. Kind of how does masonry respond? Where are some of those forces? The red pressure forces, wind loads, or inertia forces from seismic. Where do those forces go, and how does the masonry wall respond? So again, if I would look at some of the different tools that are going to be available, so this will start introducing some of the software pieces, because I think that's very relevant and necessary for understanding overall masonry lintel design is what tools do we have and what those tools are. Again, we'll talk about software a little bit more later, and we'll kind of complete the whole picture in terms of why software is important for masonry design. But we're going to start a little bit with it here because just because helping us understand what some of the forces are in these lintels. So if I would look at the lintels and the analysis options that I would have available, simple analysis and pinned end, that's how a lot of people have been designing masonry lintels or lintels within masonry walls if it's a steel lintel for a very, very long time. That's one option. I can look at a simple analysis with fixed ends. That would change the forces to be a positive bending moment and then negative bending moment at the supports. And then this third option that I'm introducing, this finite element analysis option, where I would actually have plate elements. I would model the opening with all of these different plate elements so that I can have an understanding for what some of the stresses and forces would be in those plates design-wise. Practically, I mean, you can see lintels are going to be all over the place in these walls. They're going to be in buildings like this. I could maybe have a very long span openings, or I could have a lot of lintels kind of spread throughout the whole building. Looking at it with software is going to be able to help us really understand that behavior. I can understand the overall building movement. But really with software, I can also tunnel into and look at a kind of a specific area. I can look at how lintels are going to behave and interact with piers and so on and so forth. So again, software, finite element analysis software really can help me understand, I think, the stresses and forces in the wall itself. Again, more on that later. But if we're kind of tunneling in on lintels here a little bit, we can see how the lintel is going to be integral with the wall itself. It's not a separate entity for a lintel. Lintel is part of the overall wall mesh. If I really wanted to see what some of the forces and stresses are, on lintels and demand for lintels, looking at it with a finite element analysis is going to help me understand these forces pretty clearly. So if I have, let's just look at a couple different examples. If I have a smaller opening, a 6-foot wide opening, 6 feet tall, or a 14-foot wide opening, maybe this is a big window, again, 6 foot tall, what are some of the stresses and forces? Because of the finite element analysis, I can really do, evaluate this and kind of slice and dice this thing in a few different directions and kind of see what some of the forces are. So again, 6 foot wide, 28-foot high wall, 20 feet of load above the opening. If I would look at the axial forces on the masonry wall from the finite element analysis, red color here is going to indicate low axial stress. So at the top of the wall, obviously, is going to be a low axial stress. But then you can see the area right above the opening, the axial stress is essentially gone. The wall itself, again, is bridged the opening. It's got a lot of compressive capacity. The axial forces are getting shed from the wall area, so that it's a low axial stress at the top and then low right above the opening. Then obviously low right below the opening as well. And then you can see the green to blue to purple indicating higher and higher axial forces, and that never really gets into the actual area above the opening. So you can see the arching action actually occurring in the stresses that we look at for the wall. If we actually, again, look at the sections that we have here, look at the actual forces, you can see the forces and how they're accumulating. If I look a little bit closer at the area right above the opening, you can actually see the axial stresses kind of increasing, then kind of stabilize, and then actually decrease as we get to right at the edge of the opening, which obviously I don't have any axial stiffness right above an open area, so the axial forces have to go someplace. So you can see that arching action. The other main part of arching action is I have the axial forces, but then I have the horizontal thrust loads as well. So again, looking at what those would be, looking at the horizontal forces with finite element analysis, I can see again, green and yellow kind of opposing opposite forces. Obviously, for the most part, it's kind of nil, it's pretty low, but then you can see those stresses kind of getting higher and the thrust forces being the highest, right at the corners of the opening. It doesn't necessarily carry through the whole wall though, right? I mean, it's just right there kind of at the corners of the opening, and then it kind of dissipates as we go out further with the wall, which I think is kind of interesting, right? And then the overall thrust loads are pretty small. I mean, the thrust loads are about 10 to 1, the thrust being the 1, the axial forces being the 10. It's like a 10 to 1 ratio between axial and thrust loads. And so, again, if we think back to the empirical arching action guide where we looked at that simple arch where it was 1 to 1, that's a very conservative way to look at it. Really, the actual arching action is going to be able to dissipate the loads quite a bit. We have a very deep arch here. We have very deep arches that can be occurring. There's arches within this wall, right? It's not just a singular arch. The wall doesn't just arch in one nice little uniform arch above the opening. It actually can arch the entire height. So that's why the actual thrust loads are very, very low, kind of that 10 to 1 ratio for thrust loads in the wall. So you can see them, you can see that they're there, and once they accumulate and kind of stabilize, then they don't really change throughout the rest of the wall. So I think very interesting. Other things that I'm interested in is I'm looking at the actual lintel itself. If I kind of slice and dice some of the different forces, the minimal shear forces, again, I don't have a lot of load that's going to be local to that opening if the wall is arching throughout the height of the wall. So again, the lintel load, the shear loads are going to be relatively small. If I look at the moment demand, also going to be very minimal. I can see some negative moment area. I can see some positive moment area. So all of that stuff makes sense. It's really tied in. It's kind of the fixed end member condition that I was thinking about. And so that was the smaller opening. What about the bigger opening? So if I go to the bigger opening, does it fundamentally change? Do I have some really radical differences here? A 14-foot wide opening. Again, you can see the axial stresses. You can see the red being the low axial stresses. Very similar behavior, right? It's just on a larger scale. So axial forces, you can see, again, get higher, and then they start to drop off in that area above the opening. You can see the axial forces get not just linearly, but you can see that on each jam, it's actually accumulating forces quite a bit faster, once we get closer to the opening. So you can see that the load's getting shed and dissipated to the outside, which is, again, makes a lot of sense. You can see that arch occurring. Again, the thrust forces, the thing about the thrust forces, you can see them occurring higher within the wall. So it's like it's a deeper arch that gets created. It's not so much just local to the opening. So I think that that's very interesting. I think the thrust forces, this is maybe a little bit higher, but it's not that much higher. We have still a very tall arch, very tall arches that are able to accumulate within this wall area. And so that the thrust loads are still relatively small relative to the size of the opening. It's not a 1-to-1 ratio. It's still, 6-8 to 1 in terms of the axial force to the thrust load that we have occurring. So again, the axial forces are good to understand. The thrust loads are really good to understand with the tools that we have here. We also want to look at the shear The shear force is still relatively small. You know, the thing about a finite element analysis programs is it accumulates the forces. It shows me, you know, some of this information based on the sections that I cut. Here I cut a relatively shallow section, and so you can see some of the forces. If I cut a taller section, if I actually say this larger area is the area of the lintel, then you can see my forces go up. Well, I'm cutting a larger section. And so there's some practical experience that's needed to say, I'm designing a lintel, I'm going to design this area of the opening, this height of the lintel for this span of the opening. And so as you change the different depths of a lintel within a finite element analysis, you can see the different forces that would be needed to be designed for in that local area. So that's where you can see the shear force here. Moment forces are relatively nil. Again, with the smaller section, if I do go to the larger section, you can see more relevant positive and negative moments that are being created here and shown on the diagram. So again, finite element analysis, we haven't touched on it too much, but just realizing the software really gave us a much better understanding, I think, of the forces that you have with a lintel that's going to be integral with the wall around it. So I think one of the really important steps of doing software analysis is being able to actually verify it, kind of back check it. And so that's what, you know, the next few slides are going to be. You know, first I'm going to start with the hand calculations, we'll call it. We'll look at the different spreadsheet numbers, just kind of going through these kind of one line at a time. You know, we look at the two different examples. Again, we have the length of 6 feet versus 14. We have the height above the opening is 22 feet in both cases. Wall weight, dead load from self weight. We have the loads that we have in the top of the wall, dead and live load, and then we have the combination that we used. So the different analysis options that I looked at is I looked at pinned ends, no arching action. So that's looking at it as a pinned end lintel, no arching action available. So it's just going to be a positive moment in the center. I look at fixed ends, no arching action. I look at pinned ends with arching action. So pinned ends with arching action is going to be looking at most of the load going outside of the lintel area. So the load's going to drop down to just that triangular area, the empirical kind of arch that we were thinking about. So pinned ends is going to be the same shear as fixed ends with arching action. It's just going to be a lot less load. And then what I do is I compare those different simple hand calculations to the actual results that I got from the finite element analysis. So I think that's pretty interesting. You can see that the finite element analysis confirms similar to the hand calcs for both examples when considering arching action, which makes a ton of sense. I mean, they should be very similar. You know, it's really saying that, you know, that load is just going to be the load local to the opening, which is going to be similar to the finite element analysis result. A stark contrast between that pinned end and the finite element analysis, right? Where we have far higher forces in the end. So that was looking at the shear. If I switch over to looking at the moment, kind of the similar things. If I have pinned ends and fixed ends, it's going to change the moment demand between pin and fixed ends. And then obviously the longer span. You know, the finite element analysis model really does, again, compare very well to the fixed ends with arching action. So now we're kind of tunneling down to, yeah, that makes sense. That's going to be similar to the finite element analysis model. And when you have a lintel that's going to be integral with the wall around it, you know, it's going to have reduced load. It's going to have, it's going to be tied into the wall on each side. It's really going to be kind of in that arena at the bottom. And I keep highlighting the pinned ends, no arching action to the finite element analysis model. Really, the reason that I want to point to this is the fact that this is why the different types of lintels that you use can make a huge difference. If I have to put in a different type of material, then I usually have to have control joints at each end because that material might move differently, or that material is going to be set in there in a way that I might have to allow for some differential movement for that element. Just putting those control joints in there really fundamentally changes the load demand that you have, the shear, and the moment that you have on the lintel. So that's why masonry lintels can generally be designed for a lot less loads, and they can really make a lot more sense for the overall design, structural design of the lintels. So kind of going all the way from software through software to understanding the forces, understanding how those forces compare with hand calculations, and then really kind of seeing why any lintel that you can provide that's going to be integral with the masonry wall system is going to be something that allows for the wall to actually do a lot of the work and it not just all fall onto the lintel for spanning the openings, which I think is going to be pretty important. So that leads to looking at different design options, right? So we kind of kicked it off there. I kind of pointed to steel versus masonry, different design options that we have for lintels. The lintel material does affect the analysis just because it gives you different options for how you can detail, what you have to do with those areas next to the openings. Masonry is going to be, I think, the best option structurally, architecturally, economically. I mean, from like a building maintenance perspective, it really doesn't require any further maintenance when you have a masonry lintel. When you have a steel lintel, those are common, which we recognize, but they are something that was added to a masonry wall at a different time and different age when we had maybe a lot of unreinforced masonry that we were considering. So steel and some of the demands of putting a steel lintel led to similar details that you would have with an unreinforced masonry wall. Right now, with the reinforced walls being more common, I think steel just creates complexity, and I don't think it's worth the trouble. I think it really does cause a lot of problems that we don't necessarily want to have with a masonry design. And the third option there, a precast, and maybe we'll start with that in terms of looking at these different options. Precast lintels, these are lintels that just prefabricated concrete. They can be in the shape of a U, and you can see the end reliefs being in there, so you can reinforce the masonry the same way that you would if it was a masonry. So these precast lintels, I think, are like extended or stretched out U blocks is the way that I used to usually describe them. They're can be a little bit heavier and you got to lift them into place. The compatible aesthetic with masonry, but they're going to look a little bit different. It should be modular with masonry. They maybe have to anchor them to prevent them from rolling off. You have an additional coordination item. Sometimes I think there's some mason contractors that have pallets of these, like they're just another masonry block. They're just a U block, so or a very long U block. So precast lintels I think are a really, really good option as long as you get the right ones. They're resistant to fire. Could be a potential scheduling issue if they don't have a lot in place. And then here you can see some in a job that I used. They work really, really well. So again, precast can be kind of similar to masonry as long as you have the right types of precast masonry and lintel. Steel is going to be the one that I pick on today. And again, I do a lot of steel design. I like steel. Steel is a fantastic material. It's just using the different materials within the same wall plane can create a lot of potential problems. So they're very common. Should they be? They're scheduling critical. There's usually going to be a lot more lead time than a block. They need some corrosion protection, flashing treatment. There's bearing plates that are often required. Steel is not resistant to fire. Obviously, we need to somehow protect it in some way. We have a thermal bridging issue that we create when we use steel lintels. It's used as shoring, but it's usually more common. When I talk about thermal bridging, a lot of times people want to talk about the architectural issue of thermal bridging and how the cold from the outside gets to the inside. We have that thermal bridge. When I think about thermal bridging, I think about, well, if the cold can get from the outside to the in, then it's going through a material that changes temperature more quickly than everything around it. So when I put in a steel lintel like this and I have a thermal bridge, I have a steel lintel that's going to be shrinking much more quickly than the wall around it. So that's going to put some internal forces into that wall that are going to be forces that I don't necessarily want on that wall that can cause a lot of problems for that wall. So steel lintels, sometimes the way that people are resolving them is put in steel lintels, and then instead of having to deal with it, putting in steel columns, now we're cutting masonry everywhere. Now we're creating more problems, not less. So steel columns to support steel lintels is not a good solution. Similar, instead of the steel lintels and steel columns and all masonry, kind of continuous lintel option is going to be much better structurally, architecturally, and again, from a building maintenance perspective. So other things that we want to point to with steel, looking at where you're going to expect cracks. The most common cracks that I see within masonry are going to be when steel lintels are used and the bearing, that compromised bearing crack, which doesn't sound good. It sounds concerning, and it is concerning. This is going to be the most common crack that I see within masonry. Bearing plates being too large and being exposed, and rust can be an issue. Wide flanges twisting and having some rotational movement is also going to be a concern. So all things that we have to really kind of think about. We can put in horizontal reinforcement. So if you look at the steel lintel that's in there, hairpin horizontal reinforcement bar is something that can be used, and I've used it before to prevent cracks from occurring. In a situation like this, sometimes steel is needed as this floor beam, and it's landing on a wall. You have a bearing condition on a masonry wall with a steel beam sitting on it. A variety of times when we have steel that interacts with masonry, we need to think about some of these things, making sure that that steel can move relative to the masonry and not cause further issues. Because otherwise we just have this crack or this crack or this crack. I mean, it's just those compromised bearing cracks are certainly concerning when we see them, and we definitely know that there's things that are moving there, and we have a lot of structural concerns. So now we have to shore it up somehow. We have to replace that masonry. We have to maybe break it out, make it solid. We have to do something with it. It's complicated to do it right. I mean, it's those hairpins are something that do solve the problem. They prevent that crack from occurring. But again, why do we have the steel there? Is the steel necessary? And so on and so forth. Other things that we look about, like why we have that. Again, maybe a software is a really nice little tool here to see that if I put in a steel lintel, so I just model all the different elements, concrete, masonry, we model in the steel. If I put in a temperature load and everything slips, then it's just fine. If I put in a very simple steel beam, a 40-degree temperature change can cause a 30 kip force to be on those masonry walls. So that's why you can see why those cracks occur. I mean, it's a large force. It's not a lot of movement, but it's a large force because of the stiffness of masonry that's not moving. People ask me, well, if you have the temperature load and you have masonry, doesn't that also create stresses? Well, absolutely. But those are much more distributed, not nearly the same magnitude, so on and so forth. The other thing is just thinking about the common axial forces that you have on a wall when you have a steel lintel. You have limited bearing capacity, which again creates stress for concentrations, which are not necessarily going to lead to a crack. It's not necessarily going to be, but you can already see that the masonry is stressed in that area. Add a temperature load, and you're going to have a recipe for a problem. So again, dead load really doesn't change the stress flow, just minimally around those openings. So other things to think about when we have steel and masonry is making sure that those bearing plates are okay. We're going to talk about that a little bit in one of the next sections when we look at connecting connections within masonry or to masonry. Bearing plates that can get too large can also cause plenty of cracks and rust cracking to occur. So we want to make sure that we avoid those things at all costs. So again, let's stop using different material within a masonry wall. This building was, like I said, less than a few months old, and we already saw that crack occurring. We talked about rotational stiffness. We talked about a lot of different options that cause problems here. One of the other things that I've seen people do is trying to resolve some of these issues, but trying to be creative. They want it to look like masonry underneath, but they want to use the steel. Maybe, again, they're just thinking about this in terms of like prefabrication and not having, so they'll prefabricate like a masonry and then they'll put a steel beam on top of it to span the opening. Again, that's cute, but it's not needed. You could prefabricate that all as a masonry lintel. If you have limited depth, think about stirrups that you can use and add to be able to span that opening, which can work very, very well. So other complications that we have here with masonry, steel beams that are used, what to do with the jam reinforcement. Sometimes when we have these walls and we have these jams that we are trying to look at and think about, trying to make sure that we don't lose too much of the section due to the lintels. If I look a little bit closer at some of the bearing seats of the steel lintels, trying to keep the reinforcement continuous at this location so that we don't lose all the depth of it can be really, really complicated. Putting all these parts and pieces together, again, is something that the masons will do, contractors can do, but it does really add a lot of complication to this design. So again, if we have something that's continuous, we have no control joints, we have much cleaner joints, we have a very clean and better performing design. The other thing about steel is, again, I pointed to this a little bit earlier when I looked at the verifying the forces that we have within masonry lintels, but then talking about if I did have no arching action and I don't have the continuity between the lintel, that's what steel is. We really do have steel that we probably are putting control joints on one or probably both sides of the opening. And so then that steel lintel has to take a lot of load. It has to take all the load of the masonry and the roof above it, and it has no positive negative moment. There's really no relief for the design of it. Why? So then I'm going to go back to, again, why do we start putting steel in there if it didn't make sense? Well, control joints in this location in an unreinforced masonry wall, that made sense. When we did a lot of walls unreinforced, which again, 30, 40 years ago, I think we did a lot more of that. This all kind of fit together, putting those control joints in there, having the thing be unreinforced other than maybe the reinforcement and grout that you'd have below the beam, that would be a very common design. That would be a very common way to do the design. So we put the steel in, we didn't have to deal with the shoring. Contractors were shying away from it anyway. This is kind of what our design was looking at like anyway. Versus now when we're moving those control joints away, the load on that masonry lintel is pretty minimal. The wall arches around that opening. It really does allow for quite a bit more capacity in the overall system. The masonry lintel doesn't have more capacity than the steel lintel. The masonry lintel just has less demand, right? Because of everything that can stay continuous and stay all together, we have a lot less demand. So our demand to capacity ratio, our masonry lintel can do a lot better stacked up against the steel. So again, masonry lintels are fast, economical, match the wall, moves at the same rate of the wall, built in place or prefabricated. 6 to 10 feet pretty easily. Longer spans are possible. 12 feet can be pretty common, but there's really no length restrictions. 20, 30, 40, even 50 feet. Design-wise, masonry lintels can be used. In buildings like this. This is something that with that, especially with the mixed-use buildings, you have some pretty long span open spaces at the first floor of a lot of these structures. Having these long continuous masonry lintels can work really well versus adding in other elements. We really do have to break up that elevation. Think about control joints and it really gets pretty complicated pretty quickly. Again, this is a 52-foot long masonry lintel. You look at the cross section, there's a lot of reinforcement in it. There's a lot that was going on within this lintel. It looked pretty similar to what a concrete beam would look like. And so that it was pretty similar to the concrete beam design. It was kind of the same thing design-wise. So making sure that we think about what the potentials are. The thing that I think is interesting about this is sometimes people will point to the bigger the opening, the more it makes sense to go to, say, steel or something with more capacity. It actually makes less sense. The larger the steel section, the more force it's going to put on those bearing seats. You know, the longer the span is, the higher the stress concentration is going to be from the gravity load. You know, when you have the lintel that can be the same material as the wall, you know, that the ability to dissipate the forces, you know, and have arching action and have the ability for the wall to participate and not just be in an isolated element in an isolated bearing seats, that actually makes more sense the bigger the opening. So things to think about and consider design-wise. Oops, sorry about that. Other things that you can do with masonry, obviously, is you could put in a curved piece of steel, but a curved masonry lintel works really well. You know, masonry can be more to form than like steel can. Putting in a curved piece of steel, you can have torsional forces and stresses and rotations of steel. Put in a curved steel tube. Steel tubes are hard to radius too tightly. So again, masonry can be like concrete, kind of a something that you can form, you can reinforce, you could put in a torsional reinforcement into a masonry lintel, be able to have a little more capacity there. So that you can see what the masonry lintel looks like here and then here. So again, finite element analysis is kind of a pretty big part of this section. We're going to talk about that more this afternoon for a couple hours on different software programs that are available. Just ability to have the lintel be parts of the overall finite element analysis mesh, not separate entities for the lintel. We're not putting in separate pieces. We're actually kind of keeping them in together. So with the finite element analysis, it's going to be comparing pretty closely to the fixed end beam, you know, with arching action. So, you know, do you have to have finite element analysis to utilize some of the things that you've learned? Well, you definitely don't. I mean, the spreadsheet that I did, the fixed end arching action is really going to be, you know, what we would need in terms of the forces and the stresses that I would need to design for that masonry lintel. I don't need to have a finite element analysis program, but it certainly is helpful. You know, shear walls, we really can look at the area above the opening as a coupling beam. It really does pull into our perforated shear wall. It really does pull into the walls on both sides. So that really is going to be a very nice design. You know, so masonry and lintels are just going to be that integral with the rest of the wall, creating what I would call a robust, efficient design condition. You know, again, shoring can be solved with having prefabricated masonry lintels that can be lifted and set into place. We need to make sure that we have areas for that vertical steel to still be continuous, but still something that we can utilize prefabricating. And if I say I have a 4 or 5 course lintel, it doesn't mean that I have to prefabricate the whole thing. I can certainly just prefabricate the lower sections of that lintel, set that into place, and add the later courses on as we build the rest of the wall. You know, if I look at lintels and how to increase capacity, using the right F'(m) is certainly one way to do it. If I wanted to say prefabricate and I wanted to get more design strength, you could certainly even specify a higher strength of masonry for our lintels, and then use a higher strength grout if we needed to do that. That's certainly something that could be placing those control joints away from the openings, allowing arching action. It's just going to be a much better way of detailing masonry, making sure those control joints are away. Consider finite element analysis, if nothing else, just to understand behavior that much better, but maybe even utilizing it as a tool. Deep beams could be an option. We talked about that code provision from 2013, where they started looking at deep beam provisions. That's certainly something that it works really well to get more capacity for the area of wall that you already do have. To increase the moment capacity, if you had some problems there, considering making sure that you have the fixed end condition. We have top and bottom reinforcement that's utilized for our lintels. To increase shear capacity, really adding more depth is going to be the best way to do it. Adding more courses to be included in the shear into the overall lintel depth is going to be the best way to do it. You can add stirrups. Adding stirrups to masonry should be done with caution, though. You know, our detail could look something like this, making sure that our reinforcements off of the bottom. You know, maybe this is a pretty straightforward lintel. Like I said, top bars, bottom bars, single leg for thinner masonry walls, double leg stirrups could be added for walls that are 12 inches or thicker, but only use when more depth isn't possible. So the last little bit here on lintels, again, masonry and lintels, the advantages, they're integrated. They have heavy load resistance because they're working with the whole wall. It's complicated in some senses, you know, as it works together with the wall around it. So a tool like finite element analysis does help. It's a very efficient design. You can have the best use of materials if you do allow it to be complex and integrated. It's going to be easier to build in the sense that it's all similar materials. It's going to be one contractor. It's going to be a lot better performance. It's going to be a lot more robust. It does have a challenge of requiring either prefabbing it or shoring it. You know, the other lintel options, you know, it doesn't involve shoring. There's something that you can fly in, but the more capacity is really just perceived. It's not a reality. The actual lintel themselves have a lot higher demands. If I have isolated lintels that have a control joint at each end, and I have performance issues, construction issues, thermal issues, a lot of things that I have to think about and consider there. So that kind of wraps up that section. Different types of materials that you can use, why masonry lintels make more sense, and then some of the different finite element analysis tools that do utilize and design masonry lintels. So that, I think, would wrap it up for the morning. We have several more sections for the afternoon, including the software one that I've kind of been tipping my hand towards here. We can certainly answer any questions if you guys have any questions for the next 5 or 10 minutes. And then I don't know if we want to come back at 1 o'clock, or I think 1 o'clock would certainly be, that would make sense. 1 to 4 should be plenty of time to get through the rest of the material. So I'm going to hang out here for the next 5-10 minutes and see if there's any questions that anybody does have.
And Sam, I'm almost positive I heard you answer the question, but there was that Mr. Shikis asked again, are there the design examples that could be provided? But you did answer that one, right?
Yeah, so design
so
examples.
Okay.
Yep. I mean, again, it's the Masonry Designer's Guide is really going to be the best tool for that. There's tons of examples that are in there. You know, I've certainly had a few examples that are in here, but I didn't want to spend too much time on examples, just trying to cover all the material today. So, yep, good comment. Like I said, I'm gonna go ahead and put my mic on mute. I'll hang out here for the next 5-10 minutes if I see any questions come in. Otherwise, if that's okay, we'll get started back at 1 o'clock.
Yep, that's definitely okay. And I'm going to do the same thing. I'll be at my computer if anyone's got any technical questions or issues or something. But I'm also going to mute myself, and I'll be back at 1 with everybody else.
Yeah, thanks for the question, Gregory. Yeah, I'll answer it again right at the beginning, right at 1 o'clock. But there, right with masonry and lintels, there would not be steel plates used at the bottom of the masonry and lintels. It would be just masonry. So the lintel blocks, the U blocks that would be there, would be the bottom of what you would see. There's definitely detailing that would have to be considered for how to say, especially if you had a cavity wall, how to bridge that gap. And so we have some information on that, bridging that gap with a masonry lintel and um, bridging the gap between that and say a veneer is something that's, and certainly you can use just a lighter angle or something like that to close that gap, detailing wise. Other options there as well. So no, that's a good question. So like I said, I'll answer that again when we come back as well. Well, hello everybody. Good afternoon. I hope everybody is able to join us. And can you continue for the day? A little bit about myself. I don't know if you guys have been hearing. I have a little, well, not a little. He's a large Bernese mountain dog that's in the background here. So I have a feeling he might be getting a little restless this afternoon. So if you guys hear any chirping in the background, or well, he might bark too. So just a forewarning. Hopefully everybody's hopefully he's not too loud. So is everybody with us this afternoon?
I believe so. I know I'm back here, so let me see if it looks like everybody is. So
Excellent, excellent. Okay, so why don't I go ahead and get started? I did want to just answer the question that Gregory asked right at the end. He asked if there are no steel plates used on the bottom of masonry lintels, and that is correct. There would not be a need to put a steel plate at the bottom of the masonry lintel. You would have the U-shaped block that would be at the bottom of the bottom course of the lintel, which would be enough closure for, if it's a single white wall or something like that. And obviously, how does all the door and window frame, where does that bridge? If there's a cavity wall, does it bridge the gap between, or does a light gauge plate need to be added to fill that gap? There's a few questions there, but I don't know if that's where the question was leading, or if you had further questions to that. But with a masonry lintel, there would not be a need for a steel plate at the bottom of the lintel, and then certainly there wouldn't be a steel plate there to close that gap either. So there would need to be a different detail used to close the gap in a cavity wall, if that's what you're asking. So thanks for the question. Appreciate that. All right, if there isn't anything else, we'll go ahead and get started with the second half. We're going to go into connections to masonry and a little bit about details to masonry. We just kind of want to start to cover beyond the design, kind of how do we start to tie some of this stuff together? What are some of the details? What do they look like for our masonry designs? And then, so we'll have a couple more sections, this one on connections, next one on details, and then we'll go into some software for masonry design, and hopefully help you guys with learning about some tools that are available. All right, so just a really quick overview, again, just connections to masonry. We just kind of look at some of the different elements that are used there, bearing plates and bed plates, connections from lintels, veneers, so on and so forth, and then I'll look at a few details that'll be used, roofs and foundations, partition walls, storm shelters. Some of the things with masonry design is, we have from time to time, as I help out with different masonry coalitions, design coalitions, we encounter some things that slip through the cracks, some designs that get out the door and just don't make a lot of sense. This is a design for a steel beam sitting on a masonry wall that was almost 500 pounds. It was a very, very, very heavy steel plate that was used for a bearing, for a beam bearing, and it wasn't necessary. If it was necessary, that'd be one thing, but it wasn't necessary, and it just, the number of problems that massive plate's going to create in the future can be difficult. So we can do everything right design-wise, but if we land with something like that, it's just not going to be something that's going to serve us well over time. Other things, big bearing plate here, but the other thing that as we detail in some different elements into masonry walls, thin soaps and stuff to conceal different steel pieces can really lead to a lot of issues and problems down the road as well. So again, we just try to head some of that off with a little bit better detailing and a little bit better designs. This is a very large steel beam tying into a masonry wall, not necessarily a steel lintel like I like to pick on. but this is just another one of those compromised bearing conditions that really required a very extensive and costly retrofit. So, this is probably headed in that direction. It's a large steel beam, massive bearing plates, and again, this is something that definitely could have been done with just masonry. So, and we have a lot of little details like that. So connections to masonry, getting some of that stuff right can really, those could be certainly where a lot of problems exist for masonry. I think concrete masonry, clay masonry, concrete walls, a lot of those things perform very well. It's usually the connections to them or within them that can cause most of the issues. So, some of the common connections to masonry would be an embed plate or a bearing plate. Like tying in a steel beam into the side of a wall, an embed plate is something that we would probably use if we were tying into, say, a concrete wall or a precast wall or a tilt-up wall or something like that. It's just not the type of thing that we would need to do. I mean, it's a simple solution. It's maybe what we would do if we had a retrofit situation where we were adding the steel beam in later. We could fill the wall with grout, a couple of grout ports, and get some grout in there, but maybe not something we want to do. More creative solutions, I've seen people corbelling to pick up either a steel beam or pick up a floor. I've seen this actually more and more recently. Corbelling requires a little bit more detailing. It's not super common, but that can be a very nice, unique way to add a little architectural dimensions to some of these connections as well. And it's a much better solution than the embed plate. It's going to be much more economical. Just beam pocket is going to be a very simple way to tie in most floor members into a masonry wall, tying it in and making sure that we don't lose fire rating. A lot of times masonry is going to be in the interior building for fire rating purposes. So, grouting it solid or putting in blocks and mortar and grout to solidify whatever the pocket that's created for the bearing plate is simply going to be what we're needing. Anchor bolts and stuff like that for masonry. We have certainly different failure modes that we have to consider. We have tension and shear interaction that we have to look at to make sure everything works out okay. The thing is with masonry, we do have a lot of different options here. We have a lot of different things that are coming into the masonry elements. And making sure that we have, whether it's grout filled or hollow or brick, we have the right types of anchors that are going to be used for masonry design, making sure that we account for the different capacities that can be used. I mean, certainly anytime that we can have a grout filled or a solid brick or a solid masonry is going to be more capacity, but we don't have to. If we have a light connection or something that doesn't require a lot of demand, there's some different hollow masonry fasteners that can certainly have sufficient capacity. There was actually a nice article that I reference here in Mason Contractors that kind of looked at this guide and talked about some of the differences between some of the different fasteners that you can use for the various types of masonry walls that you want to tie into. Cast-in anchors or any of those types of connections to masonry. That's, again, anytime we're connecting to the face of masonry or face of concrete, the failure modes and just you can see the different embed plates or the connecting plates got pretty large in this project that I worked on. This was actually an architect that wanted to see some of those plates and some of that kind of exposed steel framing into the masonry wall. So it was an architectural demand for some of this design, but it certainly became pretty elaborate as we're tying into masonry. Usually, as we tie into masonry, tying the concrete, the failure modes that are going to govern the design is usually the concrete or masonry that we're tying into. So just kind of recognizing that is going to be important design-wise. NCMA Tech has another guide which can be very useful here, the design of an anchor bolt embed to concrete masonry. It's got a couple nice little charts in there for both allowable stress design and strength design. It actually comes with a spreadsheet that really looks at the connection capacities as we're tying into masonry walls. It's going to be looking at a single anchor either at the top of the wall or at the face of the wall, coming up with some of those different capacities for design. The different failure modes that you have the tension yield of the anchor, you have the tensile breakout of the anchor, which is obviously the masonry area breaking out, or the tension pullout of the anchor. Obviously, the second two equations here are going to be generally the controlling variables for your design. Nominal shear capacities, we have the shear breakout of the anchor, shear crushing of the masonry, shear pry-out of the anchor, all masonry controlled failure modes, and then the shear yielding of the anchor. Once we come to the bottom of the design, we have the axial and shear capacities. We're going to look at both of those and combined and making sure their interaction equations combined is less than 1. Again, there's a nice spreadsheet from NCMA that looks at some of these capacities. When connecting to masonry, some of the other things that we have to make sure that we think about and consider is we're connecting into these confined spaces. We don't want to have anchors that go through the masonry, through the grout, all the way into, say, the face shell on the backside or whatever you have. I mean, especially if you have a cast-in anchor, thinking about the confined areas of masonry, there's the compatibility between your fasteners on the masonry that you're actually tying into is really important. Putting in a anchor, at the top of the wall, that's not more than the say the lintel block depth, if it's near a lintel or something like that. I mean, trying to consider the different shapes that you have and compatibility between the fasteners and the masonry units is going to be really important in terms of coming up with connection design. Obviously, the connection design spreadsheets are going to be working well for you. And again, this is something that you can download for free from the NCMA website. One of the limitations of the spreadsheet is going to be looking at it as an individual anchor, looking at groups of anchors. This is a spreadsheet that I created. This is going to be really kind of combining what we have with NCMA and ACI and trying to create creating a guide or creating a tool for looking at groups of anchors, because often we have groups of anchors that we're designing for the capacities of them tying into masonry elements. Bearing plates are, like I said, going to be whether at the top of the wall or a beam pocket on a wall. Bearing plates are certainly going to be the preferred way to connect to a masonry wall. For bearing plates, I think there's a few other advantages that we can utilize here. We have a bearing capacity that we looked at. We have an unrestrained bearing capacity. We have a restrained bearing capacity. So the restrained bearing capacity is really looking at the bearing capacity that you have on a masonry element when you're within the interior area of the masonry element. So restrained would be something like a base plate or a bearing plate that stays centered on a wall that has, maybe 4 inches of width for an 8-inch wall. That's going to have a restrained capacity. The bearing on it's going to have to do with some distribution of force over a larger area. And it really does help us get a higher bearing capacity. Anytime that you would have, say, an 8-inch plate on an 8-inch wall, that would be an unrestrained. We have the bearing that's going to be stressing all the way to the edge of masonry, which is going to be then unrestrained and have a lower bearing capacity. So anytime that we can move a bearing plate away from the face of the wall, it's certainly going to have a much bigger advantage. The other things about bearing plates, bearing plates aren't required, certainly by code, and anytime that we're distributing force to a masonry wall from a steel element, sometimes just setting the steel element on the masonry, maybe you just need a setting plate. Do you actually need a bearing plate to distribute that load? Other things to think about design-wise. So again, a couple of little simple illustrations to try to point to what I'm talking about here with the restrained bearing area. The top view in the image in the upper right, the green area is going to be what I would consider the bearing plate. So the area directly under the bearing. area A1 is going to be kind of that primary area. So when I can move that plate away from the edge, then what I can do is I can draw 45-degree lines down to create a larger area A2. So anytime that I can move that bearing plate further and further centered on the wall would be the best case scenario. But the bearing area is going to be, all the way up to 2 times the initial bearing plate size. So we can have a lot higher capacities for bearing anytime that I can move the plate away from the center of the wall. The other thing with dealing with bearing plates is, looking at this mason that had a bearing plate that one was coming nearly to the edge of the block, but also had to be inset into the block because of the size and thickness of the plate. So that required cutting and modifying the block to allow for the bearing plate to fit within the block flange areas. And that just requires a lot more construction time and cutting. And the truth of the matter is a bearing plate. So if I look at the 2 different plates, if I look at a 7x7 plate that comes to the edge, practically to the edge of the masonry, I have a A1, A2 in the effective bearing area that's 49 square inches. If I had a 5x7, if I have something that's a little bit smaller, the 5x7 plate inside 1.25 inches, so away from the edge, has a larger effective bearing area. Why larger? Just because the plate actually can grab some more length and not just width. So the 7 inches wide, helps me grab what ends up being an effectively larger bearing area. So that's kind of an interesting. I mean, that's obviously tested, and it's a larger bearing plate can have less capacity when it comes to the edge of the masonry wall. So that's a really interesting and very important thing to recognize and look at as we look at bearing on masonry. One, bearing plates that come to the edge are a difficult thing to deal with in terms of rust proofing and making sure that it doesn't have any conflicts with any of the aesthetics that we're looking at, but then also it has less bearing capacity. And so that's something really important to recognize and realize. So embed plates or bearing plates, it usually depends on the situation. An embed plate, unless there's an aesthetic reason for it, it's usually going to have a lot less capacity. It's going to be adequate for light loads. Maybe it's something that is when you post install, or like I said, if there's an architectural reason for doing that. But otherwise, a bearing plate is going to have generally more capacity. It's going to have more vertical shear loads. Certainly, if you size the plate correctly, it's certainly going to make a big difference. So connecting to masonry, other connections to masonry, I think, tying in frame, we talked about infills, participating, non-participating. Connecting to masonry can be really, really critical. We want to use masonry for resisting shear loads just because it's something that it's got a lot of capacity, and it's got a lot of capacity in shear. So, connecting to them, there's some hybrid design guides that are out there for connecting frames to masonry. There's different types of hybrid designs. I mean, when we have a steel or a concrete frame and we infill with masonry, how we distribute and transfer the forces from those other elements into masonry. The code, we try to look at a couple different types of hybrid designs. Type 1 hybrid would be kind of a gap all the way around. So we're really kind of building the structure, the frame, whether it be, again, be steel, be concrete. We leave a gap all the way around just because that's easier to build. It's easier to build up the masonry, leave some spaces around each edges. What that does do is it reduces the masonry to just being an unloaded, non-bearing shear wall, which is going to have plenty of capacity. Anytime that we could go to, say, a type 2 hybrid, where we build the masonry up to the underside of the structure, what that does do is it makes it a bearing shear walls. So something that's going to be in bearing is going to be a lot better in shear. The difficulty with that is the construction wise, building up to the underside. You can build up and get close, and then you could grout solid, from the top to the underside of the structure above. So what the masonry groups try to do is try to create some sort of details and methods for giving designers some options for how to create these connections and bring this stuff into masonry design. One of the nice little marriage of materials that I've been exploring and looking at a lot more is post-tension concrete slabs and masonry walls, these infill walls. They're very nice because post-tension concrete, we don't like to have a lot of walls in particular. When we build the PT slabs and we stress the slabs, we want to be able to just have the slabs sitting on columns so that they can move effectively, and we can create the compression force that makes the post-tension cables the most effective. The nice little marriage of materials here is the masonry that can come in after the fact and be an infill, can participate as a hybrid wall, but it doesn't restrain the slab from moving. So it's a very nice little marriage of materials. Again, it's a concrete and masonry hybrid frame that works pretty well. So it really allows for pretty normal sequencing of construction, and that really can be, like I said, pretty beneficial to the overall masonry design. Storm shelter connections, we didn't get into masonry storm shelters. We didn't quite have enough time to fit those in today. Just a really brief overview of storm shelters. We have certain areas of the country that have to be designed for much higher design loads, having velocities that we have to design for more than 2 times the standard velocity. So our design pressures get very, very high within storm shelters. And so having masonry being able to be designed for that is certainly anytime utilizing all of the different capacities of masonry, doubly reinforcing, maybe horizontal, vertical reinforcing. A lot of the being able to make storm shelter work really comes down to the connections. The connections for masonry, into the roof is going to be, one of the things that we have to take close consideration for, making sure that we have, the roof framing or the roof slab or whatever we have actually tied into the masonry wall. We have very long embeds or bars that we have to develop down into the masonry wall. So creating that continuous load path for masonry in a storm shelter, and then that goes all the way down into the masonry, into the foundation, making sure that we fully develop all of the reinforcement that we have that goes all the way down. Now, certainly having all of those bars fully developed, that certainly does give the structure that much more rigidity. We have a lot of connectivity between, say, the foundation and the walls, both the slabs and the foundations and the roofs that we have that are tying into the masonry walls. So that does make it even more robust. But certainly the continuous load path is going to be important for making sure that we have a storm shelter that's able to function without anything kind of failing here. Looking at kind of the practical side of what does that look like, storm shelters do have walls that are reinforced at 8 inches on center, and they're probably going to be doubly reinforced. So it's going to be a lot of reinforcement that are going to be added in these design situations. Like I said, though, having the hooks and the ties into the roof deck, the roof slab is going to be really important to making sure those storm shelter connections maintain their integrity. So it's all about load path and connections, foundation to wall, fully developed, not just dowels, masonry foundation walls, continuity, better connection options over the concrete stem walls. Having a similar material all the way down to the actual footer is definitely going to give us a better continuity. We're not switching and having different bars and dowels in the wrong locations and stuff like that. We have a good continuity between them when we take masonry all the way down the foundation and wall to the roof, making sure that we have bond beams. We're probably going to be grouted solid, so we don't have to worry about bars being in ungrouted cells, but making sure that we have bond beams and then anchorage at the top. We have doors and windows to walls, so making sure that all of those have continuity. Anytime we get into any of these storm shelters, we look at all of these different connections and the reinforcement that we have within these walls, and making sure that we don't have unnecessarily small walls either. We want to make sure that we take control joints out and make these walls as continuous as possible, both vertically and horizontally. Veneer to structural height, if it's used for impact resistance, you can certainly have a structural brick veneer, which would be something that would work very good for impact resistance, and then that could also be something that we tie back to the structural wall, or maybe it's a single wipe design. So masonry connections, we need to know and make sure that we utilize that full strength that we talked about this morning. Laps and document on drawings and embed plates, and a lot of things to consider there for connections to masonry. So I'm going to switch over to detailing for masonry. So a lot of times with detailing the masonry, in addition to some of those connection designs that we're looking at, finally getting, whether it's specifications for materials or it's connections, but kind of bringing all this together and making sure that we get design drawings that actually meet our design intent is really obviously going to be pretty important for us as designers. So different notes that we want to put on drawings. I have some do's and don'ts that I think are pretty important, and we'll kind of cover some of those here. So material notes and things that we put on drawings. We have general notes. What I try to recommend is don't try to define reinforcing for masonry in the notes. I mean, we wouldn't do that type of thing for concrete slabs or concrete walls and other important structural elements. We want to make sure that we don't try to do that for masonry as well. We don't put in catch-all notes where we try to make sure that we have a certain amount of reinforcement in there. I mean, make sure that we actually label it appropriately. Don't define control joint locations in notes. We talked about that in the movement joint section. We want to make sure that we put our control joints on elevations or on plans to try to make sure that those are very clearly defined for our contractors and those that are building the masonry walls. And we also don't want to put lap lengths in notes. No 48 times diameter bar. We talked about that this morning, how that is something we don't want to use. For the design strengths, we talked about this in terms of F prime M. We don't want to just call it the strength of masonry. We want to call out each individual piece. We want to call it the blocks. We want to call out the grout strengths and the mortar types, and make sure that that's all working together. When I say don't define maximum reinforcing spacing, that eliminates unreinforced walls. I think that's a very reasonable option for partition walls. And anytime as structural engineers, if we put a kind of a catch-all or cover or but statement on there in terms of maximum reinforcement spacing, then we eliminate the possibility for unreinforced walls or make that more confusing. And so we have to be careful with that. And remember that when we do start to reinforce walls, we can reinforce them at even 10 feet on center. If it's a shear wall, 8 feet on center, we really can't have a minimal amount of reinforcement to walls. We don't have to add a top of wall bond beam to all walls, especially those partition walls can be pretty costly to add. So putting that in the notes, I've seen notes that indicate that we want to have a bond beam at the top of every wall. That can be problematic as well. When I say don't define control joints via notes, I mean, we have different requirements. We have brick veneer, or we have structural brick, or we have concrete masonry that have different movement requirements. Expanding and contracting, they have different widths to the joints that we have to define. So we want to make sure that we are as specific as possible about those. Designers are required to locate those joints. We can't just put in the no more than 25 feet. No, we can't put those in notes. We can't just try to describe, where they go. We actually have to specifically try to locate them. Don't try to define it with words. Again, this is the section of the code that actually says design and detail the veneer to accommodate differential movement and indicate the type and location of movement joints and project drawings. I mean, the code is pretty explicit with wanting us to locate those directly and exactly what they look like on the drawings. Masonry design notes and lap splices. Again, lap splices are different for a variety of reasons. We talked about that a little bit this morning when we were talking about reinforcement. You know, all the different variables that come into determining lap lengths. Bar sizes certainly have a lot to play, but reinforcement in the center or at each face, that changes lap lengths. Our reinforcement spacing can change it, our masonry strength. And so we just want to make sure that we have maybe lap lengths in our schedules, or we have them very explicit in terms of you know, the strength of masonry used, and then you know, the lap lengths that are used. Again, here we have a W1 that has a number 4 bar that only has to be lapped at 12 inches, and when we have W3 where that number 4 bar has to be lapped at 20 inches. Just different requirements for different situations. If we have W1 on 90% of the project and we just have a couple small walls for W3, we don't want to lap our number 4 bar 20 inches everywhere. If we can be explicit about this, then that can certainly help design-wise. You know, details that really show a lot of information, I think, could be very helpful. You know, some of these details in terms of a general layout for reinforcement can be very useful to contractors. You know, where we want to grout, where we don't want to grout, where we want to lap the bars. You know, what some of those details look like. Do we want to use joint reinforcement? Do we want to use just a mid-height bond beam? You know, all those different things that can be useful for whether it's an interior wall or exterior wall. You know, both showing an elevation and then maybe a section can really be helpful to determining some of that information. You know, I mentioned this morning there was a code provision that showed the different locations, tolerances for reinforcement. So what we did, we just made a detail. The detail that kind of shows where the bars can be located, you know, how they should be spliced, how they can be, you know, the tolerance that we have for the wall. That makes it really, really direct in terms of, you know, how we can place those bars within walls. And then certainly anytime that we're out to the job site inspecting a project, we have that information right in front of us. So we know exactly what bar location to expect. Next, we want to talk a little bit about some of these wall details, prototypes, and designs. You know, again, we talked about shear walls. We talked about the different types of shear walls. We talked about provisions for shear walls. I highlighted a couple items there because those are shear wall requirements, reinforcement within the top of the walls, vertical reinforcement no further than 48 inches on center. Really, really important to consider those items for shear walls. Partition walls are not shear walls. You know, so we want to make sure that as the code gives us the ability to isolate those elements and really lightly reinforce those elements. You know, when we look at value engineering for partition walls, we look at simplifying those walls, trying to make sure that we don't have any unintended horizontal. I've seen partition walls that had horizontal reinforcement in a low seismic area. So seismic design categories A, B, and C indeed don't need that horizontal reinforcement. Possibly no need for top of wall bond beam. I mean, that, you know, that's up there for shear walls, but that's not necessarily something that we need. Minimize the vertical reinforcement. We don't need to reinforce at 48 inches on center. So that can certainly take a lot of cost, grout, reinforcement out of the wall, and also limits the amount of connections that we would need at the top of the wall. We only need to connect the wall maybe where we have bars located, and then maybe the bottom of the wall, we really don't need much of any type of connection. Maybe we had some minimal connections at the bottom or none at all. Partition walls don't have to have a mechanical connection, or if they do, it can be very, very light, simple dowel at the bottom. You know, so any details with the 3D detail or just some sections showing that light reinforcement or lightly connected at the top, no bond beam at the top, can be really important. Sometimes we have a vertical cantilevered wall for a partition wall. There you'd certainly want to have the dowel at the bottom, but what does that look like at the top? Or maybe we do have it connected at the top, and again, what does that connection look like? What does the base of a partition wall look like? Again, the lighter the dowel can be, the simpler that can be to install. Don't need a separate footing, usually just need some sort of, depends on the soil conditions, but oftentimes just a thickened slab and a a simple dowel can work very well. We don't need to have usually that developed. Top of wall anchors, I mean, there's a lot to be said here. We have a lot of different ways to connect the top of the wall, but the lighter and lighter the connection is, the easier it is to perform. And just trying to utilize some of these connections. Now, architecturally, I've seen more and more of the details on the left where we have a connector that's just enclosed in, say, a top of wall that may be grouted solid, or some limited, connection at the top that allows for the wall to move in plane, but it doesn't allow it to move out of plane. So there's some nice connectors that are from Holman and Bernard, but then there's also other manufacturers, suppliers that are giving us some of those as well. You have channel connections at the top that could be either designed or they could be a proprietary product as well. The other things, and we pointed to this a little bit this morning in terms of partition walls, the code's going to give you some requirements, but there's also just doing some design quick calculations and seeing that most of your partition walls in seismic design categories A and B don't have to be reinforced. They're very lightly loaded. Even a 6-inch wall going 14 feet high doesn't have to have reinforcement. If you get into a slightly higher seismic design category, or you like to put a little bit of reinforcement in your wall, this isn't really going to change your cost of your partition walls much. To put a number 4 bar at 10 feet on center, and that's still going to give you a very efficient design. It's just seismic design category D and E and F where you need to add more and more reinforcement. One of the very nice things that IMI did was they actually created a free online software tool that allows us to look at partition walls for a variety of loads, for a variety of different support conditions and thicknesses, that allows us to review some of these designs. So you see the link here at the top. So partition walls can certainly be much more efficient. And so we actually created, again, these papers that I do show, I think I mentioned this morning, there's stuff that all is available. You can get in contact with me and I can send, they're free. They've been paid for by somebody else. So it's just free information that we can provide to you that's based on either the masonry code or NCMA guide or a combination of the two. And so that's where we come up with some of these papers. So we both have interior partitions and exterior non-load barriers, so the non-participating infill walls. There's a lot of different types of definitions, so we have to be careful in terms of what types of wall that we have. Standard masonry wall is going to be a wall between floors away from a frame. An infill wall is going to be something that's going to be built in the same plane, bounded by a structural frame. So they're quite a bit different. They have different code sections that are going to be looking at them. There's going to be different design provisions. We have fee factors that change when we look at the different types of design. So we have to be sure that we're infill walls, that we're detailing it correctly. I mean, it's going to look the same. It's going to act the same. It's going to be pretty similar. So how we quantify this is going to be pretty important in terms of what types of design that we have. Anytime that we have an infill wall, we're going to have some sort of a strut that's going to be created because we're going to be tight to the frame, and we're going to have something that's going to be having different types of design requirements. So again, it's one of those we thought would make sense to put together a design guide or a guide to give people a little bit more direction so that we can do these designs efficiently. When I looked at some of the partition top anchors, a lot of those anchors are going to be pretty similar to what we had for interior partition walls. Probably to use this on an exterior wall, if you think about what the differences are going to be, certainly you're going to have some higher demand. You're going to have a higher load demand. We're going to have higher forces that we have to design for. So we're probably going to have to use a larger rod diameter, maybe a larger dovetail head. We have different types of manufacturers that are looking into this for us as we look at different types of connectors that make sure that we allow for the in-plane movement and slipping vertically. So again, with the guide, what we're trying to do is we're trying to give you guys some guidance in terms of the top of wall connections that you guys would want to use. But then we get into some of the actual tables. Again, this is pretty well defined. If we can look at different wind pressures, we can come up with the overall design guide. We don't have anything else going on here. So a standard wall is going to have 6 inches at 12 feet. It's going to be a 5 at 80. So that's going to be, again, just a standard masonry exterior wall, not tied together. If it turns into the masonry infill wall, then again, that 6-inch wall at 12 feet goes from 5 at 80 to 5s at 48. So you can see that the type of wall, how it's tied into the structure, what type of forces actually accumulate and actually get applied to the structure can make a pretty big difference in the overall design. So we do want to use some care and exactly how the elements tie together. So we're going to have a little bit of a review maybe on control joints here. Control joint locations affects design. We've talked about that quite a bit today. It changes the wall design, in-plane, out-of-plane behavior. Certainly control joints closer together are going to have less in-plane shear capacity of a wall. Control joint locations should certainly change our lintel designs. We talked about arching action, how important that is for an efficient masonry lintel, making sure that we have those joints away from the opening so that arching action can always occur. It would change a pilaster capacity depending on how much concrete and masonry would be tied into the design. What do some of the details look like for a control joint? I mean, there's different types of joints. You can put those in and we can actually have it filled with building paper. What is this called? The Michigan joint, I think by some people. That's how we create some sort of a grout key that's going to allow the wall to move in plane, but it's going to have that key that's going to prevent it from moving out of plane relative to one another. Certainly there's the sash blocks that we have with the preformed gasket. Again, that's another one of those that allows the wall to move in plane, but it doesn't allow it to move out of plane. Again, back to the 3D view of the Michigan joint. Certainly we can just put in 2 walls and we can have some sort of a proprietary connector that can tie together the 2 walls at a control joint as well. Other details to think about what we have in terms of reinforcement, at bond beams, how do we want to deal with bond beams and control joints? There's a lot of times that people are looking at bond beams to be continuous, except for maybe at control joints. We want to make sure that we have a smooth dowel or some sort of a means for the control joint to be effective at those locations without tying the wall together. The purpose of the control joint is to allow those stresses to be relieved. So at those control joints, we want to make sure that there's not anything tying those 2 walls together until the wall is moved or shrunk or relieves the stress enough so that can occur. Again, a couple different details and kind of exactly what that looks like. Masonry or steel column, what do we have in terms of the elements that we have, or what do we need for vertical capacity? How do we detail it? Masonry certainly can be, develop plenty of vertical capacity in an in-plane masonry pier or a masonry pilaster that bumps out from the wall. So a lot of times adding in the steel is just not necessary. There's a lot of, like I said, capacity that can be created here with this pilaster. Obviously, we don't want to have any control joints within the pilaster, within the width of the pilaster, but then it can be something that could be added on one side or each side. Again, this can be a common location for control joints just from the sense of we have very different vertical loads that are perhaps being applied here. Maybe they're going to have a lot of vertical load on the piers and not so much on the walls on each side. So putting in a control joint there would allow for a little bit of differential movement to occur. Or maybe we want to use some of the wall as compression elements and something to stiffen my pilaster if I don't have quite this size of 16 by 24. If I had something smaller, maybe I wanted to use some of the more wall length. So where those control joints go and how that relates to the pilaster is going to be important. Certainly with the pilasters, There's specialty blocks that you can have supplied for the project, and that can certainly help with getting vertical reinforcement, ties, and everything being continuous within the wall. Things that we try to avoid in the masonry industry is you try to avoid having conflicts between materials, something that a steel frame and a masonry wall sometimes don't always work really well together. We talked about steel lintels and masonry walls. Sometimes they don't work together really well. If we take out some of the conflicts between the two, it can certainly work a lot better and not have what's going to look like a pilaster, because you're going to have some sort of a cover plate, or you're going to have some sort of a bump out just to cover up what you have there. And then you have anchors at the bottom, exactly how to deal with that. Sometimes you can conceal it relatively well. Maybe you have to cut down the masonry face shells. That's just something that potentially could crack down the road. So again, steel versus masonry, we have to be very careful. If we have to put the steel there, maybe it's a type of construction where the contractor wants to go up with all the steel at once and then come back and infill with masonry. Well, then we're going to be left with details like this that we have to make sure that we work through and take careful consideration in terms of tolerances for steel and steel locations versus masonry, making sure that we understand the proper dimensions for masonry and exactly how it's going to work relative to the steel. We talked a little bit about steel versus masonry lintels, so we'll kind of clip through this a little bit quickly. In terms of benefits for masonry, you certainly have a lot of different benefits there. We have a pretty long span. We have, like we talked about this morning, prefabricated masonry lintels or precast lintels, making sure that we have our details that reflect this, making sure our control joints are away from the actual masonry lintels and jambs that we have located there. So whether it's an elevation or a plan view, we want to make sure that the control joints are out and away from our lintel designs. And then we talked a little bit this morning about what types of reinforcement that we would allow for the lintels, the reinforcement vertically, the stirrups or the top and bottom reinforcement that you can have that creates that very integral connection with the wall around it. Foundation design, we're going to kind of make a few different points in here in terms of the different types of foundation details that we can utilize. Just kind of let that sit there for a second. There's no need to grout solid below grade. I think that the big misconception that the masonry below grade has to be grouted solid. A lot of times people will reference the fact that they don't want to have any water infiltration, or they want to prevent any water from collecting here. And really, it's not going to be the masonry that prevents the water, or the grout that would be in the masonry that would prevent the water. It's going to be, waterproofing that would prevent water from coming in. Just like concrete masonry is going to be maybe a little more porous. It's going to let water through if the water is going to exist. So if we want to keep the water out, we really want to waterproof it. Grout and solid really doesn't have anything. You want to grout solid, say in this detail, you want to grout solid and have a bond beam at that transition from thinner to thicker wall, but there really isn't a need to grout solid below that design wise. No need to grout solid here as well, or here. Especially here when we have that continuity, we have the same wall that goes up and down. Don't need to grout solid, and here even putting that bond beam in, having that transition and dowel would not necessarily be something that we would have to do unless we'd have some sort of a connection or connector that would tie the two walls together. If we look at roof details, again, we talked about those bearing conditions and bearing plates and making sure that those can stay towards the interior of the wall, making sure that we have those and the headed studs that stay within, if it's a lintel block, that stay within the depth of the lintel block, so that we don't have conflicts there between the headed stud and the actual block itself. So, something 4 inches long would always work. Something 6 or 7 inches long, you'd have to use either a bond beam block or some other special block to make sure that that bearing plate worked out just fine. So that can be a joist, or you could have a steel beam that, again, you want to pull to the center. I mean, steel beams, if it's a steel beam, it's maybe a heavier connection. So maybe you have some limitations there, but still putting it towards the center is still going to be better. You're going to grout that solid afterwards for fire protection. You're going to make sure that we try to tuck that plate into the wall as much as we can, and making sure that we have a good stub length. If making sure that we have the ability to have that headed stud not go through a lintel block, and here the lintel block is probably sitting down a course or two. Same goes for joist girders as we had for a steel beam. A lot of the same comments. Grouting solid or joist girder stability. Sometimes grouting those solid has to do with that as well. And again, trying to center those studs and have the right stud length. So all different details that we want to think about and consider. Bond beams needed, especially if this is a diaphragm and this is a chord element in the diaphragm. Maybe that's one of the times where your bond beam does stay continuous along the top of the wall. And then just a couple bits here on details and case studies for prefabrication. Prefabricated masonry, I think, is becoming more and more of an option that contractors want to consider. Prefabricated structural brick panels are something that I think can really speed up construction quite a bit. It looks like regular veneer is really going to be, if it's Interstate or Belden, or if it's some of the different structural brick manufacturers, they make common brick too. So you really do have the ability to have the structural brick panels match any sort of a brick that you would have. It can be as thin as 4 inches and reinforced. It can increase speed of construction, more flexible than concrete panels. I would say the thing about structural brick panels is just, the size of the panel usually is dependent on lifting capabilities that you have on site. So making sure that you have the ability to lift the panels and set them in place. A lot of mason contractors aren't going to have necessarily that lifting capability, so it's going to probably be a general contractor that would have to be evaluating whether or not they wanted to lift and set panels. So it can be a structural brick panel, or it could also be prefabricated elevator shafts. Where we're taking entire shaft walls and setting them on one another to speed up construction. This could be cold weather construction. Anytime that we can get into prefabrication of masonry, we're obviously eliminating a few steps in terms of cold weather construction that can really be helpful for the overall design. So just some conclusions on this section. Notes on structural drawings. Try to avoid some of those catch-all statements. Try to be specific with each of the materials that you're defining. And then masonry 2 and 3D details, making sure that you create standards and have them that are going to be coordinated with some of the detailing parameters that you've set forth, and some of the other sections that we've talked about, some of the design that we have. Be careful of typical masonry detailing errors so that we don't have maybe conflicts with other materials, or what some of the tolerances might be between masonry and other materials can certainly lead to potential issues. So that would be some of the notes and details and connections part of the presentation today. We'll take a minute or two if you guys have any questions on that. All right, so next, I think what I'm going to do is let's talk about sustainability of masonry. I think that's next in the list of the items that we want to talk about today. Doesn't look like we had any questions come through.
No, I didn't see any new ones myself, so.
All right, excellent. All right, so this section, what we want to do is we want to look at, again, the low impact masonry can have on the built environment, investigate how efficiently designed masonry walls can lower embodied carbon, look at different resources to help find EPDs, environmental product declarations with masonry materials, and then just kind of point to embodied carbon order of magnitude using the ECOM calculator. So, the thing about masonry is some of the obvious. The greenest building is one that already exists in terms of the construction of the actual building. I get there's a lot of mechanical and a lot of other things that we have to consider, but looking at masonry structures, they last a long time. This is a castle that one of my colleagues was able to kind of come through, and obviously that's built that we didn't put a lot of carbon into building that thing for many, many years. So there's a lot of things that we have to think about and consider with masonry design and the sustainability aspect of it anytime that we can reuse. And looking at existing masonry structures is not something that we covered in a lot. We didn't cover hardly at all today, if anything. And that's certainly something where we can have a separate conversation and look into that. But it's that's certainly a place that we have a lot of room for with the sustainability in masonry. So some of the fundamentals, I'm not sure if you guys had a lot of discussions here, but just a few of the key terms. Embodied carbon is going to be the sum of the greenhouse gases emissions released during the following life cycle stages of a building and its raw materials. So you have raw material extraction, pulling out whatever material you need to make the concrete masonry, clay masonry. You have transportation and manufacturing. You have construction, maintenance, renovation, and end of life for a product or system. So when you have to tear the thing down, what does that look like in terms of the overall environmental impact? The CO2e emissions released for a building or infrastructure use begins is sometimes referred to as the upfront carbon. So a lot of that stuff in terms of manufacturers of products, they can help you with a lot of the upfront carbon that's going to be used, for the creation of the structure. Some of the, using the building, the renovating, the end of life, that's obviously going to be outside the hands of the manufacturers, so that we're going to be a little bit limited in terms of what they're going to be able to provide for some information. So ISO standards, how to measure the embodied carbon for a building. We have the ISO 14025 and ISO 2193. So international standards that control environmental product declarations and kind of establish a core set of requirements will be considered as the PCR. So product category rule provides rules, requirements, and guidelines for developing an EPD for a specific product category. The PCR instructs on how the life cycle assessment should be conducted. Life cycle assessment is going to be a systematic analysis of the potential environmental impact of a product during its entire life cycle. So how to measure embodied carbon in a building? Environmental product declarations is going to be a third-party verified document that summarizes the EPD of masonry, for example, as a result of the LCA. Global warming potential, it's going to be kind of a threshold value in a product's EPD, which for masonry is measured in tons of equivalent per ton of masonry. GWP is a relative measure to how much energy the emissions of 1 ton of greenhouse gas will absorb over a period of time compared to the emissions of 1 ton of carbon dioxide. So now everybody wants to reuse those existing buildings, right? We don't want to keep going with some of this. All right, so embodied carbon, some of the greenhouse gases released during life cycle stages. So again, those extraction, transportation, construction, maintenance, renovation, reported as GWP, measured relative to, again, so again, some of the CO2 emissions before the building infrastructure use is sometimes referred to as again, upfront carbon is really going to be kind of focused on. So everything kind of delineating here, the embodied carbon, you can kind of see by manufacturing and getting to site and everything to getting a building up and ready to use. And, that's really where a lot of information can kind of be gathered. It's going to be, I think, a long time before operational carbon, before we can, kind of have some studies on buildings and how they work over time, and exactly what the overall impact is going to be for different materials. I think we have some inclinations, but certainly 2050 overview is really going to be kind of a standard that was created for looking at some of these different variables for structural issues. So embodied carbon challenge was kind of something issued in 2019 by the Carbon Leadership Forum. It's a group of architects, engineers, contractors, building owners, policymakers, just trying to take some big steps in decarbonization of the built environment. I mean, if anything, just trying to have a little bit of a focus on making sure that we do things responsibly, I think would be that would be a great statement to add in here as well. Trying to make sure that we don't unnecessarily add a lot of material or embodied carbon to some of these buildings. Globally, building and constructing sectors that account for nearly 40% of the global energy-related carbon dioxide emissions in constructing, that's a pretty big number. So SE 2050 was a structural engineers 2050 commitment program. It's all structural engineers shall understand, reduce, and ultimately eliminate embodied carbon in their projects by 2050. It's a bold goal, but like I said, that's something that we can try to achieve by different means and methods. So the 2050 goal to provide an accessible, sustainable program for individual structural engineers and firms with an accountable commitment of strategy to active engagement on projects, sharing information, all in the name of achieving zero net carbon structures by 2050. So educating structural engineering profession on the best practices of sustainable structural design and construction that will lead to zero embodied carbon by 2050. And it aims to engage in an embodied carbon tracking program within the structural engineering profession, thereby enabling the establishment of appropriate embodied carbon reduction targets until net zero is realized. So obviously any things that we can do to move in this direction is going to make a better and better impact on the overall environment. So any sort of reports on current embodied carbon impacts and trends of various structural systems of different regions throughout the country, advocate and communicate with clients, design, communicate, community, public. I mean, it's really trying to create a kind of an accountability tool for structural engineers to try to be more responsible with our designs and try to make sure that we're trying to move in the direction of being more sustainable with the structures that we create. I mean, anybody can design something that is going to have a very large carbon footprint in something that obviously costs a lot design-wise, but in terms of the material usage and stuff like that, we want to be working smarter and better and trying to achieve some of these goals, trying to reduce our carbon footprint nonetheless. So I would say the the vision, the net zero embodied carbon by 2050, it's a pretty big goal. I mean, considering what they're looking for, I mean that'd be pretty fast, I think. But that net zero means that the total impact of all components of the structural system net to a zero embodied carbon when considering all the stages of the building's life cycle. So getting to net zero will require changes in both the design and construction, as well as in areas where structural engineers maybe feel that there isn't anything that we can do. I think that's a really big statement. I mean, certainly it takes energy to make new building materials. So, there isn't anything we can do is certainly a statement that, I have felt from time to time when I look at some of these different objectives, but the more that we can do, the better is definitely something that I can wrap my arms around. So, the more that we can do, the better is better than there isn't anything we can do, I think. So moving in this direction. So any changes to a structure as it relates to embodied carbon must be approved by SER. So just a little bit of a distinction, understanding total carbon footprint. So net zero energy, a net zero energy building is one that produces as much energy as it consumes on an annual basis. So net zero is certainly different than a net zero carbon. Should be pursued as a whole life cycle approach to embody carbon reduction that includes a net zero operational carbon. So some different opportunities for engineers to reduce that embodied carbon in buildings, reducing the material quantities. I mean, that's just efficiency in design. That's looking at a design and trying to see where there's potential for using less material to achieve some of the same goals. You know, I think, you know, masonry definitely leans itself to this, you know, goal right here. I mean, it's masonry is in itself inherently less material. If you look at the similar design element of, say, a solid grouted wall or a solid concrete wall, most masonry should be designed as partially grouted and reinforced. It's got voids in it. It should be a lot less material than the design. Using larger bars and less grout would be a lot less material. I mean, there's definitely ways that we can start to explore using less and less material with masonry design, because it starts with the voids. Bubble deck was always something that I thought was a fascinating design concept. We use bubble deck would be a concrete slab where you place voids within the deck or within the slab so that it can be a voided concrete element, which has similar strengths and stiffnesses, but has a lot less material. And I'm like, well, that'd be great for reducing material quantities. And then you think about that, you inherently have that with masonry. So that's obviously a very good thing for masonry to look at, reducing material quantities. Mitigating thermal bridging. You know, again, that's some of the, you know, anytime that we can move away from some of the thermal bridging that we have, you know, whether it be a steel lintel, you know, in the backup wall that has that big steel bearing plate, you know, sometimes that's a big concern. Designers are used to having that plate there, you know, but just kind of seeing that that's a pretty big thermal bridge from the outside to the in, and you know, any place that we can reduce that's going to be better if we can eliminate it altogether by using a masonry lintel and then maybe a masonry or a floating steel lintel in the veneer. You know, we can almost eliminate some of that thermal bridging. You know, if we have a structural veneer, that's another place where we have very few connections between the outside veneer and the backup. So again, we can mitigate some of the thermal bridging. So a lot of different potential in places where masonry can come into play in both those first two options. Exposing the structure in lieu of providing finishes. Again, masonry is obviously going to be something that is made to be kind of exposed, and certainly it's been the aesthetic that a lot of people have looked for throughout the years. Use protective systems with performance-based design, using alternate systems that then typically used for a particular building type. You know, things that I think of there when, you know, the different topics that we talked about today, you know, looking at a hybrid system. You know, sometimes we have the frames that are there, and then we have these masonry infills. You know, does it take more design effort and work to think about how to connect those frames and connect those elements so that we can have one kind of homogeneous system? Definitely, that would be an alternate system that's taking use of the elements that are there. Another thing that I always think of when I read this line is, you know, you have shaft walls. There's a lot of times in a wood or a stud building that we have masonry shaft walls that are there for fire, for, you know, just kind of that hardened element that you want in on a project. Those are very, very stiff, rigid, strong elements. I've seen designers isolate, you know, from those shaft walls so that just because you have some differential movement between the stud structure and the shaft wall, well, let's figure that out. Let's connect those systems so that those can work together and we can use the full capacity of masonry. Utilizing lower carbon materials, sourcing salvage materials, designing for deconstruction, specifying materials with lower embodied carbon, producing materials as near the site, reduces the carbon footprint of transporting the material. So, you know, all different things where masonry can certainly be, you know, can be reused. It can be something that can be salvaged. It can be something that can be used again. Producing materials, I mean, masonry, concrete masonry materials are certainly produced locally all over the place, and so that certainly It does help a lot with reducing the transportation cost for some of the materials. So embodied carbon actions, reuse, reduce, and sequester are all different mechanisms for taking some actions on reducing that embodied carbon. Having an embodied carbon action plan in ECAP or ECAP, articulately tell you, educate your firm staff in embodied carbon. I mean, go ahead and going through the paces of understanding and learning some of the pluses and minuses for some of the different systems that you might have or some of the different designs that you might want to consider. Describe how you want to report the embodied carbon of your projects. Explain how you will document your embodied carbon reduction strategies. I mean, I think some of these just in, address how you will advocate within the industry. I think all of those things are going to be, just going through some of those steps are going to be helpful for, again, moving in that direction. Maybe we're not going to be able to get there in a specific time frame, but as we're going through some of these steps in education and having a plan and trying to kind of push this initiative forward certainly is going to help us make a lot of progress along the way. So one of the things that is out there is between now and 2060 is the world population will be doubling the amount of building floor space. I mean, the amount of built environment that we have is certainly increasing, and so we want to make sure that as we are looking at that and building up, we are trying to do that as responsibly as possible. As you can see that the amount of carbon that we have and we use to build this environment is pretty high. So embodied carbon will be responsible for almost half the total new construction emissions between now and 2050. And like operational carbon emissions can be reduced over time with building energy efficiency and the use of renewable energy, embodied carbon emissions are reversibly entered into the atmosphere as soon as the building is built. So, right, once it's built, it's done, it's built. There's not a lot that you can do with all of the embodied carbon that went into constructing it. So operationally, I mean, obviously we can make improvements over time, and we will. I mean, there's a lot of time, is on the side of, the operational carbon emission. So, as different innovations come into play, we can certainly utilize those. But the embodied carbon is something that's going to be there once the building is built, and there's really not a lot we can do with it. So I'd say some strategic areas of focus is just having that plan for individuals and firms to commit to establishing an ECAP or ECAP and provide staff with education in the field of embodied carbon, including life cycle assessment. Engage in the sustainable goals of projects and specific low carbon impact materials. Again, we talked about that already a little bit. And then share embodied carbon with your structural systems to a central database for understanding. That could certainly be hopefully within a firm for sure, within branches of a firm, but hopefully across firms and in the general structural engineering community at large. So the SE 2050 ECAP, the Embodied Carbon Action Plan, firms are given 6 months to develop an ECAP prior to the uploading of the SE 2050 firm account. Plan to capture opportunities unique to your practice. All the ECAPs are public, so I guess, again, trying to get this out to the larger community. Firm will have the option to upload their ECAP document or simply fill out a form outlining some of the minimums that they're looking at. So there's a lot of different requirements for SE 2050. So they have kind of the step-by-step program immediately within 6 months or a year, the returning year, some of the deliverables that they want to see with it, and a reporting plan for how things have went and lessons learned. So again, all different things that we can try to implement and build into making a better built environment kind of going on and into the future. So everything from SE 2050 is up online, se2050.org, where you can download and look at any one of these documents. So looking at masonry in general, low impact masonry, carbonization of masonry, compared to published values for wet cast concrete, dry cast, concrete exhibit significantly quicker rate of carbonization. This is attributed to the porous nature of dry cast concrete for interconnected pathway of voids to allow carbon dioxide in the air to readily access the hydrated compounds in the CMU matrix. That's a mouthful. Testing is still underway to determine whether or not this trend holds over time. So I think masonry's got to have, again, just with the voids and the way that it's manufactured and built, it has a good chance for a quicker rate of carbonization. So, you know, NCMA, you know, like I said, I've cited them several different times. They're going to be kind of working behind the scenes to try to do a lot of the work here for some of the reporting and information on masonry material. Obviously, trying to get more and more information out there. You know, trying to focus on the porous nature of dry cast compared to wet cast. I think it's going to be a really good, going to be some really good reporting. So there's a lot of, you know, potential with masonry just in the terms of not just the voids that are inherent within the masonry itself, but just the material itself is a lot more porous. You know, it's something where you can obviously have air and water that can move through the material. It's obviously not like a totally voided, but it does have a very good material setup for being able to work very well. So with all the research that's been conducted on carbonization of wet cast, quantifying carbon uptake, manufactured dry cast concrete products, including CMU, segmental pavers and slab segmental walls is limited. So more research is needed in understanding this, and you know, this carbon is a carbon sink once in service. So there's a lot of stuff that's going to be coming out from NCMA. A lot of this stuff is still relatively new, and so we're just trying to keep up from the industry perspective and try to get that information out as quickly as possible. The biggest thing that I think that we can do, you know, with masonry before some of the reporting is done, before some of the, you know, trying to define exactly what masonry is just having efficient masonry wall systems. You know, that's going to be a huge part of making sure that we have, you know, thinner walls, less reinforcement and grout, less material, you know, in there for our lintels and all the different elements for our masonry wall systems is certainly going to really help to try to control some of the overall impact that masonry has. You know, efficient masonry systems overview. I mean, the advantage is you have versatile field adjustable materials. You have non-combustible materials. You have equivalent strength to concrete with less material. I mean, that's just inherent in the partial grouting and reinforcement. You can have reinforced brick so that we can utilize even higher strengths of masonry and less material, thinner walls. I mean, there's a lot of things that you can take advantage of there. Less reinforcement for shrinkage and temperature loads just because of the prefabricated nature of masonry. So where to use structural masonry on projects? I mean, trying to utilize the material in new areas where we can, you know, again, where we need hardened materials, foundation walls, base and stem walls, frost walls. Those are typical areas where we see a lot of concrete still being poured into the ground, and it's obviously places where we can put in a masonry foundation wall. We can save a lot less, have a lot less material being put into those walls. And then with the partial grouting and reinforcement, you know, we really don't need to fill them grouted full of solid full of grout, just because there's really no need for it. And if we need to keep the water out, we just have to waterproof. Shaft walls, stair and elevator shafts, again, those are, you know, probably firewalls, but those are also elements that once we have them there, we want to make sure that we are utilizing them from a design perspective. Firewalls, shear walls, we have long perforated shear walls that we want to use, bearing walls, interior and exterior, partition walls, you know, no structural function, but, you know, those certainly can be thinner and unreinforced and grouted. You know, there's all kinds of places for efficiency. You know, a lot of times when I look at masonry and design, you know, I often am talking about efficiency. I want to make sure masonry isn't valued and engineered out of projects that it should stay in for, you know, and a lot of those same conversations and comments also apply for reducing the embodied carbon in a building. If we are efficient with materials and using less and less materials, it's certainly going to cost less up front, but it's also going to have a lot less embodied carbon in the structure as well. So again, masonry strength, this is something that I've made mention to once or twice today, making sure that we take advantage of the stronger, the minimum is the minimum, that's 2,000, the maximum 4,500. That's something that we want to make sure that we utilize. We have that typical 2,500 that we want to make sure that we do consider. You can even go up to 4,000 if you need to, if there would be some special reason to get higher strength masonry. We can do some prism tests to get even a thinner and more efficient wall. But you're looking at the typical concrete masonry at 2,500. Well, that's an environmentally friendly perspective right there. Just trying to take advantage of what we already have with masonry instead of designing to a lower strength. Certainly, anytime that you do venture into clay masonry, reinforced clay masonry, is you can even go even higher with it at prime M. Definitely not at 2,000, 2,500, but all the way up to 3,000 and 4,000 for the overall design. So again, consider some of those wall thicknesses and heights. Thinking about the overall design, 4 inches all the way to 16 inches with our masonry walls. 4 inches can be a reinforced clay masonry design. You can go all the way to 16 inches reinforced concrete masonry design. A lot of times looking at the efficiency again, what's going to be the most efficient? It's going to depend on the height of the wall. A 12-inch wall isn't always the most efficient. Sometimes there's just way more material there than you need. So a chart like this is a chart that I created for a local contractors to try to point them to when 12-inch walls should come out of projects. Anytime that we have a shorter design, should be a 6 or an 8-inch wall. So this chart's kind of giving them, at certain heights, when does it start to make more sense to use thicker masonry, and for shorter walls, when to make sure that we use less masonry. Those partition walls that we talked about, making sure that we have those as efficient as possible, least amount of material as possible, try to get as much reinforcement out of those, and all the connections. Anytime that we can make all of that stuff more efficient is going to be better, and certainly going to help with the environmental impact of the design. Don't forget about 6-inch masonry. When we look at materials and availability, 6-inch masonry is certainly something that can achieve quite a bit. I had it in a lot of the partition wall charts, but 6-inch masonry can certainly help save material on a project. So anytime that we're looking at reducing the carbon footprint and limiting some of the material, sometimes the move to 6-inch masonry might be a really nice move in that direction to try to save some material in projects. So what we did with the Masonry Society, NCMA, and IMI is we developed an overall checklist for structural masonry design, trying to make sure that everybody's, again, more efficient design-wise, but certainly that really does, from the cost perspective, but that certainly does help quite a bit for making sure that we're efficient in terms of environmental impact as well. We have some key points for efficiency, again, using that higher strength of masonry, using masonry lintels instead of steel, control joints away from openings. That's just going to give us a much better design. Transform from masonry back up to shaft walls into shear walls. Try to use your masonry as much as you can. If you have a shaft wall, make it load bearing. If you have a shaft wall, use it as your lateral system. That shaft wall is there for durability and fire protection. Try to utilize that wall for as much as you can for your overall structural design. Many of the partitions and interfaces can be eliminated and designed more efficiently than some of those top of wall connectors. We're trying to get much lighter connections, again, from a cost perspective, material perspective, and then just trying to use less and less, veneer material, any materials that you can. Environmental product declarations. To reduce the carbon impacts of CMU, the two primary options are reduce total amount of materials, again, efficiency, reduce total amount of Portland cement, reduce the materials, use a strength design, ESD, don't rely on empirical design. That's something that we talked about all day today. Empirical methods are moving into the appendices of the code, and so we just want to keep moving away from that and keep going. There's no reason to do that. Empirical, why am I so hard on empirical methods? Because they're conservative. They're overly conservative to save designers time. Any of those rules of thumb or any of those time-saving tips from a design is always going to cost a lot more in materials. So always try to use something that can be more environmentally friendly than that. There's some different block manufacturers that have achieved Portland cement reductions by replacing with Portland cement with supplementary cementitious materials like fly ash or slag content. So try to make sure that you ask about it, you look into that, see if that's a possibility. Again, if we're creating a specialty mix, maybe that's something that comes more into play, or maybe that's something that they produce off the shelf, and then we certainly want to understand that. And then specify a prism strength method rather than unit strength method. That's certainly going to be more similar to what you would do with concrete, but you definitely want to have some knowledge when going into it. You want to have some knowledge for what the actual products typically are, so that you can have a reasonable understanding for what prism strengths. Usually prism strengths, you can have 15 to 20 to 25% more capacity. So anytime that you can do that, you're certainly going to be using less material in your design. So EDPs and masonries, EDPs showing GWT numbers are available online. Some of the different numbers, just so you can see kind of where they are: brick and concrete, masonry, cement, non-fabricated steel. You can see the low GWT numbers for some of the masonry materials versus some of the steel counterparts. So embodied carbon order of magnitude is a nice little website for being able to determine what some of the embodied carbon would be for some of the different materials. Some of the other resources that are available out there: Carbon Leadership Forum, EC3 calculator, Sustainable Mines Transparency Catalog, all different places where we can get more information on EPDs and information on environmental impact of masonry. So I think some of the key things to remember here is to use or repurpose existing buildings. I mean, that's obviously the greenest way that we can be designers. Design for durability, optimize systems for material efficiency, know supply chain of the project, specify materials that sequester carbon, establish carbon targets for projects. I think all of those things that we can do to try to move towards the net zero, move towards the kind of that key place that we want to be 2050 is certainly going to help us be more and more sustainable with masonry and the other materials, certainly over time. All right, so that takes us to another end of another section. Why don't we take oh boy, 5 or 10 minute break? Well, maybe a 10-minute break be okay this time, and we could start back up at say 2:40, and then I think we'll go from 2:40 all the way to 4 o'clock. If that sounds good. Does that sound good to everybody?
Yep, that sounds good.
All right, fantastic. Hey everybody, welcome to the last segment of today. I think there was one other question that came in. Please explain the prism strength method. So really, prism strength method is a pretty simple, straightforward way to determine concrete masonry strength. It's really just taking samples of the masonry materials that are going to be used for a project, taking those samples and then testing them for the compression capacities for the samples. Prism strength method is going to be pretty similar to what you would do with concrete testing. You're going to take cylinders, you're going to break cylinders, see what the overall breaks are. With the prism strength method, you're taking samples of block and mortar, block, mortar, and grout, and you're taking those samples and you're testing them, and then you're averaging over 3 different samples to determine what the overall capacity is for the concrete masonry or the clay masonry, whatever the prism strength is for. So hopefully that helps out. Let me know if there's any other questions regards to that.
There is another question, Sam, but it's pretty lengthy. I don't know if you caught it. I think it just kind of showed up. Something about type S.
Sure. Yeah. All right, so type S is typically specified below grade. If we have a brick shelf which is below grade, is it required that those few bricks be laid with type S, even if type N is specified for the graded veneer or graded project? Would this still apply if we were using AAC, that is a starter brick below the veneer? In this case, what we're using is AAC as the thermal break block directly under a brick veneer. So the problem with type N is just, it's going to be a softer mortar. I mean, I think you could certainly use your engineering judgment. I would say that you probably wouldn't want to use type N below grade though. It's just, it's going to be softer. It's going to be, you know, more water is going to eat away at it more. And so using it below grade is just going to be something that's going to break down and not going to be as durable as something that you would have with the type S mortar. So I would say, you know, you could certainly use your engineering judgment. You probably would be just fine using type N for just a single course or a couple courses below grade, but just recognize the fact that, you know, especially if that's going to be bearing a decent amount of weight, then I would probably move over to try to use type S mortar. You don't have to move to type M. Type M is hard to use and difficult and costly, and you know, I would stick with type S if there's a fair load demand on what you're using. So hopefully that answered that question. I think that's the end of it. Yep. Okay. So certainly you guys can certainly ask. Oh, there's another question. Yeah, so the prism strength method is different from the unit strength method. I think that's what you meant. Let me see. I could probably pull up. I'm going to pull up that part of the presentation. Okay, so here's kind of looking at the two different options that you have. A being prism testing, ASTM C1314. Really, you're going to build a 2-unit high, 2 blocks, mortar, grout, and you're going to be doing the testing for, like I said, 3 different samples for prism testing. That's going to be one testing method for determining the strength of masonry. The unit strength method is going to be fundamentally different in that you don't do any testing. Unit strength method is just taking the materials that you have that you're going to be having for your project. The block strength, you're going to be using that. I don't know if anybody can see my cursor, but the block strength, say if I had type M or S, again, if I had like 9900 or 1150 in terms of the overall block strength, if I have S mortar, then I know that my design strength would be 4,000. So unit strength is just taking material samples and utilizing those material samples and the mortar type that you're going to be defining to determine the overall design strength. So it's just using tables in the code. The unit strength method is going to be more conservative. It's going to yield lower strengths. Prism test method is always going to have a higher design strength that you could be able to utilize for your project. So two fundamental differences there. If you want to get the most out of your masonry product and projects that you're looking at, use a prism test method. The reason that people don't use the prism testing method is just because the prism tests are taken generally close to the actual project construction. And so if your design strengths, if they aren't meeting, the prism tests aren't showing your design strengths being met, then you have to go back to the drawing boards. Maybe you have to get the block manufacturer to make more block. There can just be some slight delays. There does require a manufacturing process to happen in between asking for more strength. So it's a little bit different than the concrete in that way. And the prism strength method takes some time for the results to come back, and then it actually there's time involved in making the new units and having them shipped to site. So prism strength is always going to give you a higher design strength, but unit strength method, more conservative. It's going to be a little bit easier to do months and a year before a project is out. You can use the unit strength method. So one's more conservative, more reliable. One's going to be more exact, more efficient, but require to be done a little bit closer to the actual construction of the project. Hopefully that helps. Okay. Switching back to software for masonry design. And then if there's any other questions, we'll certainly, maybe we'll stop in an hour or so and we'll kind of have 10, 15 minutes for kind of just a wrap up and any other questions that you guys might have on any one of the sections. So the resources for this presentation, I just tried to put up there the different software programs and different companies that created the different software programs for just kind of the software review. A lot of different varieties of programs that are up there. You know, full disclosure, I actually worked for a software company for 5 years. It's getting back almost 13 years ago, 12, 13 years ago. And so working at the software company, I certainly had a perspective on utilizing software as much as you can. Since working in practice again and on my own, I understand that there's a time and a place for when to use software and when not to. And so I'll try to make sure that I keep that in mind as I kind of go through today's presentation. So learning objectives with many masonry software programs, you know, what they are and when to use different types of programs. I break apart software into kind of two different categories. Component design software is going to be a software programs that look at one element at a time. Whether it's a wall, could be a shear wall, could be an out-of-plane wall, looks at that one wall, looks at a single lintel, you know, designs that look at just an individual part of the project, kind of one at a time. Hold on one second, everybody. Okay, sorry about that. So component design software is really going to be meant to be a program that's just for, it's very simplistic programs, but they're very easy to use. Finite element analysis program would be a separate category of programs. So we'll talk a little bit about FEA programs, when to use, when not to use, and then maybe some common issues with software and how to avoid them, and then just kind of a summary of features at the end. So really, if I was to look at two different categories of programs again, I would say component design softwares really look at individual elements. Finite element softwares look at entire walls and all of the elements kind of interconnected with one another. Component design software is going to be more conservative. Finite element analysis software, I think more exact, but it takes more time. Certainly going to be a little bit harder to use than a component design software. So component design software, common wall, it's going to look at the design spans vertically, kind of an axial and flexure design. Walls above the opening, disconnected, span horizontally, and flexure. Opening, the jam's going to be limited and disconnected. Leads to usually component design software's jam designs get very, very conservative. A lot of load demand on those. And the lintel is also an isolated lintel, usually simply supported, as we talked about this morning, not necessarily realistic, but very conservative for the overall design. The other way to use component design software, so option one would be kind of doing it kind of as it was kind of drawn up to be used. The second would be extracting results from component design software or from a finite element analysis program, and just use because component design softwares work really, really good for code checking. They're very poor at analysis, but they're very good with doing code checks on elements. So if we can pull out information from an integrated finite element analysis model, it doesn't matter if it has, masonry design capabilities within the program, we can utilize component design software to do some of the design checks. So here we wrote a quick paper on how to extract results from some common programs and how to make use of some of those to be able to do the overall design. So finite element analysis, I think more and more people are using more finite element analysis for everyday analyses and designs, and I think that certainly we want to start utilizing it for the same reasons for masonry design. Hopefully it's going to be more exact. Hopefully it's going to be something that's going to be a closer representation of the real structure to give engineers like the best possible design tool to have a economical good design. But I would say it's a good representation of reality. So just kind of stepping back a little bit, what do I mean by this? I mean, so if this is me, right? This is a picture of me. What I want to make sure that I do is I don't create a finite element analysis model that looks like this. Just kind of a sketch, just a poor representation of the structure. A lot of times that's what we end up with, like a component design model is you just have a very poor representation of the real structure. You want to get something closer. You're not going to be, it's not going to be reality. It's not going to be the real model, but we want to do something that's closer. And I think finite element analysis kind of helps us bridge that gap. It helps bring us closer to, say, the real structure, similar to how this sketch is going to be a lot better representation of me than just that line sketch from before. So hopefully that helps kind of paint a picture of what we're trying to do with FEA. So look a little bit at some of the FEA stuff and how it can help us be a little bit better designers, be more accurate, more efficient. So I had this workflow up there before about all the other different stuff. And so if I add in software, it's the same thing. With masonry, we want to make sure that we don't stop short and use the wrong materials and just use bigger blocks and minimum materials, but we actually use software, we actually utilize it, and we start doing similar things with masonry as we do with some of the other material steel or concrete. So do all masonry programs use FEA? Certainly not. There's a lot of, like I said, component design programs where the analysis is going to be an isolated, simple analysis, and so finite element analysis is going to allow us to let things get a lot more complex, interconnected, I think more accurate results, more efficient designs, but definitely more time goes into building these models. And so definitely there's a plus and minus in terms of the overall analysis and design. So finite element analysis softwares, if I look at the softwares that are going to be in this presentation, there's really two different categories. Again, the finite element softwares, which is going to be the RAM, RISA, and ETABS, or any general FEA program that you can extract results from. And then component design softwares are going to be IMI's program, NCMA's 2 element masonry direct design. There's TEDS, there's quick masonry, EnterCalc, or again, your spreadsheets would all be component design, simple, straightforward programs. What's going to be a complex problem? I think the elevation that we have on screen, that could be a common elevation for, say, a warehouse or something like that with a couple doors or a couple windows and a door. You know, all of that gets pretty complicated. Sure, we can break that down into a simple model that we could design with component design software, but that would be very incomplete. You know, really that's going to be something that, you know, utilizing software for masonry is going to be the same as the other materials. We're going to have a lot better economical design. We're going to have better understanding of the overall structure. It doesn't mean that we have to use a finite element analysis. This is the practical side of me. I don't have to use finite element analysis for everything. You know, kind of like I did for the lintels this morning. I looked at the lintels with a finite element analysis tool. I don't look at every lintel like that, but now I know that lintels, masonry lintels that are integral with a wall are fixed end elements with just a triangular load like arching action would allow. I mean, that's a fundamental thing that I learned by using the FEA, and now I can just use a simple analysis to determine what the forces are for my lintels. I don't have to build an FEA of every lintel that would ever be created. I could use it, my simple you know, analysis with some of those understandings that I had for my FEA. So, but the other things that you can certainly do with software is you can look at hybrid structures where you have steel and concrete frames and masonry, how that shares those load, perforated walls, wall groups, you know, continuous basement and foundation walls with the main walls, you know, all of those things that you can do with software that really does make a big difference. So, you know, if I looked at finite element analysis and the different types of models, certainly a multi-story building like this, an FEA would certainly help me have a good understanding for some of the forces that flow through that structure, you know, through multiple different elevations, you know, but even something like this where I have a pretty straightforward, say, rectangular box, kind of an engineer's design, we still have FEA would really help with, you know, keeping those shear walls long and making that design pretty efficient. So in economical design, you still have some good places for an FEA to be used. We have 28-story load-bearing masonry with cantilevered post-tension concrete plates that certainly we're going to use a finite element analysis for the rest of the building. We might as well include it for the masonry. You know, FEA works really well on a building like this. This is going to be a kind of a mid-rise building in Missouri. It's going to be a little bit higher seismic, taking use of the masonry shaft walls and the stair shaft that it has, you know, within the project to use that FEA to understand what the actual forces are going to be in those elements. You know, this would be a building where I would say 3 sides of the building, you really didn't need an FEA. In fact, I wouldn't use it for the whole building, but I would probably use it for the front, that front elevation where I have long span openings, how the lintels interact with those piers. I don't know that that's really straightforward. Maybe that's arching action to a certain extent, but how does the actual forces actually develop in that elevation? You know, I probably use an FEA for something like that. By the way, FEA is finite element analysis. Whenever I just say I use an FEA, finite element analysis is what I mean by that. So here are the other types of structures that, you know, podium structures where I would maybe have wood walls on top of a steel floors where I have less columns. I have masonry walls that would say be continuous between the 2 different material types, and building uses, that's another really good reason for a finite element analysis, having all those different elements coming together. It'd be certainly helpful to have that design-wise. Here, this is an example of what I talked about before with the hybrid systems, PT slabs and masonry walls, and finite element analysis is going to give us a really good tool to be able to develop that design. You know, looking at school projects, again, we have a lot of different things going on with schools and a lot of windows and openings and a lot of forces. You know, putting all of that in an FEA helps us design certainly all of the steel elements, but then how that load transfers into, you know, some load-bearing masonry walls and elements like that can certainly help as well. Options for gymnasiums. We looked at this project that we were kind of doing a study for designer in terms of, do we have solid masonry walls for the gym? Do I have ribbon windows at the top, where it's just steel protruding above, where it's kind of a hybrid design, or do I have a series of openings? I mean, finite element analysis really helped us determine the design that they wanted to use for that structure. Hybrid designs with a steel masonry frame. This is a building that I used a little bit earlier in terms of shear walls. Finite element analysis obviously allowed us to look at perforated shear walls, the lintels, and the shear wall capabilities in that design is certainly something that we needed a little bit heavier, better tool to be able to do some of that design. This building, in terms of multi-story condominium, this is a project on the East Coast where we had finite element analysis that really allowed us to evaluate many different options. We were looking at different strength of masonry for the lower levels. We wanted to use the common, say 2,500 for the upper floors, but if we get the lower levels, and we didn't want the reinforcement and the wall thicknesses to change. So finite element analysis really helped us evaluate many different options there. So a lot of the reasons that I'm giving you would be really similar reasons for using finite element analysis for concrete or masonry. You can do all of these different scenarios, and a lot of the reasons would be true for masonry. But it doesn't mean that I always use finite element analysis software. Certainly, I would never use the finite element analysis software for a partition wall. It's just way more programmed than actually is needed. It's a pretty simple analysis. So that's the fundamental component design software, this IMI tool that's online. That's a great program. It's easy to use, and certainly works very well. Sometimes a gymnasium is going to be something that we can put into a component design software. Direct Design is going to be a program from NC MA that really works pretty well in terms of laying out part of the building and designing all of that. They're component designs, but they're many component designs all at once. So that can be very useful. Sometimes I have projects like this school where I have several different programs going on. I have parts of the building that we can use component design software, and then I have an elevation or two where it's just complicated. I have a long span opening. I have a certain use of that space in the school building that requires a big opening, and so a finite element analysis might be necessary just for a few panels here and there in the design. Again, school buildings, large projects, I can evaluate walls like this. Do I need to have control joints, kind of traditional control joints of this project, or do I want to look at this entire wall elevation? And using a finite element analysis software, I obviously can put the whole wall in at once. I can have it all interconnected, and I can see where the different forces and stresses would be. Some of the areas of this wall really look like Swiss cheese. So is this actually possible? Can we get this to work? The finite element analysis really helped us with this design, utilizing the stuff that we learned before about minimum amount of reinforcement that you would need to have be continuous to eliminate control joints was another big part of making this design work. And so limiting that and using a finite element analysis software really helped with this design. Other elements, building like this is a project that started as a, I believe, a steel frame structure, and they wanted to go to a load-bearing masonry for the aesthetics, I think, as well as some of the sound attenuation and stuff like that for the project. So, again, this type of building wouldn't necessarily lend itself to a component design approach. We have a lot of complexity with the exterior frames that really look more like moment frames. We have a lot of load sharing that would happen between, say, solid shaft walls and these exterior frames. So understanding how the force distribution would work in a project like that also required a finite element analysis to get the right forces and stresses for the project. These continuous lintels that I talked about earlier in terms of how to make those work and eliminate control joints, maybe that's just one elevation of this fire station. We have these apparatus bays that have pretty big openings, and the rest of the masonry project is going to be pretty standard. So maybe that's going to be one elevation that we look at with a finite element analysis. And we can utilize that, whether it's 3 doors, 5 doors, 7 doors. I can look at, what the actual stresses and forces, what the movement's going to look like, for that elevation. I also can do a comparison and contrast with if I had isolated lintels, if I had something like this, what is going to be my deflection on that elevation? If I have in-plane loads, I'm going to have all of the load that's going to be resolved with very thin, tall piers. So I'm going to have that stresses that are going to be a lot higher. I'm going to have a lot higher load demand on those piers. And then I can also do a compare and contrast between the two of them. I can see which one's going to deflect a lot more, and which one, see again what are the relative stresses are between the two different solutions. Other elements that I think are fairly complicated and certainly can utilize tools like finite element analysis. Anytime we have shaft walls, what I encourage designers to do is, one, to use the shaft walls, whether that's a cost-saving perspective, whether it's a reducing your carbon footprint, or however you want to look at it. The more we use the shaft walls for, again, they're durable, they're fire resistant. That's usually why they're in there. But then they're also very good at resisting load vertically, the gravity loads, the lateral loads horizontally. So it really can be used for a multiple number of purposes within a building. Once we have the shaft walls, what we want to make sure is we don't unnecessarily add control joints. Just because it's masonry doesn't mean it needs control joints. We talked about that in terms of eliminating control joints. Having a boxed wall group, though, is a little bit more complicated. Individual wall panels is easier to do by hand. Once I have a boxed wall group, I have a lot more complexity. Like I said, I have about half the capacity. If I break these apart and try to design these by hand, and I'm able to evaluate that and look at the actual overall demand. But it requires a more complicated model and a much more rigid tool to be able to design those elements as a box wall group. So again, anything 2 to 12 stories, masonry can be pretty effective. It can be pretty comparable to concrete, as long as I have those box wall groups that we use all the way up to building. So just again, a really simple example in terms of how component design compares to finite element analysis. So again, before we talked about if we had component design software, we really break walls apart into different pieces. And so what you can see when we look at the animation for the slide is you can see that different parts of the wall are moving differently than other parts of the wall. And if we think about, that's based on the stiffness of the elements that are in there, the load that I traditionally would put on those different elements. And I quickly recognize, if I think about it for a second, is masonry doesn't work that way. When we build this wall, we have it all interconnected, and masonry is really going to be moving together. So if I do a quick comparison between the old methods and the new methods, you can kind of quickly see, the masonry, as long as we let it be connected, is going to share the load pretty effectively across the wall. I need to have some vertical and horizontal bending capabilities, but I do have vertical reinforcement. I do have horizontal reinforcement and joint reinforcement, and I also could have some additional horizontal reinforcement with the lintels and sills and other elements. If I look at the moment distribution, I can kind of see what some of the forces are. We could look at it and kind of tunnel down like we did for the lintels before. We can look and see what the exact forces are. It's going to have the reinforcement that's going to be laid out. Basically, the quick example of reinforcement, I'm going to have less reinforcement on the typical wall panel if I use a finite element analysis, just because it can take into account the continuity between the wall, the foundation, and the parapet. So I'm going to have some efficiencies that are going to be built in there by having some of the continuity that would be considered. So that helps. I have jams that are going to be far more efficient because we're going to see the loads sharing capabilities of the wall as it's able to span horizontally. So my jambs have far, far less reinforcement. My lintels have a lot less reinforcement because I have arching action. If I do consider arching action in my simple support, then I'm going to be able to get pretty close with hand calcs to what the overall finite element analysis gives us. So again, I'm not just, if anybody looks at this and says, boy, he's just trying to sell finite element analysis. I'm not trying to do that. I'm trying to help people understand why this tool is important to use. It's not the tool that you would use for everything. I tried to talk through that, where there's certainly plenty of designs that you wouldn't need this tool, but when you do, you need this tool. It can be really beneficial for the more complicated elements of design. So for finite element analysis, when we teach on finite element analysis, we really try to break down the finite element analysis really into 3 different steps. Pre-processing, which would be considered modeling, solving the matrix, the solver, the analysis. That's really the software. That's the power of the FEA, is the ability for it to crunch a whole bunch of numbers very quickly. So the analysis piece, kind of step 2, is the software. And then the post-processing is really going to be 2 different pieces, where it's going to be results review and separately the design. So step 1, building the model. What I try to encourage people to do is don't just build a SketchUp model. Don't just build the overall geometry and the opening and stop thinking about it. What the program is going to do is it's going to build a finite element analysis mesh. It's going to take the general geometry that you enter in, and it's going to break that wall down into different pieces so that it actually can have evaluation, because it's going to evaluate the forces and movements at each individual node. So when we have all of those, that meshing creates an opportunity for the nodes to be created and an opportunity for all the forces to be evaluated at all those different points. So you need to have a mesh. You need to have something that has multiple different places of analysis within that wall panel, so we can understand a lot about the forces and deflection. And so we want to make sure that we have an appropriate mesh. We want to make sure that we have appropriate material. As we break this thing apart, we're going to make sure that we use the right material for the design. We have to make sure that we have the right boundary conditions. How the different plates are connected to supports. Is it vertically and rotationally? How is the slab connected to the wall? How is if there's a concrete slab, is it fixed? Is it pinned? So a lot of the detailing has to come into account as we build this model as well. So this goes back to, again, using the right material. This is a slide that you've seen a couple different times today. Again, concrete masonry, 2,000 to 3,000. Clay masonry, we're even up above that. But when we look at the actual masonry wall, we have to consider out of plane loading, vertical loads, in plane loading. Do we have a fixed base or a pin base? Do we have fixed or pin top of walls? All those different elements to consider in terms of connectivity. And then in terms of stiffness, do we have a crack section factor? Again, that 0.5 is kind of from the code. Way back earlier this morning, we talked about using a reduced cross section for masonry. So when we put it into a finite element analysis, we make sure that we have used that reduced cross section in our finite element analysis. Do we have compressible or fixed? That'll make a difference in terms of the vertical load distribution. Do we have a horizontal bending considered, included? Are we checking horizontal bending? Do we have out of plane crack factors considered? Do we have in-plane crack factors that we have to consider? Looking at the long wall versus the individual walls, do we have, if we do have all the different control joints, and then we have to make sure that we model in gaps in our plate elements. We have 2 different plate elements, 2 different nodes. We don't have a common node between them. We actually model in a physical gap for our model. So it's going to be important to make sure that we build in all the different complexities of the model. So again, I talked a little bit this morning about using that 0.5 crack factor, modifying the material stiffnesses. We actually created a couple papers for how to account for partial grouting in a finite element analysis, how to account for cracking, determine what your crack factors could be for your structures. Again, depends on the different types of forces that you have. Crack factors can be different in our designs. Solving the matrix, this is typically the analysis part. This is usually what most designers, engineers, when they talk about software being a black box, they're usually talking about this part. We go from creating this model, this beautiful model that's an imitation of reality, and then all of a sudden we jump from that to results. So certainly there needs to be some steps in understanding the analysis, making sure that we agree with the analysis that's done for the design. But this is where the computer really is effective and does a lot of computation very quickly. You know, a lot of the verification of the results is going to come in step 3, but the analysis is really kind of where the program is hopefully just doing a lot of thinking for you. It's not making any decisions, because really when we're reviewing the results and the design checks, that's when we're going to be making some decisions. So again, reviewing the results, the design checks, that's really looking at the individual parts and pieces. You know, what I try to suggest to people is verify the analysis. And how do you verify the analysis? Well, it doesn't start with a complex model. When we want to verify analyses, you really have to create a model that's a lot simpler, smaller model that we can get our arms around a little bit, so that we can have a ability to check the analysis. Don't just build a complex model and use it as a black box. Try to use a simple model, understand the analysis, and understand some of the results, and then you can move into the more and more complex, add into the complexities over time. So again, it's not just design. I would say step 3 is definitely the 2 parts of the reviewing the results and the design. Some of the best parts of reviewing the results is just going to be animating the structure. I think there's so much that can be learned about the overall building or the individual results by just reviewing the structure, looking at different parts and pieces to make sure that we agree with the design. Other parts of understanding finite element analysis would be, looking at different elements. We have different options within the program, and within those different options, it's going to create different results. And so I suggest that people often build similar but different models. If we don't understand exactly how the program's designing lintels or analyzing to create the forces for lintels, build a lot of different similar models so that we can kind of step by step go through them and kind of see what some of the forces look like. So this is kind of similar to what we did before, but this is kind of looking at the overall wall, not just the lintel elements like we were looking at earlier in the lintel section. So if I have a masonry wall panel, a single story with an opening, let's just look at the reactions. Looking at the reactions for a wall, oftentimes we have walls that are going to have, with no opening, it's going to be, the nodes at the end, I'd expect them to be a little bit less in terms of the vertical reaction, but then all of the nodes along the length of the wall are going to be similar to one another. When I add an opening, there's a little bit of complexity there. Does the opening, where does the load go that's above the opening? How do the reactions kind of get distributed? What are some of the behaviors in the area above the opening that changes, the way the reactions are created? So if I look at the model, I see these reactions. I would expect the reactions next to the opening to be higher, because the area above the opening certainly had some vertical load on that. How is that load getting shared? It looks like the end of the wall has a higher reaction. Well, how is that possible? How does the load get out there and kind of skip some of the interior portion of the model? Interesting. Let's look into it a little bit. If I play around with the wall and I create the wall panels and I create a compression member just at the top and bottom, it's simply supported, but it's a compression member. Apply all the same loads. I can see the reactions change. I can see the forces change a little bit, and how the loads get distributed. So kind of how is that affecting the overall model. Now, if I change it a little bit more, I have the two wall panels, remember, between are non-compression, but still simply supported. Now I can see kind of that expected behavior that I was thinking of. If it's a non-compression element and it's simply supported, then I can see the end reactions be minimal. I can see the reactions next to the opening be a lot higher. And then I have to start to ask myself, well, the reactions are different. Does this make any sense? Do I have the ability for the area above the opening to be non-compression? If I don't have a control joint in there, masonry is actually very good in compression. So, although this is maybe what I would have expected in terms of the reactions, maybe this isn't exactly what I should be designing for. Maybe I'm trying to learn something as I'm using the finite element analysis model. So let's take another step. So if I look at the mesh plates, I look at the member as a non-compression element, but the elements are fixed. So again, so if I say the masonry and lintel is going to be fixed to the walls on each side, if I say the element at the top is going to be fixed, I can start to see some of that load getting pushed out from the center. I don't have compression, but I have continuity in the fixity that I have between the two elements. So interesting. I take another step. So if I look at it again, compression between the members, I have it fixed. Now I see reactions that all of a sudden look like the forces at the opening, at the edge of the opening, are less than what the forces are at the ends of the walls. That's kind of back to that original analysis. So, with a masonry wall, do I have those lintels that are actually going to be fixed end members that are going to be compression elements that are going to be having that force not be allowed to arch over the openings? So if I take another step, so that's looking at it all with member. And why do I use 1D finite element members? Is because those are a little bit easier to understand behavior and think about how the different, how I can change them and tweak them. Now I look at plates. If I add plates back in there, I can see similar features here. I can see the reactions changing as well. I can see, again, the force kind of moving away. And so then I move all the way back to kind of those wall panels. If I have wall panels, what are some of the boundary conditions? What are the things that are a little bit different? So I start with a wall, I look at the reactions, I really break that wall apart, try to create a simple model, make some 1D line elements so that I can modify the properties of those line elements, see what those varying properties, see how that changes my reactions. All of this time I'm thinking about how masonry is actually performing, but some of the modifications that I'm making is just trying to understand what finite element analysis is doing for the model that I'm looking at. Some of this exercise was looking at, again, that lintel above the opening. Sometimes, looking at that lintel as a pinned element really is kind of silly. It doesn't operate that way. The analysis doesn't support, it being a pinned element. Doesn't it support it being a non-compression element? Really, all the analysis does point to it being a compression element with something that's going to have fixed end conditions with negative moments at the ends, some positive moment in the center, and again, utilizing everything that I know. And again, starting from simple and adding in the complexity really helps me to get to that understanding of both the software and of the lintels that I'm looking at for design. So from tips for using software, make sure that I use the right strength of materials. Try to understand what the actual strength is. Maybe use those prism tests to understand what the strength of materials. Let the walls be complicated. Put in the joints where I need joints, and take them away when we don't have joints there, so that we have a continuous wall. Make sure that we make the modification to partial grouting and cracking. That's going to be something that's going to be really important to modify the properties of masonry anytime that we do have different materials. If we have steel and masonry, you know, how the load's going to be differentiated and how the program's going to assign the lateral load to the steel members is going to be really depending on its stiffness. And if something cracks and it has less stiffness, we need to make sure that we tell the program that so that it can attribute the load to the right element. So within all these programs, you know, what I'm going to do is I'm going to do kind of a comparing and contrasting across different programs, you know, and I'm going to try to evaluate the programs. And again, it shows, you know, if you were looking for a masonry design software, it can help with that. If you're looking at kind of understanding when I go from one program to another, why I get different results, well, just seeing the different features, that'll help you understand that. If you are looking to do some different types of designs, or if you're trying to, you know, it can just really help you with understanding what different tools you have. So whether or not it's a component design or FEA, we'll separate those two categories out. We'll look at how the different programs handle all the different types of masonry elements. We'll look at material options. We'll look at loading and support conditions. And then we'll look at whether or not it supports ASD or strength design and other materials or other technologies as well. So material options, again, a lot of times for these programs, we're just going to define strength of masonry. Sometimes the programs are going to ask us for mortar type, you know, so sometimes it's going to be using a block and mortar to determine what the overall strength of masonry. That's not common. Most of the time you're going to enter in an F prime M, and the only reason that it's asking about mortar is if you want to design unreinforced masonry. So it depends on what type of mortar, you know, because they have different tensile capacities. The mortar cement having the more tensile capacity. Whatever you're looking at, whenever you look at a program, a software program, don't use defaults. I say that often. I said that 12, 13 years ago when I worked for the software company. Defaults are just starting points. They're not meant to be standards. Too often people will look at a software program and be like, well, hey, they're using this value, and that must be an industry standard. It's not an industry standard. It's just a single point to start, single point of reference. So reset the defaults is always really important. So here, again, a good example of entering in masonry strength. I'll enter in the F prime M. Make sure we start with the actual strength of masonry, and then we put in the mortar type. Again, here the mortar type is going to be used for determining an unreinforced masonry option, whether that's going to be relevant. If it's reinforced, then the mortar type really isn't going to have anything to do with the overall design. So NCMA has a program, a masonry design system where you actually can enter in the block unit compressive strength. And so that program, you look at not the F prime M, but you enter in the unit strength of the block and the mortar type. And then what that program is going to use, whether it's reinforced or unreinforced, is going to be using the mortar type, because if it's reinforced, it's going to be using still the mortar type and the block strength to determine what F prime M is for you. Kind of a nice little feature. Or if it's unreinforced, then it obviously matters the mortar type and the type of mortar to determine the tensile capacity if it's unreinforced. IDS quick masonry, that's another one where we're going to put in the strength F prime M of masonry and then mortar type for, again, if it's unreinforced. You have quick R wall, which is a retaining wall program. So a lot of different software programs, just kind of trying to show you a lot of different ways that they enter in F prime M, or TED, where you can actually put in, again, the unit strength of the block and the type of mortar so that it can determine the overall F prime M. And then intercalc as well. We're going to actually put in F prime M. Then you could also put in the modulus of rupture. So if any of those values are different than what's in the code, I think most of the time you're just going to use code, but then it gives you kind of, again, the specific tensile capabilities for an unreinforced masonry design. So getting to this table, this is one that I use for people from time to time to help understand. You can see if you just kind of look across the table, all the different options that you have with different software programs. It really does give you a lot of different abilities to vary the strength of materials up and down the different programs. Some of the programs have limits to the wall thicknesses that you can look at. I'm not sure exactly why programmers would do that, but you do have some differences there. We have vertical, axial out of plane bending, the in plane shear walls. That's not supported with the partition wall program, which makes sense. Partition walls aren't shear walls. Walls with openings. Again, a lot of programs aren't going to necessarily look at walls with openings because it just wants to look at a rectangular wall. So these component design programs, as they're trying to stay very simplistic, the one that does allow you to put in openings, what the program is going to do is its program is going to break out the wall and put it into the different components. So the direct design, where you can put in an overall building, but it's going to do a lot of component design calculations kind of all at once. Lintel designs, we have vertical and horizontal and arching action that we can consider for a lot of these programs. Some of these component design programs allow parapet, some of them don't. So understanding whether or not you put in the parapet, what the parapet pressure is going to be, are all going to be different parts of making sure you get your design right, and then whether or not you have columns and pilasters. So that's component design programs, those isolated elements, kind of their approach to masonry design. If I get into RAM elements, that's going to be one of the finite element analysis programs. Here you can see we're putting in the F''M. We're just putting that in directly for the design. And then within the design tool for RAM elements, you can see again, it gives you back the material that you selected, but again, asking for the mortar type. It's not going to change the material. It's just going to again be used if we get into an unreinforced design situation. Similarly, with RISA 3D, we asked for F''M, and then we asked for mortar type for unreinforced design. So that's the general program, and then the specific design tool for masonry walls, wall panel editor. It gives us, again, more options for utilizing the default values that we put in or making special accommodations per panel. ETABs is going to be another one where we enter in the overall F''M for design strength. This one's not going to be looking at an unreinforced wall, so it's not going to ask you for the mortar type. It's just going to ask you for the F''M, mainly for ETABs is going to be used with masonry design a lot of times with solid grouted masonry shear walls. It's going to be the time when we use ETABs. The thing about finite element analysis is we do have all the different options here for materials. We have options for in plane, out of plane loading. We have lintels that are going to be integrated in the overall wall itself. We don't have isolated elements. And then we have parapets and pilasters and columns, all that can be added in. So other things that I think are important is when we get beyond some of those initial capabilities or materials, or what do we actually have in terms of support conditions, and adding in some of these factors for modifying the stiffness of these elements. A lot of times the support conditions, loading conditions, there's going to be a lot of variability with the different types of programs. And it usually comes down to these component design programs. It comes down to what was the intent for creating the program. Obviously, a partition wall program is not going to have a lot of different loading options. It's going to have some of the options that will be available for support conditions relative to the different ways you could connect a partition wall. Something like element masonry, it's going to give you all the different support conditions up and down, or is it something that's going to be mainly just for lintel design? You can see some horizontal span that are be checked there with element masonry or intercalc. So a lot of different variables there. And then again, going to the finite element analysis, adding in a lot of different support conditions, load conditions, making modifications. Really finite element analysis can kind of excel at this. So again, this is not a pro finite element analysis talk. You're going to see some of the downfalls of finite element analysis here in a second. Really, when we look at the different design codes, This morning we talked about from 2011 to 2013 to 2016 to 2022. Well, if I look at different software programs, the application of codes is really varied quite a bit over time. Component design programs are always going to be better in terms of code implementation. They're going to be the design arm of software. So anytime that we wanted to use a current software using something from NCMA, LMA Masonry, or something like that is probably going to give you the best code support for design. If you get into the finite element analysis world, it can be a little bit sporadic. It's not necessarily going to be the full full options and abilities to be able to do some of the different code implementation that we've talked about earlier today. So a lot of what we talked about from the software review, what I try to do is I put a lot of that stuff into some design guides or some guides that are free and available online, both from my website or IMI's website. I have a tool for how to use masonry design within RAM Elements. I have a guide, quick start guide for using masonry design within RISA ETABs. We're working on the guide right now. Component design programs, not really, a guide's not really needed. I just kind of point to where they're available so that you can download those anytime that you would need to use that software. So kind of in conclusion, get to know the software, get to know the code and how it's been implemented into each software program. There's a lot of different capabilities and limitations that we have to take into consideration and understand. You always have to understand the capabilities, but more importantly than that, limitations, whether it's how it supports the code or the different options that you have for masonry design. Always have the loads in your model reviewed by a peer. That applies for any material, but that certainly applies for masonry as well. Check the load in your model with hand, and remember, software is a tool. You're an engineer. So that's, I kind of like to end with a little bit of philosophy. It's not your business to succeed, but to do right. And I think with masonry, we certainly have a lot of different capabilities. We have a lot of different options. Sometimes I think masonry over the years has been boiled down to taking the path of least resistance, trying to just use empirical design methods. And hopefully you can see over the course of today, when we started with codes this morning, there's a lot of good code development. I actually just got the 2022 code this morning. So it's sitting on my desk right now. I'm going to be looking through that. There's a lot of different things that are built into the masonry code for moving masonry into the design arena, similar to steel and concrete. We have a lot of different options and capabilities with masonry elements. We have a lot of tools available, and that's why I wanted to end the day with software. Using different software programs really does help you model and design masonry structures and pretty complex masonry structures. So whether or not you have a reinforced brick or you have a concrete masonry, you should be able to put in whatever different types of designs or analyses that you need in any one of the software programs. So I try to encourage people to look at masonry for all these different types of building types and try to stretch their understanding and capabilities with masonry. So that takes us to the end. There's a little picture of me in my office. Hopefully, if you guys have any questions, I'd be glad to answer those at this time. And really, we can kind of open it up. If it's a software question, we can look at those. Or if you guys have any questions on any of the other sections, I'd be glad to kind of go back and review and look at any one of the sections from today.
Yeah, definitely. We got about 20 minutes here till we're officially supposed to end. So yeah, definitely. If you guys have any questions, we got some time, and now would be a great opportunity to do that. So we'll leave it open here for a little bit. If we don't get anything in, it's not going to hurt to close a little bit early if we have to, but we'll just wait here for a little bit for any questions or whatnot, and then we'll kind of go from there and just go from there. So give you guys, 5 some more minutes to enter something. I think other thing we like to offer, but we don't really talk about, you can definitely send me a question and I can pass it along to Sam if he doesn't mind too afterwards. That's something we do often, and I don't want to put him on the spot because I didn't ask him beforehand, but usually people don't mind if that takes place.
No,
So.
yeah, no, I'm glad to answer any of the questions down the road. If you guys have anything with masonry design that you're looking at, and we wanted to look at something, I'd be glad to answer something over email. That'd be a great way to do it.
And I'm not really seeing anything coming in. I have a few things to say. So, excellent. There's one. Could you please show a brief design example?
That's really good. I don't have anything prepared in terms of a design example, so that would be a little bit difficult to do. Trying to think if I have a presentation that would have some examples in it. I don't think of anything else. Can't think of anything off the top of my head in terms of a design example for masonry.
Yeah, so just wait a little bit longer here. But well, what I was going to say is, well, thanks for the question anyway, Greg, and just as something for next time. But I do have a few things to say. So even as I'm talking, if anyone thinks of something, just put it in the box. We'll get to it before we wrap up. But I do want to thank Sam for all of his time and expertise and for giving an excellent program this afternoon. And I want to thank everybody for joining us. To the attendees, remember, I'm going to send you that quiz that you need to take here in a little bit. And then once you've successfully passed that, you'll be asked to download the verification of attendance for the class. And note that you can take that as many times as you need to, and there's also no deadline on when you need to take it. So, if you are busy right afterwards or something, don't feel rushed to do it. You can do it whenever you want. In that same email is going to be a CE request form. If you are a member of one of the groups listed in that form, make sure to fill it out and get it back to Half Moon. If you are not a member of one of those groups listed, then you do not need to worry about it. If you have any problems in the future, of course, you can call our customer service and they'd be glad to help. But I do want to let you know that you can always feel free to email me. The best way to do that is just respond to the quiz email that I'm going to send. And I get people who ask for certificates or tests or something from literally years after the course. So anytime you need to ask a question, feel free to. I still don't see any questions or anything. So again, I know we're a little early, but it's not too big. It's not a big deal. So we'll go ahead and finish up. Again, thanks Sam for everything. It's rare we have Half Moon's in Eau Claire. It's rare we have another person from Eau Claire with us, so that's pretty cool. Thanks to everybody for joining us. We're finished here for the day. I'll get that quiz out to you and have a nice rest of your afternoon.
All right, thanks a lot, everybody.